I'm currently in the third year of my PhD studies at the Institute of Theoretical Physics at Charles University in Prague. And this work is based on a paper I wrote together with my supervisor, Ondřej Pejcha, last year. So when we talk about isolated binaries and we want to accurately differentiate between whether a stable mass transfer is happening or unstable mass transfer that then can lead to common available evolution, we need a good understanding of binary mass transfer, among other things, of course. But the standard mass transfer models, or the models that are available in the literature, suffer from several practical and conceptual difficulties I will talk about later. So that's why we have decided to develop a new model. And all binary mass transfer models, including ours, work in the Roche geometry, where we look at the binary from the corrotating frame. And so if we draw the equipotentials in the orbital plane, they can look like, for example, on this plot. This is for mass ratio of 1 to 2. And the main goal is to come up with an expression for donor's mass loss rate as mainly the function of the relative radius excess, which is defined as donor's radius minus the Roche-Lob radius over the Roche-Lob radius. And this then serves as a boundary condition in a stellar evolution code, like, for example, MESA. And the existing or previous models are, I would say, they're developed very much with respect to the Roche potential. So when we have a Roche-Lob overflowing donor, there it is assumed that all of the mass that has greater potential than the potential at the L1 point flows along an equipotential towards L1 from where it falls on the accretor. But the true nature of the flow may be different, so there are some possible systematic uncertainties. Then, as the donor is transferring from Roche-Lob underfilling to Roche-Lob overflowing, there is this instant optically thin to thick transition implemented in these prescriptions. Also, stellar interior that is sonically connected. Like, for example, this area does not influence the mass loss in this model. And there is not the possibility to include additional physics such as radiation or magnetic fields, because the model is too simple to account for that. So that's why we have decided to develop our new model rather with respect to the geometry of the whole binary. So we assume that the mass is being transferred and flows mainly along the axis, which is connecting the centers of the two stars, and is flowing through the nozzle that is created by the Roche potential and is converging on the L1 point and then diverging again. And we start modeling at some point x0 below the donor surface, which is a free parameter in our model. And we model towards x1, which corresponds to the L1 point. And from there, the mass falls onto the accretor. And by implementing this approach, we are testing for systematic errors. There is no optically thin to thick transition. And the stellar interior now influences the mass loss rate. And there is a possibility to include additional physics, such as radiation and magnetic fields, by implementing additional terms into our Euler equations, as we will see later. And also, our model of mass loss is analogical with mass loss models through stellar winds, because it can be shown that mass loss in spherically symmetric stellar winds is analogical to a gas flow through one-dimensional converging and diverging nozzle, which is also called de Laval nozzle. So there is like another bonus feature of this theory. When it comes to the equations, we start with the three-dimensional Euler equations, including Roche potential. So we have the mass, momentum, and energy equation, where the Roche potential is not only included at the right-hand side of the momentum equation, but also in the energy equation, the total specific energy of the material constitutes not only of the internal and the kinetic term, but also it has the potential term. And then we make some assumptions which we think are reasonable. So first we assume that the mass transfer is stationary, so we can get rid of the partial time derivatives. That we assume that the mass flow is effectively one-dimensional along the axis connecting the centers of the two stars, which allows us to use hydrostatic equilibrium in the perpendicular plane. And then we make two assumptions which go hand in hand, and it is that we use lowest order approximation of the Roche potential in the perpendicular plane, and then polytropic equation of state in the perpendicular plane. And this allows us to integrate the equations over the perpendicular plane and arrive at the set of one-dimensional Roche equation, one-dimensional Euler equations with the Roche potential, where again we have the mass, momentum, and energy equation. And now we have the characteristic cross sections Q rho and QP that correspond to the density and pressure profiles respectively that are integrated over the perpendicular plane. And because we only use simple polytropic equation of state in the perpendicular plane, we are able to calculate their ratio analytically as a function of the polytropic exponent gamma. And we have an expression for the mass loss rate. So in principle, if we are able to solve the system of equations, we can arrive at the mass loss rate in our model. And so this is a set of three equations for three unknowns: velocity of the gas, density, and temperature. And this is a two-point boundary value problem. So we have two boundary conditions at x0 at the stellar interior, and then one at x1 at the L1 point. And we solve this by numerical relaxation code we have written based on numerical recipes. But in order to close the system of equations, we still need an equation of state. And in the most realistic case, we have used MESA equation of state provided by MESA equation of state module. And this is the result, which was also shown by Pablo. So we took one donor that was evolved in a study led by him in 2021 with MESA. And then a posteriori, after the evolution, as the donor was losing mass, we recalculated what different prescriptions would predict. And we found out that Pablo's prescription gives roughly twice as high mass loss rate with respect to Kolben-Ritter, and our gives roughly twice as low, which has motivated us to modify the Kolben-Ritter prescription, which is already implemented in MESA, and rerun the evolution again with modified prescription to account for our mass loss rate prescription. And here is the result of this experiment. So we see the evolution of relative radius XS corresponding to the inner or outer Lagrangian point, as denoted by the solid or dashed line respectively. And toward the end of the evolution, we see that there is a lot of happening. So there is a zoom here. And so we see that Pablo's prescription does not predict any L2 overflow, whereas our prescription predicts significant L2 overflow, which is associated with common envelope evolution, or in general, lower stability of mass transfer. So that's our result. And what I'm currently working on is implementation of radiation transport in flux limited diffusion, and also assuming that radiation and gas are at the same temperature. And So the flux is limited by the flux limiter, and the radiation energy density is given as radiation constant times temperature to the fourth power, where there is Eddington relation between radiation pressure and radiation energy density, and the Eddington factor and the flux limiter, there are analytical expressions for them, and we can derive again 3D time steady Euler equations, including the Roche potential, where now the red terms are the new terms, and we can go through a similar procedure as before, but this is still an ongoing work. So sadly, I don't have plots that I can show right now, but if you want, we can talk about it later in person. Thank you for your attention.
Thank you so much. We have about 4 minutes for questions.
I just wanted to comment. So when you say that there is no optical affine to optical effect transition, so by adopting that there is no radiation, you're already adopting the optical thick in the sense that you're adopting adiabatic evolution for your stream, for every stream. Further, when you say that it's a stationary flow, you're already going to the Bernoulli case. It just you can write it in the 3 equation, but they all converge to one Bernoulli equation. So in a sense, you're doing the same thing. It's just that you write it in a little bit more complicated math. Just a comment. And then you go to flux limited diffusion and saying that the temperature is equal to temperature of gas, temperature of radiation. You're going back to isothermal. All what I'm saying is that when you're trying to add more physics and you write more equations, you're essentially doing the same stuff. And so I'm just a little bit confused why you get the factor of 2 different from Kolben-Ritter, and whether it's related, because I didn't see how you connected to the donor materials. So I mean, see, you say that the previous prescriptions been suffering by not connecting to the donor or something. I didn't really understand how you connect to the donor. Is that related to that? I mean, where the factor 2 coming from if you essentially going to the same limit? You have, if you remove all the math and you just converge your equation, you do the same Bernoulli adiabatic as Ritter did. And you also even convert it to the same Q, which is effective stream. Now, the factor of 2, where it's coming from? Do you understand the physics? Like where the difference is coming from? If you do the same adiabatic stream, which is stationary, somewhere from in terms of physics, the difference has to come from.
Yeah, so if oh yeah, I don't have the results here, but even in the simplest polytropic case where we model polytropic donor, there is a difference between our results and Kolben-Ritter's model because the geometry is different. So even if we use polytropic equation of state along the, let's say here, along the x-axis and model a polytropic donor, because we have different geometry, we arrive at a different result than Kolben-Ritter. And then in this case, we use equation of state provided by Mesa equation of state model. So I think the difference comes mainly from using different equation of state. And another point you mentioned was that I think you said that we do not connect to the donor.
I'm asking how you look at it. I didn't say that you don't. I just asked how.
Oh, okay. Yeah, so this is, for example, how we connect to the donor. So we start modeling at some point below the L1 point. And there is a potential difference between the point we start modeling at and the L1 point. It is lower in the potential. And also, if you look at the stellar structure in a MESA profile, you can calculate the change of potential with respect to the radius. And if you have, you know what the value of the Rho-Schlob radius is, so you can connect in this way the radius to potential. So you know, if you know the potential structure of the star, you can connect it in this way to the potential structure around the L1 point, and you can map one-to-one a density profile onto the surrounding of the L1 point, and then you can choose an x0 point, and you can look at the value of density and temperature and other parameters in MESA, and you can take them as your initial values, and then you can solve our equations, the two-point boundary value problem, where you have three equations for three unknowns, and you have boundary conditions from MESA, the density and the temperature at the x0 point, and then you can derive critical condition for velocity that has to reach critical velocity and the L1 point, which is roughly, again, the sound speed, but not precisely. And then you solve the two-point boundary value problem.
Okay, I think we have a really short question from Floor.
Yeah, I just have a quick question, which is, did you also compare the angular momentum loss or like separation of the binary between the different methods?
No, we did not take into account angular momentum loss. We're just trying to focus on, for given, let's say, geometry and the binary, we were trying to focus on computing the mass loss rate at the given time as good as we can.
I'm Jan. I'm a last year PhD student working at HITS with Fabian Schneider and Saskia Hecker. So for most part of my PhD, I've been concerned with the hunt for stellar mergers. And if you remember the introductions from yesterday, I'm a theorist, I'm not an observer. So to hunt for stellar mergers, I computed a grid of binary evolution models with MESA. So I listed some of the settings / ingredients of my grid: solar metallicity. We modeled rotation and tides. Also important, the evolution of both components. And then it's been already a hot topic today. I allowed my models to become non-conservative because of the spin-up of the star, in the same way as Pablo and Kushik described earlier. So I have an example of one of these models here, where you case a mass transfers on the main sequence. Important here also to understand the models. We model through some of the contact phases. I mean, some, because we only model through the main sequence contact phases. So here you see a system that becomes a contact binary, detaches again, and later becomes a contact binary again. So what is going slow? Well, so computing a grid to find stellar mergers not only gives you stellar mergers, it gives you a whole lot of other information. And what I want to do basically today is show you what are some of my results for the mass transfer stability and for the mass transfer efficiency, and where do we find stellar mergers. So the full grid includes 0.8 to 20 solar mass stars, but I'm going to disappoint low mass star people today. I'm going to only be talking about 5 to 20 solar mass stars today. We have the full range of initial mass ratios and the full range of mass transfer cases, meaning the initial separations go from the mass transfer on the main sequence all the way to no mass transfer at all. So this and much more was compiled in a paper that was recently published. So you can scan the QR code if you want to get it on your phone, which is not an ideal way of reading a paper anyway, but still. So it's about 6,000 binary models. And I want to dive into the grid immediately itself. So what I'm showing here is a slice of my grid, all the models with an initial primary mass of 10 solar masses. We have the initial mass ratio on the x-axis and the initial separation on the y-axis. You immediately see some groups of the case A systems, the early case B systems. So these are systems where you're off the main sequence as a donor, but you still have a radiative envelope. Late case B systems have convective envelopes, and then everything past for helium ignition is case C for me. So let's look a bit at the evolutionary outcomes of this grid. And let's start with the yellow colored here. These are yellow colored models here. These are all my models that went to runaway or unstable mass transfer. If you want to know what my exact conditions are for that, because I was a bit vocal about it yesterday, don't ask me, and I have a slide for that. And so the thing with these runaway systems is that if you have a kind of fluffy, extended red supergiant donor and a more compact companion, then we expect these systems to become classical common envelopes. So where both cores evolve in the envelope of the donor. And then for these early case B and case A systems, we expect them to turn into contact binaries that will likely merge very quickly because this is an unstable situation. But I promised you stellar mergers. We get a few here, but most of them you're going to find in this case A contact binaries. And these are contact binaries that exist because the accretor, as a result of accretion, starts expanding. And if you keep expanding enough, then you're going to both be filling your Roach loop and you get a contact binary. Now, when do we get a merger? Well, I'm going to show you in a moment. It's not such a straightforward story, but a good indication to say we're going to get a merger is if this contact binary keeps expanding and you get L2 overflow and you lose angular momentum, you get orbital decline and you merge. So I don't know if the contrast is good, but you find them here and here. So this is kind of a story I just told you. You get a contact binary, it evolves, it evolves, it evolves. You get L2 overflow. I said, well, it depends on the outflow velocity and a whole lot of other things. But for now, for today, let's just assume that when we get L2 overflow, we get a merger and then you get a transient, which I learned this summer is not luminous and not red, but is a nova. But I used to think they were luminous red novae. And after that, you get a merger product. And I'm kind of overshooting in tomorrow's session now, but these merger products are obviously also interesting. What do they look like? How do they evolve further? For this last question, there is a paper published from Fabian Schneider, Philippe Zadlowski, and Eva Laplace from last week, where you're going to track these merger products up until they explode. And what I'm personally interested in now is, can we distinguish these merger products from genuine single stars, so single stars that evolved or that just evolved in alone, or at least did not merge with another star. And there are several ways to do this. So the first one has been done recently by Menon et al., where they looked at the surface properties of such stars. Another way to do this, and it's also a hot topic, is astroseismology. So there has been a paper from Earl Bellinger where he already did some comparisons, and there is a paper that I'm hoping to submit very soon where we're going to do more detailed comparisons between merger products and genuine single stars. And one of the big kind of smoking guns is something that Earl also found, is that if you compare this buoyancy travel time for such models, is basically a measure of how close your frequencies or your periods are spaced. If you compare those, then you can see that there is already quite a big difference there. Okay, so I talked about the mergers, but a contact binary doesn't necessarily need to merge. So what can also happen is that it detaches again. So we were wondering how do our case A contact binaries look like? And how do they compare with observations? So I've plotted them here, and as you can see, most of my case A contact binaries form at low mass ratios, while most of the observations are at high mass ratios. So a problem, but it doesn't need to be a problem, because if we look at the coloring here, we see that these yellow systems, they're runaway mass transfer, they're unstable, they're very likely to merge very quickly. Then we have the pink ones, L2 overflow. I told you before, they're also very likely going to merge, and then we want to observe them as contact binaries. And now we have the orange systems where, if you look at the hatching now, these are systems where the expansion of the accretor happens because it's out of thermal equilibrium. Now, if the star regains thermal equilibrium, it's very likely to shrink again, and it detaches again, and you don't have a contact binary. Oops. Or in the other case, this expansion just keeps going, and you overflow your L2 point again, and you merge. So most of these systems are either going to merge or detach, while the systems here, they are there because the star expanded on a nuclear timescale, the accretor star, and there's basically nothing telling it to shrink again, at least until the end of its main sequence. And this is also exactly, these are long-lived contact binaries where we observe contact binaries. So let's quickly go to the, I don't know how much time I have left. 0? No, my timer says 8 minutes. Okay, yeah, well, very quickly. So stable mass transfer, that's why we're here. We have a whole bunch of models where we have stable mass transfer that doesn't lead to contact. For example, case B and C mass transfer, which is also something I tried to say yesterday. If you look at the donor star alone, you expect unstable mass transfer because you have a big convective envelope, but you have to take the orbital evolution into account. And this is very non-conservative mass transfer, which helps with this. And this is something that Pablo was talking about earlier today. Everything that I hatched in green here are non-conservative systems where the matter that is not being accreted also cannot be pushed away using exactly the same condition that Pablo used, because I got it from his thesis. And so it's kind of scary or interesting. It's basically the whole diagram. So you see a lot of systems that we expect either some matter flowing around in whatever way, and then there is the work of Ruggiero, for example, or there is, here it is, or there must be some better accretion disk physics to explain this. As a kind of a fun thing, we just rerun the whole grid, switching off rotation, so we get fully conservative mass transfer. And I think we can all agree the landscape looks quite different now. So we get a lot of contact binaries and a lot of double core common envelope phases here. And then the last thing I'll show you is we did some population statistics. So with my non-conservative or my original grid, to get a lower limit of 12% for stellar mergers of all the interacting systems, and about 19 for classical common envelopes. If we now use a fully conservative grid, the numbers almost double. So we get to 23% mergers, 35 classical and double core common envelopes. So it's kind of the two extremes, but the differences are kind of huge, I would say. So I'll leave you then with my summary. I'm sorry for apparently going over time. Yeah, thanks.
Thank you so much for that wonderful talk, Jan. We have a question over with Floor.
Yeah, in the plot with the observations overplotted. So
Yeah.
what does the probability of the observations mean here?
The probability.
Yeah, there was like a like where you have like, yeah, this one. Like the observation points have also some PDF.
Yeah, they have some error bars, if that's what you're asking.
So the y-axis tells me how each observation, how likely.
No, yeah, so that's the confusing part about the plot.
Oh, sorry.
PDF is for my models, and then the mass is just for the yeah.
Sorry, I missed the other axis.
That's why figure captions are important.
I don't know if I've asked already this at some point, but you have the over contact models, right?
Yes.
So have you done this plot, but with the lifetimes of them to get the actual observable distribution?
We haven't done that yet. This was an idea at one point to do it, and well, we wanted to actually compare it between the fully conservative ones and the non-conservative ones. But I heard from Luc yesterday that apparently modeling over contact binaries without rotation, without Matthias's work on the tidal deformation might also not be great. So we might have to, but especially, yeah, we could do that for these models, definitely.
Yeah. Well, I guess that's not a reason not to show it.
No. Yeah.
It's also, it's important to know it, I think.
Yeah.
So I was about to going to ask you the same question. That was my first question. So you can do this time, weight, and make a direct comparison with the observation.
Yeah.
And my second question is that the merger. Can you tell me? Can you explain us about this buoyancy? You use this buoyancy time scale to distinguish the mergers from.
So here they are. So the buoyancy travel time is essentially related to the cavity within the star where your G modes can propagate. And so well, because the structures of the merger product and the general single star will be completely different. The Hertzsprung gap star is basically, in most cases, for low radiation masses, fully radiative, while for my merger product, it's actually igniting helium already here on the HRD. So you get a convective core, an intermediate convection zone. So the cavity where your G modes can propagate, they cannot propagate in convective zones, becomes a lot smaller. And this is already influencing the G modes by a lot. It's always, I feel like I had to do a crash course on astroseismology first. I don't know if it makes sense what I'm saying now.
I would like to hear it more later.
Yeah, we can talk about it later. Yeah.
Thanks for a beautiful talk. Really beautiful slides. Also, I really appreciate the advanced pie diagram, which shows how much the field has grown in 10 years. But I wanted to ask about the same plot that Flora asked about, the observations in there.
Yeah.
And I'm sorry if I missed it, but so basically, when you overdrew the box of where the mergers were, there's quite a few systems that actually fall within, observed systems that fall within where you expect mergers to happen. Do you think the observations are wrong, or do you think the theory is wrong, and you could still have these extreme mass ratio things?
I think you could still have them. I'm not in a position to judge whether observations are good or bad. The thing is, we do, well, according to the models, find models here that are also there because the Jupiter expand on a nuclear timescale, so long-lived models. So we're not saying that there shouldn't be any there. We're more saying that it does make sense according to our models that most of them are on the right side and on the left side.
Do we have any more questions for Jan before we go to discussion groups? Jan, you said you had an extra bonus slide for what you were discussing. I would like to see it.
Yeah, but it is interesting. I think I'm not saying that I'm correct in the way that we define runaway mass transfer, but it's a hard thing to do, right? And so what we tried is we looked at the mass transfer rate, and we kind of saw that if it's doing this kind of a convex behavior, and it doesn't recover, because on the next slide you see that it also does that, but it does recover. So if it does that, and the mass transfer rate also goes above the thermal mass transfer rate, that's already like piece of evidence one. And then the other thing we looked at is if the donor star also keeps expanding beyond its road trope. It's kind of a combination. It relates to what Natasha was showing yesterday, that what this I would call an unstable mass transfer. And this is a case where in the end you also get L2 overflow, where the donors are just keep growing and growing and kind of engulfs your companion star. So that's the way we tracked one-way mass transfer.
Thank you so much for that explanation. That was very helpful. I think we're going to do discussion groups now, if whoever's running that. Thank you, Jan.
Okay, so one of the things that we wanted to do is a lot of questions have already come up, some of them yesterday, and then actually in this morning's talks have been really good and reflect a lot of the questions that we had thought about. We thought we'd divide up into smaller groups to have really solid brainstorming session. The idea was to come up with some problems and not just think of, okay, identifying the problem, but what is the roadmap to figuring out what we do well on that problem, what we should be doing, what we should be thinking about, try and organize ourselves, what will come with new instruments, new observations, LSST, JWST, try and organize our community in some way. And the idea was that each group would present, like sit together, discuss, put together a slide, and then we'd come back and share as a bigger group the slides. And then this roadmap is there for everybody. Obviously, this is not an exhaustive list of questions, but you know, there were some topics that came up quite a lot. Say the. Is that one working?
Is it working? Yep, that's working. Okay, I'll use this one. Yeah, so the goal is I put the link to this slide deck in the Slack chat. So the goal is for everyone to split up. You'll talk about whatever problem you chose in Slack, and then sort of write up a report about what your main takeaways were from the discussion. And the goal is that we'll have these slides that we can all refer back to if we want to know sort of like, what is the state of the art in terms of this question? What are the open problems? What are, you know, observations or modeling that people would really like to see done? So we have a little bit more of a roadmap for how to kind of make progress on some of these issues that people have raised. So, I mean, this is certainly not a comprehensive list of things you could discuss in your discussion section, but some ideas that we just started throwing out. You know, what is the state of the art of the modeling? What is the best we can do right now? What observational constraints do we actually have on the problem? Is this problem unique to particular mass domains? This might be a sore point for me because I do a lot of low mass stellar evolution. And I think we have a little bit of an imbalance where there's a lot of people doing modeling in high mass. There's a lot more stars to observe in terms of low mass. So, you know, can we help each other out with some of that? We haven't talked too much about this yet, but we have a lot of interesting new observational missions coming up. So are any of those particularly promising for addressing these problems? And of course, you know, what new modeling approaches are needed? Do we need hydro? Do we need, you know, adjustments to the 1D codes? So every group will ask for a representative from the group to come present, you know, 5 minutes on this question and the main points we should take away from this conference about each of these.
So you should be able to pick an emoji that's in Slack that represents the topic that you'd like to join. And the idea is then they're in the slide deck on each. There's a question, you and your group will work to fill that out. Do you want to go through?
Yeah, so we can just quickly go through what we picked as questions. So the first one was what happens to eccentricity during mass transfer? So this one's come up a lot. I think this is a hot topic. We know that a lot of stuff is coming out of mass transfer eccentric. Possibly it's actually entering mass transfer eccentric, but we're usually modeling these things as circular. So what, you know, what are the implications there, and where should we be going with that?
And then how do we actually measure the accretion efficiency during mass transfer?
what is the efficiency? What happens if we get non-conservative mass transfer? What happens to the mass that's lost? That's come up quite a bit in these discussions.
Yeah, and then sort of related, a lot of people have been raising this issue of rotation in stars. And in a lot of cases, we very quickly spin up to critical rotation, and that limits the amount you can accrete. So, what are the theoretical expectations there in terms of when we're reaching this critical rotation rate? And we expect that that's limiting accretion. And then, the flip side of that is we know that there are systems where very conservative mass transfer is happening. So are our models really saying that's only happening in very close systems or in very particular situations that it can happen? And if not, do we have a problem here? Do we need new mechanisms to actually shed angular momentum in a lot of these cases? So there's a lot to dig into there, I think.
Yeah, and then in our discussions that we've been having about the stability of mass transfer, if case B, C, D mass transfer onto a main sequence star is actually more stable, which seems to be the consensus in some cases than we previously assumed. Should we be observing more of them? Where, how do we find them? And if we can't find them, why not? I mean, part of this question was, what are the systems what are the observational systems that are lurking out there that we don't see? How can we find them? How can we use new missions to actually answer some of these questions, and modeling as well? Like, what do the models predict? We already heard from Jan's talk about some of these cases.
Yeah, number 5, I think some people are putting up their models, and there's a quick slide, like what physics did we include in our models? So I would love if we could just kind of have a summary of like what things should be included in mass transfer models, like what stuff should we not be ignoring, and what are things that people haven't really looked into that might actually have a big impact on mass transfer.
Yeah, I mean, some of these things are uncertain for single stars, but I mean, then we double it with binaries. It's it's an important thing. And then finally, it came up yesterday about pre-main sequence star evolution. There are a lot of actually different fields that have very similar problems. Accretion is a universal process. What can we learn from other fields? Like, should we be talking to other communities where they've maybe made more advances? Should we be looking at what they've done? People like who do accretion onto X-ray binaries all the way to AGN, should we be trying to make connections with other fields and other evolutionary phases across mass regimes? Those are the choices. And then we'll divide up. So I guess in Slack, if you could select, I don't know how are we, I should check, I can check on my.
Why don't you check how we're doing?
Okay, so has everybody,
well.
everybody divided themselves up? I think we'll have should we do dragons over there, unicorns over here, octopuses, and then on one of each of those tables, octopuses, bees, and ladybugs. Doesn't seem like anyone is doing the elephants, the whole like evolution, but maybe we don't have those communities here. So it's a bit of a
So we will get back together. What time?
Oh yeah.
What time do we want to get back together?
I was saying maybe you should reiterate where it is or write on the board, like dragon here.
Yeah.
Sure. So we want to.
We have until 12, half an hour to come back.
Yeah, so we have 5 topics, so 5 minutes each. So let's all make sure we're back in the room by 11:30, so we can report back.
Cool. Okay, so dragons over there. Oh, what?
You want me to write it on the board?
Dragons.
Or draw a team of dragon.
If you're more artistic, you can draw. Yeah. Unicorns over here. Unicorns over here.
Nice.
And then octopus. We'll go octopus. Oh my God. Bees, ladybugs, and then elephants. I see we only have one elephant.
Yeah.
The elephant in the room, which is not in the room.
I have no idea. I feel deep. No. I think, yeah, I think you started a little bit later. Sorry about that.
Was
I would have let you just like go forever, but Emily, I feel like it's really hard to work with other people.
Well, it was gonna maybe.
Are we participating in these discussions?
I can leave them up, but I also linked in the Slack.
I don't know.
I'll show you one. So there's one part of the corner is like a mirror. When I was doing all the Lucid distributions of
Do you want their discussions?
basically shows this is the rotation rate relative to synchronous and the orbital periods basically cover
like I can say what I remember, but like without like
different initial rotation things. You see this, so
what I do know is that
okay, so this makes a big difference. No rotation. So this initial critical breakup, the initial rotation.
there was like a factor of two and there was
They're all unicorns.
Yes.
So what we did, so I was following the output certain things was one of the
stuff like that.
These are both cases of stars that are very
different tidal prescriptions. So because we have different
circular case, because it was supposed to reduce to like the standard equation, and it was doing something strange. Yeah, and this was when we were trying to use these equations. Why isn't it working? Yeah. So then after that, we were like, oh,
are you going to
I am
and then he walked away.
not like a.
What was that catalog?
One thing that is
Come around.
is it like this?
I need the 500 process sample, and it's.
I mean, I think like calibration. Yeah, you have to and just hope that the stuff that
Oh,
right ones.
okay. Oh wait, is this eccentric mass?
It is eccentric.
Yeah,
You know what?
I was gonna say, you like this.
I know. Right. Sorry, I'll just say.
I guess there's the ones on the Hayashi line, like the giants and stuff. That show that you don't have perfect circular rotation, but it seems you need a whole lot of angular
Yeah.
But we are only focusing on one.
That was what was motivating.
There were 5 questions within a question.
I'm gonna find one of them.
It's like an enhanced Taylor Sprout.
Also,
Oh, yeah.
Yes. I can just put it up if that helps.
Yeah.
where is the link? Which channel? That we can use for every start the same.
So actually,
I have opinions of both. Not just one. Accretion disks and spin off.
Oh yeah.
There is a differential rotation, it will create this magnetic field. I think some of these are a little bit on subject mass transfers, like are there new modeling approaches needed? Yes.
Like,
What do you mean?
But I think, so I think it would be very helpful to discuss why, like, what is the current state and what is missing?
yeah, I mean, otherwise it's always a solid body, right?
Yeah. So I think it essentially gives you solid.
I have one thing to say, I guess. So Adrian has this eccentric rotation.
In sequence stages, it becomes a bit trickier. And there you do get.
Are you already on the Slack channel for that base?
Oh yeah, get it.
Yeah, I did the Slack channel.
Also should be.
Yeah, we should. Should I take
I
out?
have seen it.
Then it's harder for you to run.
Yeah. Well, that's. That's fine. I think Poncho can explain the things that I was
Think about these rapid mass transfer phases.
By the way, it's not
Unless you
correct what I
achieve
said.
the rotation profile of the star sufficiently fast, that would just is a competitive effect versus just luminosity.
The Phil Davis is.
I guess for regular stellar evolution, it's just a very small part of the energy.
Well, so the, well.
But I agree, like 10% of the mass
So that he did pretty crude and thinks that that should be.
at Keplerian, the energy budget to fully dissipate all this rotational energy.
But one of the.
Never negative.
I see.
Yeah. So that's something that I think no one considers.
Like a sub question I have.
You should expect some form of distribution. Whatever the process is, there needs some.
Often model mass transfers.
But it's totally not obvious.
But I
How,
just seems to always never happen.
It used to be kind of the idea that if
all right, how much of that goes
the atomic time scales are similar, and then it's maybe.
I wonder, I mean, in a sense, you have
So if you're like
an initial situation where you
Well,
think
yeah,
all
that's
this
kind of like the
material
other
is on
thing,
top,
right? That's
but almost Keplerian. Well, it cannot be Keplerian,
But we would want a general thing that's
if
kind of.
that propagates inwards, you have a different energy, total energy. Whatever the difference is, somewhere. More or less we conserve angular momentum, but not energy. So you need to put it somewhere.
And did all of these
So
music
that's
calculations.
definitely something we don't
The thing
account
that came out
for
is that you do have relatively equal
conservation
mass
considerations.
systems. So your primary is between like 1 and 1.5 solar masses, and then your secondary is
Initially.
a little bit initially, and your secondary is a little bit less.
conserving momentum, so you don't need energy.
And your orbital periods are.
Well, it's just a different distribution of angular momentum.
And then he found
So
that
that's
the
just
way
pi
that
omega
he
is your angular momentum
Yeah.
for each layer. It will not give you the same total energy because that's omega squared I.
Yeah.
That kind of makes sense for normal stars because
Even
they're
if
not
you
that
reduce
mostly
it and conserve angular momentum,
French. So if you want to make it stable
you were essentially trying to sink to a lower
very
state,
early on or
which
very
would
late,
be,
so you really need to have
solid
it non-conservative. But I think that's a very different scenario than for like the star regime where you have more stable mass transfer.
yeah, no one considers that. Something actually I think I never thought about.
What are they now? You said they're initially.
Probably the energy budget is not the grid.
Now, what are they observed as? Okay.
Remember this, that you
I saw this in some papers by Patrick with Norman.
There are a few hundred days, I think.
Reading like.
days.
Isn't that common envelope like?
That's what I said, they're only
There's like very heated these.
these are like wide orbits, so they started on the
My
Arctic.
expectation would be that this would make all problems worse because it would then to close your stars. The closest star would have a lower critical rotation rate.
Initial orbital periods were like around
Then you go easier into this problem regime.
So.
But yeah, I said it before, but the thing that worries me in Adrian's
So the
model,
point is that
it's
we
not
can
so
find
much the
a
level of conservativeness, like all the binary calculations in the 80s, they started with conservative mass transfer because that's where you start,
I mean,
right?
it's not like a huge variable.
It's
So
manageable.
that's where you start, yeah. But it works with more the other assumptions that you have to take
We expect the
together,
physics
which is
to
that the
operate
mass
more or less
ratios,
the
that the model is only valid for mass ratios.
It's
that are
not
very
like
extreme.
calibrating
So in
overshoot.
where it says
We
Q
see
much
more
larger than
I
1,
don't know how far you go from the
you
convective
have to be
envelope.
larger than 10
This is
for
really
the
accounting for all the physics, like the composition profile or not.
Exactly, so I think it's not only the conservativeness that is missing, but it's just the approximations that Adrian had to do in order to even get a model out. And it just requires
which is
more effort to dive into it and look more
not the
into
young Fei, right? All of his, or Will, any of Will Scholl's models, right? They're massive star models. They're way more inflated.
I mean, Adrian, they did, like, I don't want to criticize it, but because
they are
like a really good addition to the model that was right?
There's
just one more step. And
A lot of, but there are papers that do things to conserve.
There's
Mass transfer. And they're on Slack
sonic
channel.
turbulent motions, and so
That's- yeah, I
turbulent
mean,
pressure
we-
actually lends
yeah,
itself
there's
to
some of them already.
highly
which does serve to
The only
extend the
problem
envelope.
with the Sopolo is if
Some of it is
close to
like
low eccentricity.
what you want to call
They use like delta just at periods. You're done.
right, but yeah, they are. They
long
are.
as you
We can make small.
The radius of like
I think
one
just pull
offset
up- I think that
is
was
something
what-
like 2/3
Yeah, I guess
is significantly farther out though, isn't it?
Yeah, but But you have to, what you have to be careful with comparing unphased models to MESA models is
I feel like Adrian always wanted
this, or what you call them.
he wanted it to like collapse.
Because it's true that you inflate relative to a MESA model that
Do it as a
flavored the 3D simulations with, but to say that that is a 3D simulation
The
of
delta
that
function
MESA
helps
model, I
you
think is a little bit misleading. So it's true also of the red supergiants that when we put in the red supergiant, it was sort of
Otherwise, it's a Gaussian or whatever.
thing. It becomes 800 or 1,000. Actually, the two red supergiant models in our
I've seen papers that don't go.
were both based off the same MESA model, that they have a kind of 200 solar radius difference. And some of it is because of the way you drive the inner boundary.
Yeah, so one of the questions I was thinking,
Like
does it ever increase
conditions at the base of a MESA model, or at the base of what you call the envelope,
eccentric mass
and
transfer?
you actually construct a completely different solution, which is pure radially stable. You then let the thing run until it reaches a steady state, and then it becomes its own structure. So I would say that I'm not too worried that the radii are extended based on against the MESA model, except the contribution from turbulent pressure, which seems to be
That's a baseline increase though, isn't it? Because you don't
ratio. It softens the, yeah, it contributes to hydrostatic equilibrium, so it softens the steepness.
So even just including from the Bill's analytic modification, that would add turbulent pressure, or let's say TDC.
Mostly the wider ones.
I don't think this is the way that you would want to do it. This way that you
The
had
turbulent kinetic energy density in
I was
TDC
just
kind
thinking
of
wider
maps onto
because
the turbulent pressure in
Right, yeah, tighter.
the 3D Euler equations, but not completely.
all this
More of a characteristic velocity of transport.
Implemented.
Same as MLT. It's a proxy and it's better than doing nothing.
Effects like the eccentricity, but you'll just have a bigger star, which is going to be. But yeah, this question.
Oh, but you can crank, I mean, if it's a convective envelope, you can also just crank down the mixing length or crank up the mixing length and you recover your radius. So two things happen, right?
For identical physics, right?
Well, so I mean, here's like, yes, but like if you look at say the 3D red supergiant, we find two things. One is we find an inflation of the envelope from turbulent pressure. We also find very high mixing length alpha.
The way we calculate mass transfer.
And so those two effects, if you want to ask like what would the radius of this star be, it's unclear that there's an obvious systematic difference.
Or with average mass transfer.
Just from these sort of mass radius.
Spreads it over the orbit.
The better thing to do for that is
And then
look
what
at
do you
nature, say,
with
what are
average
the
mass
radii of these
Let's
stars?
just do what we normally do in binaries, right? Yeah, just whether or not that makes sense at all.
This seems like one of the open issues.
What are the video of the stars? I
How
find the
about
approach
then,
studying more deeply with the Wolfrayet stars.
I think
much?
Really tricky.
I think they just
Less
lay out the
familiar.
theory very nicely and then
So just maybe I can draw.
I'm much less familiar with
Say you
the
have
assumptions
this
that are making the limitations of that model, and it's way
as
older.
a function of R over R star. They have some definition of what they consider to be the
I think this is implemented.
You can plot the velocity. So normally the typical model you would have is that you have
Yeah, bin star, bin star.
rows.
Yeah.
So it's Lenos CS.
You're out.
Yeah, there's.
So then essentially what's done is that you have this beta velocity loss.
But yeah,
Form for the
I don't remember how it in the paper described how.
Okay, this goes like this.
At
At
different.
some point within this atmosphere model with a given
But the
velocity
whole
load,
setup of the
they-
oscillating orbits is
they equal
Is there
2/3.
any limitations to it?
The problem is that actually driving might not operate like this. So
Unless
you
the
had some
Sokolov
simulations.
Spitz
So
model.
Luca Bonatowski in Keulen was working with this. Actually, you might have some initially driven
Already, is it
outflow that
already
then stalls and potentially slows down. And then you have this kind of behavior.
Wow.
So from observations, one issue is that actually this is something like it was just to implement. You're limited in terms of what you can feed into an atmosphere model.
And now I
prefer like draw this line in here. What? And more or less assume that there's a photosphere over here. And
what is
that
out
the
of those
hydrostatic surface lies further off. So whenever you have this optically thick outflows,
everything always like goes back
when
to
you're approaching it from limit, it's
and then
very
firing
tricky to
back
say
to
what's the
that.
surface. The surface
And the surface, right, exactly.
I know how to say it quickly.
It's even hard to identify that in the 3D model.
Yeah, halfway.
So you would throw it out 2/3 Was this for an optical peak outflow where we're actually talking about the more or less the photosphere that's in the wind already, or?
I was just thinking of
Like it reconstrains.
not I wasn't thinking about any optically thick
But I mean, you're thinking about a 3D simulation where you compute an optical depth, right?
Yeah, it's just an average optical depth.
It might be that.
Over the
Okay. But you could in principle be taking finding the photosphere lies in the outflow already.
I know
Like
that's
high.
So I can tell you you mentioned Will's models, your phase models, these models. So for Will Schultz has some models that are kind of local patches of blue supergiants, like 35 solar masses or so. There it looks like the tau equals 1 surface is kind of in what we might consider the star. In Jan Fay's Wolf-Rayet, or not Wolf-Rayet, LBV simulations, then the photosphere is generally out in the optically thick alpha. So if you just calculated tau along various lines of sight, which because it's very inhomogeneous, that may or may not be the way to do it. And it turns out that how you do your averaging, what you call your average can get you a factor of almost 2 difference.
So those equations don't call the photos. They don't like that root.
But that seems to be a lot more heavily into wind in that diagram.
Whether or not the delta function is like getting worse is another question.
Red supergiant. One thing that's been done in getting this quantity
NASA knows how to adjust
in other simulations, like
the
some
orbit Andrea gave us and the M dot, right? So the M dot's not gonna like
is to instead just take the luminosity leaving and then just take, L is 4 pi r squared sigma t to the 4th. You get your average temperature, you get your average luminosity, those lines kind of cross at one point, and you call that the photosphere.
So that was the problem.
So it's even just saying what you call the photosphere, especially in this really inhomogeneous surface, subsurface convection, is already kind of.
I'm trying to understand because in the low mass regime, it seems like literally all the posts.
And I think this is
mass transfers.
I think it's a fairly so.
We're talking about like mass.
I think above.
It's a general. I'll say the problem is general.
So what we think underwent is partially stable.
When the
so I was trying. We were just talking about it in the massive or intermediate mass regime.
And especially large scale. So if
stars, they're all of them
a simulation of the sun,
so
the granules are small.
Anything between
fluctuations are
and
not
hundreds
too
of days.
large. All of the turbulence is very
stable mass
subsonic.
transfer. They start.
The fluctuations go something like the Mach number squared and
the tides circularized them.
Turbulence, and so you don't have to.
The tides efficiently circularize them.
So like if we're doing the sun.
So they started very circular on tight binaries. These mass transferred towards the end of the main sequence, and
because the plot that Ali showed earlier, if you like squint your eyes a little bit, make yourself that at 100 days, the spread in
But for these, for the more massive stars, the really luminous ones,
4 days.
There's just so much more luminosity that the convection has to carry, and the only way to do that is by driving really.
The more massive stars at a shorter orbit.
Velocities relative to the sound speed.
or at least the population that I'm thinking about.
These inhomogeneities that really
but
shape the
question, right? So
surface.
do these systems
Even in stars where you
start
call it a
mass
radiative envelope, but there's
orbit and
a
then
subsurface convection zone where the velocities are large,
do they
even
start
though
mass
it's
transfer
MLT
to orbit?
stable,
Is
on either side of this convection zone.
all of these
That's a
other-
condition on the acceleration.
So we're gonna know
At the surface that.
yeah.
I don't even know.
Like the circumbinary disk and the but there are like I mean those mechanisms
Really far, and I can get like a little ejection of material, like a profile like this. And then I ask myself, okay, how do I communicate this? Like, is the surface here? Is this something that's just gonna leave? And then should I just place it inward? Well,
those are all mechanisms that would work even if we have the old school circular
One
method.
thing we're exploring with
It's like something
so they do a bit of
extra they put on top.
is to try to construct
like binary disks.
put the photosphere deeper in, but we have an atmosphere model that tells us what's happening outside. And says what mass is.
There's not so much from
The way it's hypostatic atmosphere.
Yeah.
So
So
it's
you're
like
essentially putting your Eddington gradient at just a deeper.
Yeah.
So
if there was
like one method is this kind of like grazing envelope thing from Nova current.
I guess it's more or less going back to the subject of the workshop, which is mass transfer. But it's because it's important. So our nature people are working on
that suppresses the tides. But it doesn't show the eccentricity, it just stops the eccentricity from and then I guess is that has these like natal things in white dwarf stars.
So let's go to very low metallicity, let's say solar orbits. Here, for example, where winds are not that important, what we see is that
you don't have all of these eccentric systems don't have white dwarf stars.
But as we keep going up in mass, we actually start seeing that this, the terms.
Yes, otherwise you
would.
Yeah.
Now to the point that we have like the dams happens here. In these modes.
But then again, there's also
inflated. We're predicting that all interactions for these very massive stars, these global solar masses, are going to be K-8. They're going to be main sequence. And that is potentially very wrong.
Okay, so it's just like a computational artifact. It's not actually what's happening.
So it could be that essentially from these 3D models, that essentially you're considering the motion of the material. That's why more or less my impression was that the media are actually more or less.
Spin mass loss.
You still have some inflation.
Spin mass loss, not mass transfer, is avoiding a lot of difficulty.
For this structure here,
Questionable.
let's say that I wanted to put as an output instead the effective temperature at 99% of stellar mass.
Yeah, I was thinking that type resonances with tiling.
For most of the evolution,
That's
yes,
crazy.
much more compact.
Okay.
But at some point, if the Eddington factor is really high, there's still a significant amount.
It's complicated, but I don't think it's like, oh,
rising here in the Hayashi line.
Yeah.
It's like the Hayashi line means you have a lot of convection.
Yeah.
A lot of masses in convection.
I see. So it's not okay.
So yeah, during this expansion, then that's right. But once you hit essentially hydrogen recombination and you develop this, this has a large chunk of convection.
So I think,
but also the thing is that this sets where we interact, but also we have no idea about the response of such a star to mass. So I don't know if we could put within these 3D calculations a binary there and make it even more complicated to see how mass transfer operates in this high. So I think this essentially has a large impact on.
Record, I mean, I get the same kind of inflation for us.
I can imagine like the moment at the conference that you mentioned that 20 years ago and everyone was like
1460. I get this impression.
It's extremely sensitive to mass loss rates.
Yeah.
And overshooting. So essentially, if you manage to strip the star or mix it very well, it behaves like a helium star, and those remain hot. So that's another thing. So one other issue in here is that we have observations, especially which is the gravitational. So we're bringing a whole bunch of stuff populated over here. It's not
all of these systems.
It's not entirely clear if it's just low number statistics or we're not sampling the right metallicities.
What's done in Hobson?
I'm more and more starting to get convinced that even at very low metallicity stars would evolve like this.
The binary to be certain.
They would be very well mixed. Not from rotational mixing.
Okay. Yeah, I was about to say that.
Magic non-rotational mixing processes.
Yeah.
It's basically, if my intuition is right here, this can really help. My whole idea is that if you don't have any nice, MLT almost like you'll get this data, I guess. You basically turn on something that reduces the opacity effectively of the envelope. So the star just doesn't.
X-ray binaries, I think, are.
So it will be more blue when it's really.
Also.
Okay. Well, if you believe my story time when I slept.
Go to the right.
Yeah.
So it's like. So somewhere in between, the reality is that you probably don't just inflate the envelope like in 1D. You get this turbulent convection that's probably more efficient
I don't think that they're all.
at transferring energy.
But
Envelope
eccentricities
still
of
doesn't
BE
always-
binaries?
Well, you said they're all circular.
One of the
I
things,
meant BE plus.
one of the things
yeah,
Mesa
exactly.
isn't really doing
Extra
self-consistently
binaries are tend to be.
is
BE.
including this pressure term from the turbulent energy densities, and especially schemes like MLT++ or the superadd reduction just are sort of pushing flux around, right? And so when you push flux into convection, maybe you call that a higher convective velocity. In nature, that's probably what's happening, but the larger the convective velocity relative to the sound speed, again, the more likely it is that your turbulence is
argue that
larger amplitude fluctuations, and then you have.
Are there any new observations that will help this problem?
This is a pressure term, stress energy tensor.
So Will has.
Yeah, Will has a.
It feels like
basically
discern between is different if it's pumping.
all of this in, and it's like, I guess it's almost there.
Yeah,
but the differences in the population.
Will, yeah, I mean. Will
You
now is doing
mentioned
data
that
reduction for Roman.
BE plus binaries
How has a more
maybe.
certain-
I've been
because
hearing
started
from
off
Matteo
circular
promises of
right,
having this
well,
calibration stance.
right?
Decade.
Yeah, I mean,
in that
Matteo's
comparison,
one of the
I
fixing
feel
problems as well, so.
What he did, because I feel like something could be
what their
done.
differences
Yeah.
are.
Atoms.
They're not all subject to the same mechanism.
Put it in the code.
Well,
but
we don't know what all
So at least we see what's wrong.
this
Will transition.
2017, so there's
Yeah.
more
He might.
systems, but it shows
Right.
different.
Some of Will's implementation is based on this sort of pseudo Mach number scheme that works in the machine that he tested it in the models that he has.
Very much.
Comparing, the more broad you want to extrapolate that, the more uncertainties that lies. It's kind of like winds and massive stars too, like, everyone you pick your observational data set.
So the difference.
I think we're getting a little results here.
Yeah.
As far as the ladybug topic. Should we maybe zoom out and think about addressing the big picture questions that were posed?
Argue this.
Magnetic fields, Pablo?
So what are the errors?
Like in my master's. So I have a big picture question. Binary evolution. I feel like often we use these sort of secular average timescale things for wind. Does it matter if the wind process is actually a stochastic bursty thing, binary?
A little bit more like the.
Of course, pulsations, right?
Dynamically.
Drive things on some shorter timescale.
So I would guess if it's really stochastic and not phase dependent,
I think it's kind of nice
the
that we don't see these.
average out in a sense. The angular momentum you're removing for a given period of time really average.
Is there any currently interacting
Yeah, it seems like that one is our easy case.
known and are eccentric?
Yes.
Hard case,
Okay.
because
Yeah.
you can't use a time average radius
Okay.
relative to a rush. Right?
Yeah, I guess that this plays a role in like very late evolution, so like Mira variables. So you have.
So we have 5 more minutes for the discussion.
Oh, the star is changing enormously in rate.
Oh, okay. I forgot about that.
What observation is Gaia gonna help?
Regular
Observations we need are in the long run.
the oscillations are usually at lower astrophysics.
Maybe tens, days, hundreds, thousands.
I tend to have the feeling
But
that
those sources
are more
are already in
very
there.
valuable information rather than something that.
There, not across all masses. I mean, I think the Gaia.
Do we have observations of sitting virtually overflowing stars?
We have actually quite massive
But I think
heartbeat.
DR5 will help.
Oh.
So there's
More fun.
Well, 5 would have everything.
Okay.
Fast.
What do you think about
Yeah, probably things will be.
what I've heard is that the heartbeat
We're
signal
gonna help with
is
the
extremely sensitive
slightly longer baseline.
structure of
The,
you might be
because of how they're doing. Yeah, there will be EPOC astrometry, but also it's how
the
they're
main issue with mass is that they have a lot of intrinsic variability. And it becomes quite hard. You just have like red
that
noise.
they didn't understand.
As far as I
So they just kind of cut parallax SNR versus orbital area. And what that did.
To identify modes that are not just stochastically driven by the
500 parsec, right? Effectively. Plus or minus, I know it's not exactly.
Yeah, so we're really gonna get the massive.
That's a little different than my intuition, I guess.
Low mass and.
My sense of our model for
have like a
what is the mass transfer rate as a function of this?
I think we could, there's probably a
Delta
lot,
slope,
like I think.
is pretty sensitive. We have sort of some prescriptions that exponentially ramp up, ramp down. And so if you like really start pushing stuff, 1% past.
While you were presenting, I had a WhatsApp chat.
Really get a different answer.
She's showing your plot, and then he told me, I don't believe any of the eccentricities; they're all bullshit. But then you actually said that you validate many of them with spectroscopy, right? So they're not.
Yeah, I mean, at least some of them, yeah. They're actually pretty good. Running the he is giving a talk to 7 what the problem is that we actually have to consider is that this rate per giant radius.
Okay, well.
That makes a tells us is well, at least some of them defined by tau equals 2/3. So which next
bothering me is
extended atmosphere that might exist.
Like if we can get absolute rate
and really influence the mass transfer. Because this, even though there is a little material in the atmosphere, it starts
like stability, for example, like which one should
get extended again, and then it will lead to more mass transfer, and this is a issue. So I think this is a
grabbed like a
big
bunch of
urgency
sequence binaries and a bunch of white dwarf sequence binaries, and they're not
What if you do like an identical
sequence binaries that there's two big bumps that are more in orbital periods that are due to
relax it?
There's a
like
dip.
that would because I feel like that could cause.
But then in the white dwarfs,
well, I'm curious because that could produce
where there's like Roche overflows.
I was just gonna say where how sensitive
way at the one end, and there's a huge wide bump as well from like non-interacting but wind mass loss. We can get the relative heights of
functional form of the density
bumps and the relative height.
By relaxing too, then you're
And
basically kicking it back into the mesa solver. So you want the structure, whereas like when you just develop that atmosphere model, you don't have any other hydrogen.
This is where these things are going. Now let's focus on this.
I'm agreeing with you.
Yeah, no, but in principle, the way these calculations work is that you're integrating through the overflow.
Like regimes, you also get clusters.
Extended layers, but they have very, very little.
You're making your slide with like
things are minutes left.
Just
we
giving
need to make a slide. Yeah, Evan and I have been.
Feel free to ask us whatever you need.
You do have systems.
Yeah, we can.
System eccentric or have very small eccentricities. So that's
Daily systems.
I do like this.
You're making your slide.
The red supergiants, the atmosphere is very fluffy.
Yeah.
So we can also get
that would be tough
a lot of overflow when we have like formally loaded overflow.
Unless it's like mass ratio.
But indeed, this atmospheric
all have to like start that.
Or that kind of environment. That's you don't deal with it.
But I mean,
what would be better? I don't know what Andrea's showing. Is showing us how to do better? You know?
That's for the high mass X-ray binaries. I plot the mass ratio and the eccentricity.
Essentially broadens enormously the range of which.
Yeah, indeed.
Up to period. So, good start is that we can pick up
a set of internal assumptions about the structure of the atmosphere, right? And then they map that onto like somehow that maps into the radius of the star, and then there's a sort of subgrid model essentially that may or may not be consistent with the actual stellar model. So yeah, it's hard to
For most cases, we're underflowing. We just use a Bernoulli equation to move from the surface to the Lagrangian point, and we assume isothermal atmosphere. More atmospheres are not isothermal. That's a very bad assumption.
It's not enough, right?
Yeah. It is true that a lot of these mass I just mean that some of these would make it sort of simplified assumptions that
Oh, yeah, you
approximate
see
conditions
that
at the surface of the
The
stars at
data
the
are
level
not
of
able to circularize them just yet.
How do we get around that?
Yeah, two group
Doing
one's
this
longer than
Well, I don't know if we can construct it as having a more general atmosphere model. I'm trying to do similar like these Bernoulli calculations. Eventually more.
Yeah, I have also one question for massive stars. That's easy to imagine, but for white dwarf binaries, what's the reason to cause the eccentricity?
One thing that I'm not sure I understand is that
What's
if you have a supergiant let's say that
Enough in the widest orbits.
is white giant and only hits the
In the wide orbits, yeah, and it depends on the. I think it depends a lot on the mass of the system of all things. It depends like on the phases, evolutionary phases. 2 minutes. But the higher mass you get, then the less likely you are the giant branches.
Essentially, whatever material you remove, you cannot just cut a star and the star will
No,
be cut.
sure.
So it essentially fills that.
Yeah, but okay, but this will
You have 2 minutes to write down your ideas. No, it's on the stack.
Oh, it is. Oh, the pressure scale height becomes comparable to the radius.
Yeah, I'll need an extra.
So you can have a meaningful fraction. In your Tolkien sequence, your pressure scale height is like 1,000. The giant, it's
yeah.
Assume we have a circle.
Or distinction like formally keep the roadshow would be 30% away from the roadshow. There's still a lot of
I did want to say something about this. In an earlier paper that we had with Gio Miru, we found that
because of
using correct initial distributions for things.
Yeah, but
basically it's the most important thing to find the distribution of eccentricities periods in clusters.
I mean, if you extend it
and that
more,
even if you enhance tides by a factor of 1,000, the change is not dominant over using the correct initial distribution.
I get it.
So everything above basically 10 days starts quite eccentric, and all the bullshit shows basically in that regime where they already start at something like
so we can take some kind of maybe
there's one extra thing to care about, actually using the correct initial these systems that we see might not have been led to be eccentric by some process. Maybe they're just more eccentric states.
I have a lot to say about mixing. Extra mixing session.
Well, we can start with
that basically resolves most of the eccentricity period.
we can give them like another minute. We just need to like summon people on the side.
And that's definitely the dominant effect.
Do you want me to put this up on
Saying,
my
how does that extrapolate?
Yeah.
Extrapolate on what's so simple of the type scale.
I may actually discover this, but
oh my god. Suddenly you realize
Yeah, so the thing I was wondering is that slightly more massive stars.
You might be able to get more of it. But that's the whole problem. Like there's so many factors.
We're right about this.
Oh, I saw you put them in scenario.
I didn't get all your text to fit on like the slide. Why is it like so small?
From there to Maybe everything. That's not what I want.
Because they're so, fast is so high. The material lower.
They are not.
And then for compact optics, you can definitely get.
Oh, sorry. Oh, yeah, right. Yes, so we can do a chair for that session. I agree. She did also just look over. So.
We'll just, I'll start it with the discussion.
Okay, have a seat. Let's get started.
Oh, yeah. Should I talk? You could talk. You can turn it on. At least not in this like the same. Okay. I don't mind.
Ding, ding,
Yeah. Like I just don't want to. Just try to summarize.
All right, welcome back. I hope you all had a good discussion. I know time was a bit short, but I'm glad that hopefully it seemed like a lot of people had some good thoughts on the topics. The slides, people are working on some of them still. Question 6, nobody voted for, but I think that means that we need to reach out to other communities and try and understand what they do. But that maybe is a problem for another time. Okay, so do we want to start with the first? Or we can start at the end.
You gotta read, but like in 5 seconds.
Okay, so let's start with the question number 5. Let's go to the end.
You just refresh now. It's
Oh, is it ready? Okay, we can have one person or a team. You're welcome to come up if you want, or you can stand there. I'll time 5 minutes to present your slide. So group 1.
Oh, yeah. Good? Yes.
okay. Go for it.
Are we going to put the slide up?
Yes.
Okay, yeah. So eccentricity during mass transfer, there's definitely a set of models out there. We found a whole list reaching back to the 70s or 60s even. They do apply approximations, but we have found some that include non-conservative mass transfer. I think the biggest issue is most of them seem to deal with the mass transfer rate calculation in the delta approximation, and that's something that's probably valid for very eccentric systems, but mildly eccentric systems not so much. In different slides and different resources, we have found that there's a whole bunch of eccentric systems, carbon-enhanced metal poor stars, the barium stars. They do all contain systems with eccentric systems. But a side note here, we shouldn't confuse processes that might make them eccentric with their initial eccentricities. There's definitely a whole population of longer period systems that are born eccentric, and there's papers on this. That might make it even more difficult to estimate what the effect of this eccentric mass transfer is. This is indeed something that is seen over a large range of masses with these systems, though. Observationally, Gaia will help with this. And there's some catalogs that definitely will help with this. Right, and indeed, I think if we combine our powers, then with population synthesis, we can do quite a bit because many of the other eccentricity inducing processes are in there, maybe tides, maybe kicks, these kind of things. And if we have a code that includes all of these non-conservative stuff and non-delta function mass transfer rates, then we could try it with different population synthesis codes. I think that would be a desirable thing. And maybe something we should start here and start making, right? Okay, that's what I want to say.
Thank you. Does anyone else
From the group want to add anything? Anyone from the audience want to add something?
Yeah, question.
I'm thinking of the last line, like shared between pop synth, like in an algorithm of this kind, does it need to be limited to rapid population synthesis?
No.
Not necessarily, right?
No, I didn't write rapid on purpose.
Okay.
Does that mean rapid?
No, yeah, it could just be a package that's you know, a repository on itself and includes a Fortran wrapper or whatever.
Yeah.
There's just the averaging that you need to do
Yeah.
the orbits.
I just had a quick question, which is like, it says like eccentric high mass X-ray binaries, but so do we think in some future we can, you know, distinguish eccentricity from mass transfer versus like cake and so on?
Oh, you mean so the eccentricity induced by the kick?
Yeah.
And the eccentricity induced by mass transfer? I guess that depends on how this mechanism induces the eccentricity further, right? There's definitely effects of pumping eccentricity in this. And I think we need to run models to see what the different distributions of this is. Well, there's some.
Yeah, and I suppose from the observational side, then it's going to be really helpful to have like good data sets where you have like specific types of systems and you observe like a substantial number of those, and where you start to have an idea where you would think that there would be a kick or not a kick or something like that. So I think that like getting, you know, multiple, like, and not like a small number multiple, but, you know, like tens or hundreds or more ideally of systems at like given evolutionary phases, and with given types of stars, where you can say like this population does this and this population does this, at least from the observational side. I think that would be really helpful. Yeah.
So just a comment on disentangling kicks from other eccentricity enhancing processes. I think one avenue I think would be useful is to, from observations, characterize the eccentricities of the progenitors of the systems of the high mass X-ray binaries. And essentially that's something that we need to use as a prior to any kind of inference on these compact object kicks. If we're using, for instance, B X-ray binaries to determine what are the kicks that they receive, we need to have information on the previous state on the eccentricity and period separation to have a clear identification. So at least that's a problem that potentially can be separated by understanding the population before.
That links a bit to the pre-main sequence that we were talking about, and understanding what are they born with, what's the distribution, and then what are the processes that either maintain eccentricity or change the eccentricity, pump it, circumbinary disks. But thank you very much to the first group. Second group, I forgot what these were. Oh yeah, those are the unicorns. Now we have the dragon. Dun, dun, dun.
Hi. So to constrain accretion efficiency, so first of all, there are many ways you can lose the mass from the winds of the donor. If the donor is very massive, from isotopic winds from the accretor, then if you have a disk around the accretor, say in case B mass transfer, then you can lose mass from disks as well. But fortunately, we have a lot of observations to compare models to, like, and they are kind of like dependent on mass a bit as well. So if if you look at like 10 to 30 solar masses, then you have like strip stars, which are not Wolf-Rayet. But if you go higher up in mass, then you have Wolf-Rayet features. So, but there are a lot of observations we can compare our models to. And then there are some upcoming surveys that can give us much more data to observational data to compare these models to. Yeah. To get constraints on mass transfer efficiency.
Okay, comments, questions for this group?
Yeah, I don't know. Maybe I wanted to add that. He was saying that we have lots of observations, and because there are lots of systems that can give us constraint on this, but actually the number of papers that dare to give constraint and say, well, we put this constraint for this kind of systems are very small. I think I can probably count them in 1 or 2 hands, and and this is maybe surprising, or maybe not. I mean, maybe if we really start digging into this, we find that even if we have so many observations, these are not really that constraining, and that's a problem for the models, because we can come up with lots of models, but if we cannot compare with something solid, that's complicated. So I don't know. I'm a bit confused about this, but.
Other comments on mass accretion efficiency?
It's not a comment, but a question. I'm just curious what you thought of when for the 5th item, magnetic field modeling. Are you thinking of donor or accretor, or what's that?
Maybe Brian wants to take that question.
Well, I was just noting that a lot of the all we're saying is that there's been a lot of advances in studies of accretion disks in recent years, which seem to show that the magnetic field that you feed the disk has a big influence on the properties of the outflows from the disk, even the evolution of the disk. So I was just saying that it would be good to connect these communities more. There has been some efforts along these lines already, but and maybe we should think about more boundary conditions for accretion to simulations that might be motivated by the mass transfer. So what do we expect for the magnetic field strengths that are feeding the disks from the stars, and maybe that should inform models for these accretion disks. That's what I meant.
Any other questions, comments? I mean, if you take the systems that we observed and you add up how much you think is accreted, and you add up do we see I mean, can you add up the material that's donated and the material that we see and the amount that we accreted? Do they equal what we expect? I think it's hard to tell from the observations if we always see the mass that's lost in non-conservative cases. Do we always see it? Yeah. How do we estimate this?
I wanted to echo what Ruggiero said. I think there's just it's really difficult. Let me start with that. And I'm not an observer, so I don't know the data well. But I feel like if there was as much work into trying to constrain the accretion efficiency as there went into trying to constrain alpha common envelope, I think we would be much further in life, maybe. I don't know. It's a difficult problem, but there's individual points where we could learn something. And I'm also guilty. I didn't do anything. So, but it would be nice if maybe we put our attention more there.
Like an alpha. Other material you want
I was going to say, what if it's exactly like alpha common envelope? Maybe a parameter we should not use at all.
Well, yeah, but there is a question: how much mass made it from star A to star B, which I think is a better parameter already than alpha common envelope.
And do we constrain that by looking at B and seeing how B changed, or do we constrain that by looking at the environment and seeing what was lost from the system? Like, how do we disentangle that? I think is both, and which systems, and you know, blue stragglers I think are good.
Yeah, I vote clusters.
Clusters,
You have the
because
best
they
mass constraints, and so that might be a path forward, doing this in more clusters. I mean, the problem is you have to have extremely well observed systems to get all the constraints that you need. So, you know, I think we don't have that many constraints because we need a lot of data. But if this is like a priority that we should have as observers to think about where we can get these constraints, I think I have some ideas about that. So it's good to know that you guys are interested.
Super. Thank you.
Yeah, I think if many of you are interested, then I also have a lot of algol systems that I want to look at. And they are like short periods, so we can get accurate constraints, like masses and stellar parameters. Yeah.
Yeah,
I'm
like,
very happy that many of you are interested.
Absolutely, because I feel like it seemed like for a long time, like theorists refused to believe that the objects we found were actually post mass transfer, because how could you get stable mass transfer? And now the question is moving to like, well, okay, it's not conservative, so how much mass actually gets transferred? So it's kind of a new question, and one that I do think we can start probing with observations to some degree.
Super. Thanks very much. Group 3, I forgot what that was. Those are the octopuses, the octopi, the octo.
Yeah.
Oh, yeah. There you go.
Yeah, so I mean, I think Pablo had given the answer to how do we get more conservative mass transfer. It is like coupling the disk to the star. The problem is that in 35 years we haven't tried, and so what we discussed is like what would be the challenges in doing this, and what would be the trends. We didn't really converge on what observations would help in deciding between option 1, which would be these, but we don't have option 2, which is what we are most of us using when doing binary calculations. And that's because of the issues that we've already been discussing of it's difficult to find these systems. So actually following up on what you just said before, I have a question of, do you have clusters with turn-off masses that have radiative envelopes with these blue stragglers?
Yes.
Great. I think those are very good data sets indeed to try to play with these things and distinguish these models, because the rotation rates of the stars and their masses will be different.
Yeah, so for the studies that I've been doing, it's like the more mass of a blue straggler you get, the harder it is to detect the white dwarf, which you need for like the best constraints on mass transfer efficiency. But if you want like a limit, like we could do limits just from what the mass of the blue straggler is and the turnoff mass is. So it's like we could certainly put some limits on this, if not do like very reliable amounts.
Oh, and in terms of what masses, well, applies to all the masses, and that's why these constraints are valid.
Yeah, so maybe adding to the cluster thing, I think Chen Guang is, she should have been here, but I don't know why. And, oh, okay. So she also works on clusters and binaries in clusters. And I think, remember from her talks, she was saying that with the accretion efficiency that we usually assume in MESA, so the rotational limited accretion, we definitely don't form enough B stars, for instance. And so that's I think already a constraint. So she was advocating for a higher efficiency of mass transfer or higher stability of the mass transfer. Sorry, I turned it off.
And when you spin up, do you get dynamos, magnetic fields? Like, should we expect these things to be magnetic? Does that then slow down the rotation? What's the physics there?
We did touch upon this a little bit. And if you look at systems like the ones that Julia is observing right after mass transfer, or if you look at runaways ejected from binaries that presumably have accreted mass before, they don't show any particular sign of strong magnetic fields. That doesn't rule out that during the mass transfer process that you have not observed, there might have been relevant magnetic fields, but it doesn't strongly suggest it either. Like Faye also brought up that in accreting neutron stars, sometimes you have the magnetic field that changes the accretion flow completely, takes mass from the disk, shots it onto the pole, and then rotation is not a problem anymore. But that probably requires pretty strong fields that we don't observe. So this, it seems weird, like it seems premature to ask the question, what about magnetic fields? Well, we have plenty of problems without the magnetic fields anyway, and no hint that they should be there, I think.
So in CVs, there are things called, oh, this thing is weird, intermediate polars and polars, where they do exactly this. So it's neutron stars also, but also polars, and you literally launch the material onto the poles through these magnetic fields. What systems is Julia modeling? Sorry,
not modeling, observing.
Observing,
just
sorry.
Right after Roche-Lobe overflow with the strip star impostor things. Yeah, and Tomer, yeah, many people.
Tomorrow.
So regarding white dwarfs accretors, I think this would not necessarily save us, because if you have a magnetic field and you have something like polars or something like that, you also have a much lower critical velocity, because now the critical velocity is not the surface of the star, but is the outer radius of the magnetosphere. And so you can go into a phase in which the star is not rotating very fast, but still the material cannot get inside because it's propelled away. So that may also make it worse in some cases.
Just want to like bring you guys another intention, like this one talking about like synchronization or like, yes, some role about tides in doing this, because we usually think about like tides always helping with energy dissipation, which means we tap the orbital energy and put it into the star, and then lead to, let's say, orbital circularization and like alignment of the spin and like orbit, like doing spin orbit alignment and also trying to synchronize the star. Actually, there's a new thing, it's called inverse tide. I think, yeah, Jim Fuller posted this paper on 2021. Some tides can doing the opposite. They're trying to like transfer energy from the star back to the orbit, and then leads to like pumping eccentricity first, and second, like causing spin orbit misalignment, and also trying to do like desynchronize the star spin. So like with the orbit, so like, yeah, so like that doing some opposite like direction. So that may helps like, I mean, in like our traditional way, think like if mass transfer happen, we always like synchronize the orbit, like the star spin synchronize with the orbit. So then, yeah, affect some like star rotation speed, but like there's can be some opposite way for understand this issue. And also, yeah, this also depends on what kind of like mode you excited due to tides, like if it's a prograde mode or that retrograde mode. So that's, yeah.
I guess that would help in explaining post-mass transfer eccentric things, not that much in making mass transfer more conservative, or at least it's not obvious to me how that.
Change the speed. I mean,
oh, you spin it down with the inverse tide and prevent reaching critical. Okay.
Okay, thank you very much. Let's move to the next group. Please.
Okay, then in terms of case BC or D mass transfer into main sequence companions, why do we not see them? And if we should, how could we see them? We first look at some systems that seem to match this class that we are aware of. There are two specific ones that we know, VV Cepheid and Epsilon Aurigae. The first is a red supergiant with the main sequence companion. The second is a yellow supergiant with a companion that's hidden by a thick disk. So these are both eclipsing systems with very long periods, which I think are of the order of 1,000 days for VV Cephi and 10,000 days for Epsilon Aurigae. So what happens, we imagine happens with this kind of system, if they are out there and potentially observable, is that because these are very long periods, they're not necessarily, you don't necessarily observe them for more than one cycle. You generally don't observe them for more than one cycle, and so they're not automatically connected to a binary necessarily. And this may be associated to a different kind of source. These are also eccentric systems, which heightens the chance that they're undergoing episodic mass transfer, and that connects to the long periods. But if they are being specifically targeted, then maybe more systems of this kind could be found, for example, in TESS, LSD, or Gaia light curves. We don't necessarily propose looking for them in the X-rays, which we generally associate with case B or further mass transfer in systems with compact objects. But we did think about looking for more subtle signs of this kind of mass transfer. For example, in peculiar supernovae, where for example, the supernova occurs while there is an active episode of mass transfer. There's going to be a talk by Andrea, sorry, Andrea tomorrow on this topic. And also potentially detecting signs of mass transfer to the companion in the abundances, for example, in barium stars. But we do need to know exactly what to look for. So besides looking for a very long period light curves, we would also need to know exactly what kind of emission we expect from these systems, which of course necessitates that we have a proper modeling for the kinds of UV and X-ray emissions that we would expect. So more models would be welcome, and looking for this kind of systems so we can get clear predictions of what we are looking for. And also for more particularly for distance systems in mass transfer from supergiants, we have observed with ALMA that these are often very dusty environments. So maybe we should be looking for infrared accesses. And then this potentially is something that we could try to do with JWST. I don't know if anyone wants to add anything. Okay.
I can say on the modeling side, I mean, really, what does the accretion look like onto a main sequence star from a giant? In 3D models, most people model the accretor as a point source, and it could be a white dwarf, it's just a mass. And I think that's part of the problem of like what should we be seeing for accretion onto these systems? So better models of that. Other questions, comments?
So just, you mentioned white dwarfs. I think this is actually quite an interesting regime because you have this these expectations that depending on mass transfer rate to a white dwarf, you expect very different phenomena. If it's too high, then you get that the white dwarf tries to become a red giant, and it can essentially fill its own Roach law. So I think what happens there is a bit of a mystery. And then you have this range of novae or stable accretion. So there's a lot of potential phenomenology in there that's interesting to study.
Other comments? I mean, in that case, that's why they invoked these, disk winds that can stabilize things. But I still think it's hard to see why don't we see the AGB stars and the red giants transferring mass onto a main sequence star, or do we? And it's only these really wide systems.
I think that you do. I think the hot subdwarf B stars have stable mass transfer from a giant branch star onto a main sequence star. Probably others as well.
Just to go off that though, like one of the problems we were kind of thinking about is, if there's X-rays, it's obvious that there's accretion going on. If there's a hot companion, like a very bright white dwarf or a subdwarf star, that's very obvious, we can find that. But are there subtler signatures that we could be detecting earlier on before the star is super stripped that would kind of clue us into earlier phases of the mass transfer. And I think we do see these clues, like with these eclipsing systems, they're really hard to detect because they're eclipsing every 10 years or 20 years. You get one dip, and only if someone sees this weird light curve and is like, I'm gonna dig more into this, are we getting results that's like, oh, we found an accreting main sequence companion around, a supergiant or a red giant. So I think there could be lots more of those hidden in the data that just like they don't have bright X-rays and they're hard to find in the light curves. But if we actually went digging for them in this like huge number of light curves we're having coming online, we might find like quite a few. So I think that might be an interesting route forward.
Maybe one signature of accretion on a main sequence star is just the fact that if you look at the 1D evolutionary tracks, Pablo showed some in his talk, like the star will be bloated, get redder and out of equilibrium, the accretor. So it might not look like a main sequence star, like observers might not put the spectral class that corresponds to main sequence, but they were probably lurking in the samples already, as Holly said.
Maybe the ELM white dwarfs as well, some of them. The who? ELM white dwarfs.
Extreme low mass white dwarfs. Any other last questions? Okay, then we have our final group. Thank you. Ladybugs.
I'll go. Okay, so as we were convening, Brian walked by quickly and said, oh, this one's really easy. The answer to which uncertainties in stellar astrophysics have the biggest impact on our models is all of them. And then he walked away and joined some other group or did something else. And I think our discussion did bear that out mostly, maybe with the exception of winds. We talked a little bit about winds, and it seems like, at least in some cases, slow winds, you can maybe take a secular average and maybe things aren't so bad there. But we talked about a lot of other, things that happen during binary mass transfer. Angular momentum transport in accretors is certainly something that we don't always pay that much attention to. Very rarely account for any sort of heating and dissipation in those differentially rotating layers that can matter. There was a lot of discussion of large fluctuations, particularly in massive stars on the high luminosity end, where I initially wrote in these slides that it's just impossible, but Jared deleted that and made it more diplomatic. So maybe there could be progress made there, but I think it's certainly a challenging problem if you want to go into the regime, probably, especially where you might want to do population synthesis for, LIGO binary black hole sources, for example. We talked about pulsations. I think there's probably a lot more to say there. We didn't even really touch on tides. And Mung's really nice talk yesterday has convinced me that tides and their interaction with pulsations matter a lot. And let's see, a few other things. Yeah, I guess on the higher mass end, red noise, intrinsic variability, and how that might interact with mass transfer from massive donors, also important. And yeah, then we had a really interesting discussion, I think maybe previewing a talk that is yet to come. I can't remember who it was going to be by, but what is the effect of the structure out beyond the photosphere? Because usually, for example, in MESA, we have some, Andre, great, okay. Yeah, but so for a prescription in MESA, for example, right, we have some physics calculation that is done more or less independent of the stellar structure model, right? And then attached onto, what's the effective radius of the stellar model. And if you, start trying to take into account the different details of different types of stellar structures, especially if you have a star that has an extended atmosphere, that could really introduce a lot of uncertainties. So I'm really looking forward to Andrea's talk about that. And then we didn't really talk about this, but Pablo said there's a whole large discussion to have about mixing and how that interacts with mass transfer. And EB also said the same thing about opacities. He's been doing a lot of work on opacities. So keep an eye out for that, I guess.
Thanks.
Just to comment, we do have extended atmosphere included in our mass loss. So, I mean, it is, and it is not just extended atmosphere, it also includes the binary effective potential. So it is taking into account the modified gravity.
I have a nasty thing. Like, these are individual ingredients that are uncertain and important, but in some of these physical situations that we try to model, shouldn't we also worry about treating these as independent things? Like, for example, okay, this goes into the mixing, but the example that I have in my head is that in MESA or in a stellar evolution code, you calculate the diffusion coefficient for every process, and then you just sum them, like every process doesn't know about each other. But then you reach critical rotation with a thermaline mixing coefficient that is higher than your meridional circulation coefficient, and they still don't talk to each other. And that's a bit weird. Should we worry even more than the individual ingredients in how we treat them together when they come at the same time with similar amplitudes?
I mean, convection and pulsation is another example.
So I don't know, do you want to go? Okay, so I guess it's quick. I guess we shouldn't over rely on calibration. So I guess calibration can be useful, but we need to use it to inform physical understanding. So we're not just moving knobs around, but actually understanding what's happening. If we understand the physical process, in principle, we can think about them together in a very different regime. Ideally.
Yeah. What I was going to say is kind of related to what Pablo said, and what Evan said. We didn't talk much about winds. I think we did in a few different ways. One is we talked about kind of the clumpiness of the winds and the time scales on which the winds are launched, and if they're bursty, and how that relates to the orbital period or some of these other things that that matter, whether or not we can kind of marginalize over that. Another thing related to that is also that, a lot of the sort of stellar wind prescriptions that we use, some of them are physics motivated, some of them are motivated by physics flavored, some of them are motivated by calibrations to observations, and a lot of times what we do is we'll kind of crank up the number up or down, or put in a constant wind or something like that, and because the wind and its evolution also then affects the orbital evolution, this can be a pretty important ingredient in this, and there's maybe an open question of how much, is it okay to turn that wind as a knob? Do we need new prescriptions? What should we be, what even should we be testing there? I also wanted to sort of echo something that's been said or read something that was said in the chat, because Simon isn't here right now. But he said specifically regarding pulsations that this, for red giants, there's an upper limit of about 1 kilometer per second in RV amplitude from pulsations, depends a bit on the surface gravity, and there's sort of a stochastic contribution at the kind of 0.5 kilometer per second level. Overall, and that's important in red giants. AGB stars are a little bit different. So if you're undergoing Roche lobe overflow on that giant branch, when you're pretty luminous and your convection is large scale, and et cetera, then pulsations should be included. On the main sequence, the RV amplitudes are much smaller, so it probably can be neglected on the main sequence. And then classical pulsators are typically a few kilometers per second. There's complex relationships between pulsations and tides, as Mang told us a lot about. Right, gravity modes can be tidally excited, sap orbital energy, leading to more rapid inward spiraling. Thus, gravity modes must be included for stars bigger than 1.2 solar masses on the main sequence. And also, pressure modes can become tidally trapped in one hemisphere, but there hasn't, but Simon at least hasn't, and neither have I, seen anything in the literature about them strongly affecting the orbital evolution. But that might just be that there's some work to do there.
I would just quickly also like to add one thing, is that especially with the case of red supergiants, not only does
the fact that they have an extended atmosphere complicate things. It's the fact that they also have pulsations at the same time. So it's not really something that you can just study individually. So you can make a model with just the extended atmosphere or just pulsation. You have to track both of them. And so then tracking down what's causing what, and also they're eccentric. So that makes, I think it's going to make the problem much more difficult to address. And just as a sort of anti-publicity against me, I'm not going to specifically talk about this in the talk tomorrow. Feel free to talk about me whenever. Just the talk will be more supernova-ish connected. So, but yeah, feel free to talk to me about this whenever you want.
Thank you. Thanks very much. Any last burning comment someone wants to make? Oh, yeah.
I wanted to react about stellar winds. I heard many people using the Dutch scheme, for example. It's way outdated. You want to check recent literature. Also, if you check recent literature, sorry, don't use Bézer's mass loss rate for red giant because it's not correct. It's been demonstrated. It was computation. I mean, there was a mistake in the analysis. Check this 2004. 2024? No, 23, it's last year. But the question I had.
You should add these things to the slides. So do add some of these things, like don't, that's what we were kind of going for, like don't do this, do this, what's best practice.
My question was, nobody mentioned 1D versus 3D in those uncertainties.
We talked a lot about it.
It's not on the slide. So as an observer, I was wondering how wrong we are, or correct we are.
I mean, it sounds like from what Matteo says, everything is dealt with in some kind of prescription on each individual thing. And that might be okay if we understand the physics of those things, but they have really complex interplay between them. And I don't see how you can do that in 1D. Yeah, I mean, I don't know if we understand the physics, number one, but can you do even the interplay between them? If you need the 3D model, I'm a 3D person, I'm biased. I like it.
Before you can answer the question, can you put them together in 1D? Maybe
Yes, and the way to understand the physics is?
Yeah, we don't understand the physics, right? Because otherwise we would not run the simulation.
I don't know how much more time do we have to go now? We went over. Zero. We're minus 15.
Minus 15. Sorry. Yeah, I do really like the discussion. So I'm biased, but maybe we should continue it over lunch. Thank you, everyone. Big applause for everybody.
And please do keep adding and putting the don'ts and the do's and the things on the slides. I think that's the idea, is to have something, and we'll keep this in Slack.
Yes, and so we'll have lunch until 2 p.m. again, so same as before. And if the next 3 speakers somewhere during lunch, that's Holly, Nikolai, and Reinhold, could just come up and quickly test your slides, and please write everything down. We'll have more discussions, so more time to continue.
Should we just chunk this all notes in that slide? Yeah.
Well, there's enough to say.
There's enough keywords. There's enough keywords.
We have to charge them over lunch.
It's a question.
I was going to test my laptop.
How to change the slides? Remote.
I think you get the USB and
Like a Mac.
you know the USB?
Yeah.
Is this an HDMI? Is this
Where's the second handheld mic? Oh, you.
Okay, because probably I would.
Yeah, there, so I'm coming there.
Just tell me. Things to discuss.
Here we still have like three.
Eigenlijk niet meer fysisch.
Which year it was? I'll double check this.
Ja, man.
Because fingerprint is the most recent one. It's very different. Let's use it.
Whether we have human stars.
Yeah, because it's very the original one. I was wondering.
Oh, those line numbers is the.
Or like the abstract.
What's happening?
I was
The
wondering.
line number doesn't show up at the.
Oh, that's like a parameter. Oh, at the abstract?
Yeah. I don't think they can. It'd be like major, but I can check like prescription, like this one. Weird. I think the line number environment or related to the AES template or something. Where do I go? Later is like very crowded. I know, I was doing the same thing. Oh, yeah.
Oh, apparently we went really long.
Yeah, what? The internet is, yeah, we're reset. Also, like
When we already.
Kyle. Mine looks like this. If you add this two lines, like on top, stage line number to this, and I can see maybe to the reference. Doesn't quite matter. And let me see if I. This option. Or do you mean like the figure description doesn't have like numbers as well?
Yeah, the captions.
Oh yeah, it doesn't matter. Mine doesn't have that.
Okay,
It should
but
be
on
fine.
the abstract.
Yeah, abstract it does. Should I send that to lines to you?
I have it. So no, I'm just gonna say that the model has no understanding of Chinese and how we know what rights are. We keep quiet. Here instead you put a 0.4.
Yeah, so I do not use the limit factor as a criteria.
Yeah.
Yeah, there are some words that say observation with 0.4 is a good cutoff.
Yeah, we
for the LMC.
Yeah, it's a point. I mean, we try to put it 0.5 or
And the limit factor is depends on what.
Yeah, my point. We set it at 0.5 just to be sure. But yeah, I mean, so my point is that okay, for how you start. Yeah. Yeah. So let's say if you're 10 minus 2 or 10 minus
something between
Oh, you would just comfortable if I said,
Submit to our
so let's say that.
Oh, I see. You know, some people wait for the cutoff time, it's like a little bit before cutoff time. So then during the next day, it will show up on the top. So I know.
I thought it was at the beginning of the stack.
I mean, if you pass the deadline, that one goes to the bottom the next day.
An optical deformation
You submit first, you're at the bottom of the stack.
Oh, good point. Yeah.
Oh gosh, I'm gonna find out. I mean, I didn't do it exactly at 2 p.m. I did it like 5 p.m.
Yeah, but no more 5
Do you know how the archive stack works?
In order to show like on the very top of archive, you should like submit right before the deadline, right after the deadline, or right after. Right after. Okay.
Because you want to be the first.
Oh, I see. They
You want to
do
be the
this.
first submission. Because it's like everything.
There's like a block, a time block where they're accepting submissions.
Yeah, like for the next day.
Yeah.
I
So
think
you
it's
want to be right at the beginning of
yeah, yeah. Like might be
try.
like 12 a.m. like.
Yeah. Okay.
I used to do that when I was in grad school. So now I'm like, don't have the stamina just to try to time anything.
Yeah.
So I remember that that's a thing. I'm pretty sure it's right after the deadline.
Okay. Well, I mean, since it's taken into account with the radius implicitly with metallicity.
For some reason, the lines are not showing up.
Doesn't show. Like even you have that 2 lines. After use package.
And the point is that my muscles
Right, both in
parameters or something.
Template mine is like AAS tag 6. Yeah, I didn't take off.
I'm doing decaf. I never used to understand the point. Now,
Right, yeah.
It's always something that you can't pick and build and that gets I can use all the other line driven parameters and then when I get to Helium stars it will okay, I have it. Then probably I will contact you again. It's part of my prescription. Okay, that's it.
Okay. Yeah. Like that. Just for information,
Let me know if you want to use because that's too big. So like maybe not allowed.
We have okay power, so.
I already
Not urgent.
using like the
When yours is like charged up.
I already using everything.
Right. Where you
And with the thing is about it.
Yes, same.
Very good. Yes, it's amazing.
Maybe I have an old line number.
Can I see your
Oh, wait.
the can I just do this? No, let me try the
Oh, it works.
Right. I just do document class 2 column, then a as text. Blah, blah.
I must have been using the wrong. Wait.
Change the template.
I needed to put document class line numbers.
Right. I don't have that line numbers in the document class line.
I was using this before, just that, and it was not. I don't know. It works. I'm not questioning.
It doesn't matter.
Oh. Really? Like there's an error, or like it's just not. Comments unnecessary. Do not use this as a check, as you check this paper. Are we exposed?
Or even decided we don't use that.
Yeah.
Not immediately. And I guess in the past I've put William's email, but maybe you can put Janet.
Yeah, I had to add line numbers to the document class as well, and then it worked. In case that you ever run into that, remember, it said it on the documentation for so I just it's not it's not
But there's interesting questions like how much mass is interacts with the I think it ultimately works on similar problems they were assigned by the result events. So you get the situation where we probably only survive in this environment. We're thinking about now is whether they can be self-sustained in the sense that that assumption that it is going to tend to accrete away. If you're stripping mass from the star, and that is adding to the accretion, then you have an extra source of mass being stripped. Think about this. Trying to understand the lifetimes of these sources. At some point, the expanding the star will start to expand. Actually, situation where stars are with a million solar mass primary and a dot, and a dot, and you see they're swarming around. So the interesting thing is that the gravitational wave driven mass transfer time scale is linear, it's expensive. So if we test it as find this what that means is around any there should be like around 10% of the population there should be like
But sometimes I speak to work.
What's thinking about these mass transferring and back and San Diego star has one. I think that's substantially significant. Although I think now
It depends where it is. Yeah.
it's also possible that mass transfer, we're talking about stability of mass transfer. My guess is that these transferring masses are mass transfer mass it is thicker at the Roche size. So it's impossible for me to see that this is going momentum back efficiently to this binary my guess is that it's highly non-conservative by definition. So that's why I don't know.
Is that surprising? What is the
Yeah, no, but I'm also still working out on a project. I'm like trying to understand wider users. I really like the, you know, like also I want to say with the paper, right? So there's all these like basic physics that we do. And then you vary that, you get such like value and outcomes, like how many goes and I think it's like, so basically doing that with like, yeah.
a lot of but a long but then why they not clear that
So, you know, like I saw like
Sure, yeah. Well, let me very quickly. Yeah, what's up?
I was just wondering about this.
Oh, wow, yeah, they like.
Just not to radiation. Because I try to get this
Isn't it? Like, I don't, they're just like, this is like.
It doesn't have to be. It doesn't have to be Eddington. I mean, it's super Eddington. I mean, there's two ways you could cool an efficient. One is just very high efficiency. So Eddington just comes in because if you calculate, if you equate photon diffusion time with radial advection time, you find that advection is shorter. So basically, photons are trapped and carried in the flow faster than they can radiate. And carried through so-called trap radius. So you have a radius which is that defines yeah.
How much is the incoming matter?
Yeah, this is right. This is just that definition. Yeah, if you were thinking about it,
Like they're so.
But yeah, so this is the radius. So basically, inside of this point, you can show that yeah, exactly. So that what I meant to say. So if you said the condition to get a thickness,
I don't know.
You know, if you were thinking about high accretion rates, then the condition to get a thickness would be that you would want the traveling radius to be larger than the radius of your star, or the radius, or you would want it to be larger than the circularization radius. You have the companions overflowing. Matter goes down, forms a disk of some our circularization. The location of this traveling radius relative to our circle will tell you what part of the disk would be in this thick state. And so, but it's hard to satisfy this because to make this condition, or this is the condition for the disk to be thick on any part of this. To satisfy this requires m dot over m dot Eddington. larger. Basically, yeah. I mean, basically, it has to be larger than our star over Rn. Or here Rn, sorry, Rn here would be if this is defined as you know, as you said, some this would be something like this. So this would be enormous for the sun. I mean, the ISO radius is 10 to the 5 centimeters. This is 10 to the 11 centimeters. So this would have to be 10 to the 6. So accreting onto a star would be in the trap regime for accreting onto a star. Would you have to be accreting on 10 to the 6? That's what's normally called. But you could be thick. You could be thick at very low accretion rates too. Because then the gas, then the disk is on dense enough for two bodies cooling.
Oh.
Yeah, I mean, well, I think for most, there's two reasons the disk can be thick and can cool. One is at high accretion rates, photons are trapped. The other is at very low accretion rates, which is like Sagittarius star. Like the black hole in the center of the galaxy. Low luminosity accretion flows, they're also like the accretion rate, because it's such a low accretion, it's very dilute plasma. So what causes, for an optically thin disk, what causes cooling is particles that are flying by each other like Bremsstrahlung radiation or something. I mean, everything always scales as density squared. So if you go to very low accretion rates, meaning very low densities in your disk, it can also be thick.
Are we sure that you put it right?
Geometrically thick, yes. Well, yeah. You're geometrically thick whenever you can cool on the inflow time. Which is sort of the definition of inflow. You have the cooling time, rate of cooling time, which is your radiation-dominated disk, basically photon fusion time. And then you have some inflow time, and you compare those two. And you're thick if you can cool. If you can cool, then you're thin, geometrically thin. Yeah, but I think in practice, in practice, what happens is if you try to feed the black hole, above this rate, and this is based on simulations. I mean, the ones by Stone don't include any radiation, so they don't include any cooling. But there are people who have done radiation hydro simulations, a super accretion. And generally what they find is sort of the same thing, that there are these powerful outflows of mass.
So I would just grab
so that the accretion rate that reaches the center is much smaller than the accretion on the outside. But they do find that it still radiates at roughly the Eddington. So if you try to feed it at 10 to the 5 times m dot Eddington, you don't get 10 to the 5 Eddington luminosities radiated. You get something of order of the Eddington. Because that's, I mean, if it were higher than that, I mean, the usual story is if it's higher than that, then the matter can't stay bound. I mean, by definition of being the Eddington. So that's kind of the limit. I don't know if there's an obvious, and it also doesn't come out isotopically. So you do these very thick disks. On large scales, they're becoming much thicker than so a lot of the radiation is actually. Yeah, it's not preventing accretion. It's not preventing accretion because radiation is beamed out. But generally speaking, this is like you could be feeding it at 10 to the 5 and not anything. This is maybe like 10 or 11 would be escaping luminosity. But with these types of the problem is with these types of radially efficient flows, they've usually been studied. Ultimately, you need somewhere to take the liberated gravitational energy. I mean, so for a black hole, it's easy. You could just, you can either drive it out in winds or jets. Yes, jets and winds, and that's the usual solution. But the other solution is you can just carry it into the horizon. But for a star, you can't do that. There's no horizon. So winds or jets probably carry away the excess if they're above Eddington. But as I said, it's very hard. It's very hard to get above Eddington for a star. Yeah, I don't. I think you're going to be in this regime. I mean, there's a nice review on water where they show. I mean, most of the parameter space in astrophysics, if you think about it broadly, most of it is actually in this thick regime. If you think about it in terms of Eddington, you only get a thin disk. This is for black holes, but you only get a thin disk for like a range. Let's say the lower bound might be 10 to the minus 2 or maybe 10 to the minus 3. And then the upper bound is to get a thin disk, which is a thin disk by definition, the gas is cooled, so it's able to flow efficiently onto the central object. But yeah, well, my guess is with the star. My guess is with the star that my guess is that the gas can't cool. It's just going to build up and form a hot. If you feed mass onto a star and it can't cool within the disk, it will just form an atmosphere above the hot material.
Yeah, because this seems
either be lost in the wind of the disk and never get down to the star. Or get down to the star, it will just form a hot atmosphere, and then it will cool. I mean, it has longer to cool. I mean, a disk has to cool on the inflow point if it wants to be efficient.
So
whereas a star, the mass can just build up and cool, but it has forever. I mean, so there would. I mean, how big it is would depend on how fast you're spinning it relative to how big this atmosphere.
And then this outflow gets so strong. For example, the wind
Yeah. I mean,
something like this usually is almost very balanced by
you get that. The most extreme case is where it goes as radius to T is less than equal to 1. So basically, if you have a star, this comes from Blanford and Beckman. It's called this is called the audio spiral. And it is a model for thick accretion disks. advection dominated inflow outflow solution. So basically the notion is that you feed the disk some rate M out at R out. And most of the mass is driven in the and so I go all the way down to Rn. The M dot that makes it in is basically Rn over R out P times M dot out. So if you take, so this is basically what you said. At any given radius, the mass that is flowing in is almost balancing what's flowing out. But there has to be a small net inflow. Yeah, of course. And so it's just that it's reduced by this factor, which can be, like if this is, let's say this is 100, and it can be 1%. But that's the peak has to be less than 1 because energetically some matter has to accrete because you have to get the energy to drive the wind from somewhere. So if it comes from gravitational potential energy, then P can't be larger than 1, but simulations find that this is actually closer to 0.3. Oh, okay. Where people have done like this simulations that Stone does. But my point is that M dot in will form some kind of atmosphere, and the thickness of this atmosphere will be set by the balance. The M dot in, the rate at which you're adding mass to the atmosphere versus in some cases. But this is only, the point is that this type of structure where this is only going to be true if it's advection dominated.
Also, aber ich muss im Spektral zum Beispiel nicht.
I mean, I don't think you can get in there. I don't think you can get in there for an optically thick disk. I think you'd have to have a very low accretion rate so that your disk was optically thin. But so the radiation is not trapped. It's just it's very low density. So it's optically thin so that the cooling, the relative cooling time for a thick disk, the relative cooling time is basically the vertical optical depth through the disk times the light process.
Das war unsere auch.
So for an optically thick disk, this is the thing that you can preserve with advection, right? And this is how you get this photon trapping. But for optically thin disk, the cooling time is given by the two-body rate. So it's basically proportional to 1 over the density squared times some cooling function. So if you have very low density, this can be very long, and if this is longer, the advection time is R over B, R over B, R. Yeah. So this would be basically. So if you have very low density, so that your cooling rate is longer than your advection time, but this is unfortunately like an implicit problem because your viscosity might depend on how thick your disk is. So but the fastest advection can be is for a thick disk. So for viscosity here would be like yeah. So viscosity here would be like CSH times alpha or something, or for alpha model, alpha CS squared. Yeah. So right. So if you have very low accretion rates, the disk is thick. So this is longer than this. And you're optically thin, then you could form a thick flow. Yeah, and then but the question would be if your accretion rate is really so low that rule, like this, the outflow rate might not be that high because it's it's a low inflow rate. So and also this condition could be satisfied at, I don't know, it could be
Yeah, it's
satisfied
different.
inside
Different
subradius or only outside subradius. In AGN, they tend to be on larger scales. Yes. And it's because of this, or sorry, this is the reason why.
So I have this sequence of this.
It becomes longer than this, which is why people think that this transition in X-ray line. That'll always give you this trapping. I mean, because you can show that they're the same thing. Because what enters the opacity is what enters tau is the opacity which enters Eddington. So if you do an imaging of the March, if you require, say that I require that tau R over C be larger than R squared over viscosity. Yeah, the viscosity, let's see, what is the viscosity? Yeah, but no, it's fine. This is fine with the viscosity. Oh no, never mind. It enters in the definition of m dot. So basically, this is the trapping condition. So m dot.
Hello.
M dot is basically.
I just named after the discussion like this someone said.
Mass of a disk.
I was like, if I didn't notice that, that would be
by viscous line. So the m dot in steady state is you can show that it's basically this. So if you replace this, so if you replace viscosity here with m dot over 3 pi sigma here, and you replace this with sigma kappa, then more or less this translates into the R larger than R trap condition. Okay, so it may be possible for main sequence stars. Now for black holes like S433, this trapping definitely happens.
Okay, so I think
I'll talk about that in my talk. You see these disk winds. I mean, you see these huge nebula that are inflated by the disk winds and jets, or whatever you want to call it, like they're egg-shaped. And it's just because the mass transfer rate in those systems is probably 100 Eddington or something. I don't know.
So if you get a black hole, then
it's very easy to do this with a black hole because
okay, let's try. And it's okay that this is
a black hole, then you totally get this trapping.
Yes, for sure, right? Yeah, for sure. And so that reduces how much the black hole grows from accretion. And it also means that most of the mass is, I'll show it in my talk.
Right?
I touched. Yeah, I would try. I mean, totally.
You can see the
plus 4.
That's
no. Yeah. These are not.
Same. Forget about it. The last 3 good ones.
You just say it. And it's like, that's fine.
Basic shocks interstellar.
My favorite.
Sorry, they're coming out this way.
Just imagination.
Yes. Yeah, this is like a jet, and this is
just knowing that you were proud of
the disk. This is the disk. Sorry, the disk winds are coming out like that. So the disk winds go out, and they sweep up the interstellar medium.
It's almost like the syndrome, Stockholm syndrome.
Yeah. So in
it
there,
shocks,
so I think,
and then also the jet goes out and
And we might need to, we should check. I'm not sure if our.
Okay, I have to work on my stock a little bit, but yeah, thanks a lot.
Or if you have BCM, you have BCM. Okay, great. There's two.
Not anywhere to.
Yeah, this is what, oh, there's something about Vegas. Huh? Like you need to do it
Yeah, probably.
It was on my side till 2 seconds ago.
Yeah, probably. Because I was like, I want to show a feed and I will go for it. He disappeared in that period. Have some meaning. Sure, yeah. I have to finish my talk at some point, but we can chat.
I just wanted to ask, like, I'm one of the
Someone to ask me how to pronounce his name.
Yeah. And then.
So I would say it's Nikolai, but ask him if you want the I assume there's someone signed up. I haven't paid attention, but so there's an hour and a half total. And so usually we have the person speak for 20 minutes. You will be so the expectation is that we would have discussion for maybe maybe 10 or 15 minutes further. So your talk, in total would maybe go for a little over a half hour, maybe 40 minutes in some cases. We ask a lot of questions. So the way it usually works is we have two speakers, one who is internal to CCA, one is external, usually. I don't know if we have someone signed up for the second talk. Matteo would know. But then at the end, we usually have an opportunity for if people from the group want to show like a slide or something.
If they are what they are.
So it starts at 1:10. It's not exactly an hour and a half, it's an hour and 20 minutes. So it starts at 1:10. It goes until 13:10. And it goes until 2:30. But it's a group of people. There are people that work on stars and people who work on plasmas and compact objects. It's across the street. So the CCA, so the CCA is in 162 Fifth Avenue. And so if you're registered as a visitor, which I believe you are for tomorrow, you should be able to just go there and show them your ID. Like these are the fifth floor.
So it's a really rapid.
So I have meetings in the morning, but I get lunch.
The orange, I guess the orange is one that maybe.
So you go to the 11th.
Yeah, maybe.
I guess.
So
it is because it's the second one.
Usually get lunch around 12:20 or something, 12:30. We go at 1:10, 1 o'clock.
Exactly. This is the culture, right?
Clearly.
CA is on 5th.
So your contribution was paramount.
All right, looking forward to it. And then on Friday, are you coming to school? Or do you know?
Oh, but I was just looking at one line in this mathematics. I know systematically. So
yeah, we're not giving a seminar, so I guess it doesn't really make sense for you to come unless there are people around. We have a spring break. It would be good for us to catch up. I do have a few meetings tomorrow.
Yeah, so funny.
Sorry, on Thursday. Yeah, sorry.
Gee, still rich we have
So everybody who's at the meeting will be invited to the group. So I think it's very informal on Thursday and Friday.
No, Zero Helium.
I don't think they have planned sessions.
That's 4471, but like.
I'm showing you here, but that's from my top. Oh, that is Friday for different stars. V9, V1, V8, because and this is the strip star.
That's fine.
You have spring scale it depending on the map.
Yeah, that's fine. That's fine. Yeah, I probably will have to be
looking at 2000.
So that's why I was saying if you and I wanted to chat more.
Need a strip star peaking in terms of excess, turning it for extinction.
Maybe
Friday.
Okay, yeah, we can
think also go outside.
Yeah, let's see. I may be able.
Yeah, it is very obvious. That would be like a huge excess.
Late on Thursday, but yeah, I mean, we can also catch up. It'd be good to just see how you're doing.
You have a hope to detect.
I agree.
What are you? So what are you working on? I don't know if there's a whole lot we have to discuss. I just wanted to see what the status was. So you're.
Okay, fair enough.
It might be right. So you're not working on magnetar flare, right?
Still not change your SCD slope.
Applies for a grant that our university.
No.
The decision should come.
Not the SCD slope, but
I mean,
reduce of the.
But the SCD that the Bethany had.
Or the temperature, right?
How far? Did you had an SCD?
2002 was the redder.
But like how red? Like it
Here,
looked very,
maybe.
okay, so really the whole thing, not just swing.
Yeah.
If I get the money, I thought that.
What I'm saying, radar genes, right? I mean, yes, there are slight differences here.
Yeah. We probably need to host you down here, honestly.
But in terms of slope,
just in the sense that,
this line up and this line up, you're going to get somewhat higher line.
No, it'd be great to have. It would be great to. Well, I don't know actually. If the grant money has to go through a university, then we would have to do it in Columbia. It's okay to go.
Sure, it helps, but I think
Yeah,
your point, if I'm correct, is whether it works out, right?
Yeah, the only thing I was going to say was.
We shouldn't see a B3.
Working with Tejas to post-process the calculation.
Our observation was a B1, then if this is true, we should not
Yeah,
see
but
the strip star.
the reason of the BE thought that you lose it because they're redundant.
Wait,
Because.
E is something else, right? I'm talking
Sorry,
B3.
B3, sorry.
B3. Just a normal, let's assume this is B.
Okay. I was thinking about having a student
my argument is that they use
look at this as well, and I don't want to take something that you want to work on yourself.
You can, let's assume I can scale it up.
I have a student who wants to learn how to use.
I multiply this, what, by a factor
I
of
was
5.
thinking, not about necessarily directly taking your trajectory.
So what would you get? You would get blue plus purple.
Sort of.
You would still get a very similar SCD.
Motivated by the flare scenario.
I don't know if she's sensitive to. She only has
some analytic estimates we did for.
They don't recognize the success. They're comparing it to. Well, they're plotting it on the color magnitude diagram.
He's been working on
this color magnitude diagram plot and everything that lies to the left of the.
He's been working. He's interested in
this plus this
Villanova and like
it lie to the left of the
process. He wants to also learn how to use, light curve code like Sedona to calculate light curves. So I wanted to ask if that's something where we could collaborate together, or he could work on it and from that angle, not necessarily directly using the simulation data, but doing like a parameterized model. Well, we could use the simulation.
No.
What's the entire slope?
I was thinking about it as more an exercise in trying to create more first principles like. I mean, if you haven't got very far, he hasn't even learned to use Skynet. Is that I don't. You were thinking more about trying to expand and do additional like calculus, multi-Ds.
I asked Bethany what's the earliest type start that they have in the
The earliest B.
earliest, but you said
Like you mean not like the earliest companion.
somehow, and then third, implement or perform nuclear arrangement. That was the grant proposal. So yeah, by the end of the month, I should know more whether.
Okay. This would be less. This would be less. Less about the nucleosynthetic yield and more about the output for radioactive heating. I don't know if you talked about this in the model, but like for example, one thing tells you what is the composition of nuclei you might create. And another piece of information is how
she only analyzed the ones that are going to. Yes. Yeah. So that doesn't help us. You
no, but I want to skip stuff. So we have
so we used in our paper estimates from my paper, but one could do it. So anyways, as we go forward, I will loop you in on what I could do. I don't want to do something that you're planning to do. Anyways, I think there will be plenty of projects. I don't think there will. I think there'll be plenty to do. Okay. No. Okay. Yeah. And you would be involved in. I'm just trying to come up with. I have a student who's very interested in. Making light curves of kilonova. Well, actually, what we've been looking at specifically are supernovae that are enriched in the ordinary supernova.
Yeah. I briefly read the paper, and so yeah, you were looking at how much our process ejecta do you need to no, one of the things
right. Yeah. So that same student reference. What is
if you go to the table.
Ani Patel, so he's not here. He has classes. No, but she also said he's a student of mine in Columbia. He's in his second year somewhere. Like
there is a table.
But he wants. I want both of them to learn how to use Skynet. It's going to be interesting. What parameters do you want to know? So I thought, this might be an interesting project to learn, but I don't think our interest is much reference model. She has a reference yields,
which I think is in the table.
More on the side of the light curves. And we used a very simplified. We used very simplified radiant transfer code, and we were thinking about which treats the opacities as continuum. First, in reality, the opacities are expansion opacities, meaning that the opacity actually cares about the expansion. This is just because the opacities are lines, the material is expanding, so as photons diffuse out, they see the lines. So you can't actually just use like an opacity. There's an opacity that actually depends on the history. So like a code like Sedona, for example, has its using that to calculate better light curves. Magnetar flares, also for his other project. But anyways, I'll loop you in as we go ahead. All right, good to chat with you, and yeah, we'll see you tomorrow.
I mean, it's not so drama. You get affected a little bit.
Anyway, maybe.
Also,
maybe
it
you
is
have
most
to. You have
likely
some-
cooler, right? So that is what it took here is 80,000.
I brought up your Facebook just to read through it, and then I saw. It
doesn't matter. 50,000 or 80,000 doesn't.
There may have been an unfortunate mishap there.
Scale, huh?
But the overall,
The vertical scale, it would, yeah, but it would not be brighter than a cooler strip star, unless you keep the same size. Yes, but it won't have the same size. Just to like everything normally changes. If you keep the same size and it's cooler, it's going to be brighter.
Let's take one.
No, that's not even obvious.
Do you have the colors on this? You don't have the one that the presentation can be redder.
I will also take one.
Yeah, I see as well. Yeah, color matching, because it could be on the edge, right? Which would help.
When should we do it now? Do you want to do it now? So
is it colors?
I would bet that the only thing you can do to constrain the parameters is to look at the strings of the one lines.
For this one?
Yes.
Yeah, that's
But
gonna
then
be.
the problem is that it's still generate, right? It's either hot or cool.
Yeah.
You have the SED by any chance?
The SED? No, I'm looking for your figure.
The color magnitude,
Yeah.
that's what I meant. I have the magnitude and color.
When did we
It's a
set
very
it?
blue one. That's why she finally accepted. I mean, the color is minus 0.4.
I don't know if this is the last one.
Never seen this.
You sent this to me.
Oh, no.
This is what I have. Or wait, let me. I can go to P1, right?
You say you give me B minus V or minus 1.4?
Yeah, that makes sense. Minus 0.4. So, yeah. Okay, we can look at this one. Doesn't matter. So.
Wait, we don't know how.
That really doesn't make sense.
One doesn't make sense.
That's when I get it so blue.
That it's so blue? Why not?
Because from the spectrum, it's a star which is fast rotating.
Yeah, but
well, but
there's a strict start.
If if the colors impact so much in the optical, it means that the structure is far going for the solution.
Well, I don't know if you should see. Well, I suspect that it's bright because gravitational tells me what it's. It's kind of the same argument.
I agree.
First of all, it could be like a B3 or something.
So it was not to astronomy.
No, it was like, well, we call it spectrum.
But if you go in and smear it out.
This thing lives for like 20
No,
minutes.
yeah, mine's the same way. Yeah, if it's moving, you
This
smear
little
it
fellow
out.
is like
moving, yes, but if you're so
yeah, but still, he did his time. He also survived 2 times falling into the ground. I don't know how.
You
Also takes it down.
I don't know. If it dies, and you would like frame it.
Anyway,
Survivor.
look that it's a rapid rotator. I mean, it says super rapid rotator.
I'm going to be essentially take the analysis.
No.
So I was don't like that much.
No, but so let's go back to our discussion.
Follow up? Yeah. And it still would be nice for sure. Which I completely must have.
Yeah, you have the first match with ISO data, right?
Yes, you can check that on paper 1. This buoyancy travel time that I talked about, like it's basically a value that you get when you integrate. Okay, no, let's start from. I tried studying before, so merger properties. So you can see it's a blue star still, but it has an intermediate convection zone, and it has convective component. And so we compare it at this point where I draw the green line with single star, like a genuine single star, which is just a Hertz from gap star. So it's fully radiative.
So at which point did it went through a merger process?
Right after main sequence. So when you turn on the Herschel gap and then we and that's kind of the thing. You get a long-lived blue supergiant, which crosses the Herschel gap. So let's say you have an observation of a Herschel gap star. You might want to know, can we distinguish it? And so what the thing to understand the difference is that you have structures are really different, and what you can draw is this is basically just a grid by Sarah frequency, but it determines the so-called mode cavity and gravity modes. So in charge of gravity modes, which are modes where the restoring force, the buoyancy, and then the pressure modes are just acoustic modes, basically. And these gravity modes can only propagate in regions where you don't have convection. If you have convection, you have a nice couple
She said,
and because of these things, you get so-called like mode.
She thought that what we see is the stripped star, and then there must be a companion compact in that chance, which I don't think.
Unless this is there any
Stories are very
no, very hard.
Yeah.
So you have a mode.
This is not hot. We know it, right?
Paradigm shift. And so the whole point is that you can see the star is fully radiative. There's no convection anywhere, and there is just one big mode. So the gravity mode can technically just propagate this whole region. But then for the merger mode, you have two mode cavities.
You like to zoom in a lot.
Yeah, but this is fine. Which is basically this one. So the modes cannot really propagate in between. Yeah.
First of all, so these two merger particles have different
Well, I'm curious the coordinate. This is a merger product, and this is a single star.
Yeah.
Like this is not a merger product. This is just a regular single star.
Sorry,
no, I wasn't.
Natural. It just slipped out kind of. Understood that this was single star. So
it might actually pop there because we're going to. It must.
But this
frequency is very high. Because of the merger, and this is something that this is one of the things that is the cross correlation method. In this case, it's two lines, but you get just gravitational energy. So the temperature, it's not method that you try this cross correlation. And look for this, and it's just at such a high temperature that it drives convective storm. That's a very natural proposal. And you ignite helium in the core, so here it's staying for a long time. It's going to probably before actually becoming
because what else can you explain? Yeah.
It's extremely oblique. And even optical color, you're right. This is weird. What is the intrinsic color of, I don't know, B0, B1?
But anyway, she has a magnitude, right? So
yeah, I mean, it can be non-spectrally.
Do the full CD, put the B star CD.
Yeah,
B star
and put
CD,
her data.
and put her data, and you already guessed
This ratio would be lower.
Yeah, purely by observation, even if you don't understand it.
I don't know exactly what the spectral type is.
Yeah, that is hard, right?
But it must be like B1 on B0, right? Otherwise, it's so the thing is, the total masses don't match up.
No, it's unacceptable because it's hot. Because the colors are.
Yeah, like it's somewhere here, right? Am I correct?
It cannot be B3.
No, but
so in the probably one of these.
But it's also you have a second star, right? So you brighten it up.
It's probably this actually. It's this. Minus 0.4 something.
Now is why is this?
That means, by the way, we have a few more.
This one, not there.
This one.
Maybe I should do a few more to look at that.
Yeah. You want to look at all of them to see if they're out the growth rates?
Yes.
How fast are we? Yeah, you can you?
Okay, here's another minus 0.4.
Okay, give me name.
Roll 563.
560. Why are they all in 5?
Well, because I was looking next to it. It's not
okay, nope. Not that, but look.
It's a binary.
Look. Not this one then?
What is this show or what? Can you show helium too?
Yeah, it's just gonna.
Yeah. Okay, so that's why this guy is hot. This pi zero, that's his frequency travel time. Could be still essentially, but okay. Integral over your root frequencies or over your mode. 81.
Also
So if
5.
your mode guarantee is super.
How many? Well, but
Yeah,
now.
looking at all the minus zero.
Yeah, but then you also get these.
Yes. Exactly. So the stars are probably up there.
What is wrong there with this?
Magnitude.
Just saying, the epoch 2 is really already sexual. Something
You can transform it depending on
Wait,
what kind of
can we have a look? This
by
one,
L, which is essentially
that one is
it's by basically by zero divided by.
But yeah, the same happened in.
It's the spacing period, some of the modes. So that these are the like the period spacing patterns.
Decide to re-enumerate.
So I'm not going to show them now because they're going to be like a lot. So if we have basically 4 exposures for sub-epoch, rotating chemically homogeneous
And the
star,
repeat that has been done later on everything. I
all
think
one
it's
works to be
clear for everyone that
we expect that if you take
we want to take 5, 6, whatever.
if you manage to observe all the modes in a star,
Chronological, independently of
the yeah. So if it's not the case experience spacing because compared to relations have been you just get a straight line.
I mean, I think
this
not.
is exactly pi zero value or pi L is going on here. So that's the way in which you can observe it. So if you can observe a star,
again, epoch 2 is massive.
The thing is, you will see that it's
also minus zero.
Dated. They're not chemically homogeneous.
Okay. So not all minus.
So that's why say the presentation is kind of the first indication that
what I'm saying is these guys have comparable colors. For example, what you just checked is also minus 0.4.
Purely based on how high they will be, what is like the average period spacing, because there is already a big difference.
That's just
this
for
is what
reference.
Rules paper, so when I mentioned fourth one, what they show quite nicely or that
45,
no?
No, really? Not sure.
Can you zoom in? This is what Earl showed. So they have this like mean period spacing value, and they compare it for classical neutron gap stars, so the genuine stars, and for the mergers. Now, but all these, there is some overlap, but they are in a way to now I'm actually not that different.
You want to see it, your star?
There is some.
Let's go to this one, which is the actual one.
Single star. You see that there is
basically it's a extremely rapid rotation. We see that not the space.
I hope I'm not like dumping too much information in one time.
It's a super rapid rotating star.
I mean,
we send out 500.
If you want to know more about it, Earl's paper is
motion is very hard to tell because you can zoom on one of the lines.
It's very hard to trying to do the same, obviously, because I want to be able to binary people can read the paper and understand what I'm trying to say. But Earl also does that in his paper, so it's kind of remarkable.
No indication of
I can explain some of these concepts that I just explained.
I'm gonna see where it falls on the CMD, but would you mind sending me a plot like this? Because like if our samples contaminated by fast rotators, that's good for me to know.
Well, it would be contaminated, right? I wouldn't call it contamination.
Well, I mean, if I'm saying this is the strip star sample, but there is not necessarily.
Wait, so this one is in your clear strip stars?
Clear? No.
Yeah. So it's
No,
not
it's
the
in
ones
the-
where I found the helium, but there are definitely bluebirds of the zero age main sequence and multiple filters. This one, I think it even 6 to 9 filters it was blue in.
Yeah.
And it wasn't even near the Zams too much. It was really bright. It was up towards like where the Wolf Ray star kind of regime of our CFD. So
and hoping
maybe that's the, yeah, you need to cut it off a little bit sooner, but
It's one of those.
Yeah, good,
Your
that's
CMD
the-
is nice.
Yeah,
This
that's
is just Gaia.
Gaia CT, and it's one of
They
these.
have a trash can full of weird
Relatively low mass at the edge of our sample, very blue
and so
object. Makes sense.
And it's a rapid rotator, so it should be round.
To its
Yeah.
B status.
because that's it, usually given the rotation.
Yeah.
You want to look at a star and
Yeah.
to say, well,
I can have one, I can send you this,
if I were not
right?
there,
I can send you the plotted whatever,
because also
yeah.
the data is
What do you
What we
wanna
were
have?
thinking now in terms of quick action items, maybe would you have interesting?
so it's hard
No.
to get
Okay.
Might be a good proposal for that. Definitely UV spectroscopy
like
of the source.
mission.
The Challenger deadline's this week. I was gonna say that, but maybe it doesn't make as much sense.
Say massive stars, like our massive
What this
stars.
week?
Yeah, because originally I was thinking why the SED is so nice that it doesn't look like there's a huge contribution. It's true. It's not a ship star because there's no helium. Two lines.
The one we're seeing here, we don't see any.
I'm gonna
Yeah.
show the plot that I showed them.
Space
Inva.
observation.
So,
But
like,
I think as far as I remember,
probably know this.
Yeah.
So like the strip star mountains here. And these
because
are
these are
SEDs for
periods on the order of days,
one.
and if you do ground-based observation,
Okay, and the slopes are
like,
different because I think
you're
it's
doing
more
it once a day,
Yeah,
so they might start to interfere and but the best would
What I mean is, would you be able to tell the difference between a hot star,
to
like an
be
O9,
lucky and have these kind of stars in
and a
your
strip star in terms of your SED?
Well, I think the
I
O-star
don't
would
know
not
what
be
the
fluid.
current status is, so I'm trying to be a bit like.
It won't be, it shouldn't be bluer to the main sequence. But,
But I'm,
it won't be bluer to the main sequence.
Yeah.
No.
And like this one.
But if you put a strip star next to an O star, you won't see any.
it doesn't matter whether it's a
You can get
merger.
some UV access, but yeah, it depends on the mass of the
Time.
ship star.
The end result is
Degenerate with the extinction.
Sure, yeah. But like, I don't think
This
the
is
extinction would be too much of a problem in this case because of how many different color combinations it's
I
doing.
can
I can
find the coed, or I can, but I guess
Yeah,
magnetic radial velocities doesn't make sense, or you take that.
None of our
piece, but-
targets, so that I looked at the.
Yeah, the moment I was just
majority are-
Yeah. They checked exactly this, so they made.
I can-
It really fits its group stars in our.
It's still really cool that it's like
Yeah.
like with a really high rapid rotating source. And I want to look at the spectrum about that a little bit more and also look at like where it is in our CMDs.
You want the spectral like fixed stars or?
So I think two options. I mean, I haven't read the paper, I don't even know what the
Really
options
just
are.
for like my own
Um,
reference,
but-
because like if I'm publishing like these are like the
It
robust
would be
strip stars.
great, for example,
Not a strip star.
I
It's like
mentioned
useful
this.
to make
Probably
a
strip
straight
star.
base on that.
It's probably.
Where they
think
It's
so?
not, I mean,
Whoa.
There's no way to. How do you get to the
So if you would have good data.
I don't know if it's post-match lunch.
Make this really hard.
You know.
to say, well, based on what's
No, I don't know.
Actually,
See, that was exactly my point.
Pre-main sequence mergers, doesn't Chen have all this fancy
I still think,
split main sequence?
yeah, but then
Yeah,
it
but it's
would
not the
not
same
look
mass.
like, also it wouldn't look like
Yeah.
the structure of a star, for example,
So
the
it
semi-convection,
Yeah,
overshooting, everything that can make it
It's
into.
larger.
Yeah.
How big is the radio?
One of the most
I mean, look,
Maximum.
that's what.
But the
measure.
Very hard to measure. No,
Maximum
but
50.
we can do better.
Just
No,
to
the
write
50
the board,
is
whether or not
50, but that's the same
they're
size.
both super giants.
But
But
using one line.
we
I
are
think
doing
better.
We can work.
for
Don't do it like right.
mega years in the blue, while your Hertzsprung gap star just
Can
moves
you
out.
output a
The
coordinate
Hertzsprung
spectrum?
gap, I mean,
You have a
it's
switch, yes,
potentially
no?
stars.
But do you have an
Um,
easy switch or do I?
And so this is one of the ways in which you
I just need to save them.
could explain.
Put them in the measure.
If you're doing it already, then you can send
Because
it.
then I fit
If you
this
have merger problems that stay there for a while, and
Wait, I cannot do
the
it.
problem is there's too many supergiants observed.
very
Go for it.
And
Real abundance of the
if
red.
they're all
Alex
merged,
was really angry.
the equation problems,
How I was using
that would explain why they stay there for so
Well,
long and are
exactly, you know
observed.
which way.
I was just scaling the line and the line,
Yeah.
it's just as the only thing you can do is still stay. You don't have.
Yeah, 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 yeah.
You're not gonna be on the paper.
Yeah.
Let me come up with high semi-convection efficiency, low overshooting. His models could reproduce the long-lived the supergiants.
I also find that in like my higher mass models, I don't have such high semi-convection as Apple. Yeah, 100%.
Yeah, 100.
Yeah, like 666.
Right, now I need to change the range.
I do find these.
I actually I'm gonna do for the fun all of this.
Like I do find them too, where like this is again my merger product in black, and this one, the funky looking one, this is also one that stays. It's not super long lived, so but it does ignite already. Yes, it's red supergiant. But still, astroseismically, these two objects are different.
So how did you make your version? I don't think it's from energy.
That's a great result. It's not a binary now. That's why. It's not a binary now. That's the problem. I don't store the velocities, and it only plots the ones that it shows as binary. Now that I did the full spectrum,
like we just want to get the basic structure.
Solve it by doing
our chemistry is not correct.
That would be ugly.
But yeah.
Yes, Gyre has resolved all this period gap thingy.
Gyre basically takes a model which can be anything as long as it's in the right format.
Let's say the binary is everything that exceeds 1
solve the position. So yeah, you can feed it anything and it will tell you how it goes. It's it's correct. So it's I didn't appreciate it until I started using it, like how powerful it is.
I mean, this is by cross-correlating the entire spectrum.
Without looking at any of them.
Without looking at any of them.
So the thing to pick would be, I would have this one because that's the network and then the main programs. So we go from
Sulfate pulsation.
Would be like
sulfates.
That would be eccentric. We should also.
Well,
yeah.
I don't know if it's
so. So Gyre does. I use
the co-observation. So I use one of the observations, cross-correlating all of them. That's the one we call it. And then use that co-observation to So first, exactly. I will eventually change it for you.
But that's exactly what I was saying.
Or that's a bit well. So the question is, I don't know.
I don't see any options.
For such a case with 9 epochs,
I'm perfect.
Again, I'm not plotting the results. I will store the ones and then I'll see the quality and stuff like that. But this could be real. So one thing I would like to do maybe is to plot these two. I say you don't trust me. You're about to make me.
You can plot it. That's something you expected. I knew you probably know it.
Find the right window. It's cool. It's cool because
it's quite a big show.
This is exactly what I do.
Myself.
What?
No. So wait.
I hope. I mean, the numbers correspond to the
Emacs, and now I'm all into Emacs, so that's good. But it's
you just start.
For a while but I cannot. It's the learning curve is like too hard.
It becomes a shock.
I'm like, just use Obsidian. It does the same.
Isn't that sick?
I
wanted to go forward with it, but I need
to just like
Wednesday,
and it takes a while before you have to set up.
We see why we get low. Okay, so ignore them.
I see the other two that are.
I mean, I guess you can use it
and maybe 3 and 4.
That's why
Oh, cool. Okay.
I have been curious.
Shouldn't I quickly go off to the last tables? Like going to left?
It does. That's where it crashes.
Okay. How far is it in time?
I switched the. It's fine. And your little fix that you pushed out helped it.
My random.
Yeah, because I made it like a lot very small zones because the way that it's working now is there's no flame, so it's just cell. How I use Excel to run the whole, it's like very
start rounding up. Thing I need to do with it.
so the opacity was an issue too. I switched to the page, like the planetary nebula.
Select all of the tasks that are still open.
I see how much I can push it. But that's not gonna, this is all gonna be wrong. Everything that, I only care about just getting the feed and then
Time of thinking about it.
and just there. And then that whole expansion.
Within there, and I just compile it again. And I just check it.
Yeah.
Wow.
There's a cabinet there.
I was waiting for that.
Reference.
Yes.
And also
Side calculus. My moles.
just write down tasks.
What is the density of what? I think everything will be fine in the core. You're just not gonna get.
Great, thanks.
Everything expansion.
Yeah, but think about it, it starts so compact. It's not gonna be like.
I don't know if I RSP too much.
At least, you know, expands.
I was putting this inside.
I think the peak should be. I don't know. I'm not gonna make any guess.
What's the overall size scale of the thing we're simulating? Or maybe not I know it is somewhere. Wouldn't it be like?
Oh, I might have plotted it. Did I? Or I switched it. I turned it off.
Oh yeah, log density. Okay, log density.
Radius 10 to the 6.
Yeah.
So you can see it just like.
Yes, Holly, yeah.
I only care about.
And it's the
Really cover this. This is because I had
I'm
many zones.
25.
So it's basically like the whole surface is like all in one zone. So it looks really.
But you're really. Anyway,
yeah, and I could do the whole thing. It was just a test. But what's the radius now? 10 to minus 3. It finishes the burn. So even at this point,
Where are you seeing?
Okay, great, thank you.
Yeah, so I kind of believe this.
Yeah, and then okay, the luminosity.
So would be.
You can't trust all this because I was switching. Shouldn't look like this. Can't trust it until you.
So I know what to do.
I'm using Bib, so someone like it.
I'm around.
Okay, hello everyone. Welcome to the afternoon session. So now we have Holly talking us about reproducing the orbital parameters of evolved post-interaction binaries. So the floor is to you.
Yeah, great. Can you hear me okay? Is the microphone working? Yeah. Okay, great. Yeah, so first of all, thanks very much to the organizers for the invitation. I'm really happy to be here. Yeah, so today I'm going to be talking about this reproducing the orbital parameters of evolved post-interaction binaries, and particularly focusing on these unexpectedly eccentric binaries which contain post or current giant stars. And this is kind of an overview talk, like it's not going to be absolutely everything in there. I think this is a pretty big topic, but I'm at least going to hopefully motivate you to see that there are a lot of these binaries which are eccentric, and we don't really know why. And there have been a bunch of people that have tried to explain it, and it's at best medium successful. So here is the plot. I think we've already seen this a couple of times now so far, but here we've got the orbital period
on the x-axis, and we've got the eccentricity on the y-axis. This blue contour is showing what the models roughly would predict, kind of like from population synthesis. And then all of these different points are a variety of observed systems, which are quite clearly quite different to the models. So you can see particularly that you have a lot of these systems from around about 100 days to about 10,000 days, where you have quite significant eccentricities, which is not expected. There are all sorts of different stars in here, but one thing that they do have in common is they contain either a giant or a post-giant star, and most of these systems have interacted. And so I guess for this talk, first of all, I'm going to break down the observations a little bit, and I'm going to go through various different evolutionary phases, and then I'm going to move on to the theory side and talk about some possible explanations. And the crux of the problem basically is when you have a giant branch star, here's just kind of like a Kippenhahn diagram of a one-ish solar mass giant star. It's one-ish solar mass, and this black line is showing where the convective envelope is. So this is up to the main sequence. Here we have the giant, and here's the dredge up happening on the giant branch. So you have these deep convective envelopes. This is for low and intermediate mass stars. The star becomes radially extended. You have this deep convective envelope. You expect tidal dissipation via the equilibrium tide to be very strong, and that's why we would expect these tide systems to be circularized. Okay, so now I'm going to go through some observations, and just to kind of break this down, what I'm going to talk about, starting with the on the left, the initially more massive, and on the right, the initially less massive. I'm going to not really talk about main sequence stars, but that's where everything comes from. Then I will mention some RGB main sequence stars, some AGB main sequence stars, some white dwarf main sequence stars, some white dwarf RGB stars. And I will also mention SDB plus main sequence. These SDBs are where the mass loss has been so extreme on the RGB that it stripped the star. And I will also mention this quite new class of objects where you have a SDB plus white dwarf but in a wide orbit. So just so you know where we're at. And then I also kept like a little diagram at the top here for all of the observations, just so we know where we're at. And I think this is kind of like a nice story as we go through. So we start at the base of the red giant branch. And these are some observations of oscillating red giant binaries in Kepler and TESS. These were observed by Paulbeck in 2022. There's a little HR diagram just showing them kind of clustering around the base of the RGB. There's going to be a lot of these PE diagrams, so I'm not going to necessarily explain all of the features of the x-axes every time. But what you can see is that at high eccentricity, high orbital periods, you have a big spread in eccentricities. As you decrease in orbital period, you decrease your at least number of high eccentricity systems. And at the base of the RGB, below around 10 days, you don't really see eccentric systems anymore. This is pretty expected. This is actually mostly coming from the pre-main sequence evolution. So on the pre-main sequence, you have a big radially extended convective star, and it kind of predicts, at least in the lowish mass range, that up to 10 days, your stars will be circularized. And then on the main sequence, you get a relatively minimal tidal evolution. So this is fine so far. This is good. Then I'm going to move up the red giant branch. I'm going to go to the tip of the RGB here. This is looking at some ellipsoidal variables in the LMC. These are observations from Ni et al. In 2017. Here, these are relatively close binary. The giant branch stars are very large, so these objects are, the giant star is really quite a substantial part of its window. So you see the ellipsoidal variations, and it's just a plot of the period and eccentricity that you see. So you can see that, sort of like above 100 days, seeing eccentric systems, but then in the range of a few hundred days, you see quite a few eccentric systems. So this is already quite a big change from the base of the RGB, where everything was circularized for around 10 days. So you can see that quite a bit of circularization has happened. SDB stars plus main sequence. The SDB star is formed by an RGB star being stripped the main sequence companion, and this is stable Rosetta flow. Here again, the PE. It's worth paying attention to the axes of the eccentricity here. So this is like 0 to 0.25, and 0 to 1. And you can see that the closer systems are more secularized. I would actually argue that these systems with eccentricity or orbital periods around 750 days and eccentricities around 0.5 is close to secularized. But you do have some non-zero eccentricities as you get a little higher up in the orbital period. Oh yeah, mentioning this. It's a relatively narrow parameter range for how these stars are stripped. So they think that the progenitors are from like 0.7 to 2 solar masses. The secondaries are a little bit lower, and the initial orbital period range is 100 to 800 days before the mass transfer. And the only way that these masses and periods are secure to the mass transfer models where they're about 5% automatically. Next, we've got the post-AGB stars. Similar pattern. These are observations from Glenn Uman in 2018. All of these were expected to be circularized. They found about 2/3 of the systems were eccentric. Got this questions yesterday, but here we've got white dwarf plus main sequence, and again you can see sort of this like 100 to 1,000 days. Again, have these eccentricities, and then you got to varying stars. You've got a white dwarf primary and RGB secondary. And again, you have a lot of systems from like 100 days to 10,000 days, which are in eccentric orbits. These are kind of interesting stars because I think that there's been some interaction with the AGB companion. So you see all of these chemical peculiarities and sort of like giant star that you're observing has been enriched with less process elements. And these are also predicted to be circularized. There's also another problem with these barium stars in that they're expected, like it's quite difficult to fit the former AGB star within this orbital period range. So it's also difficult to explain the orbital period distribution. You've got these hot subdwarf B plus white dwarf / neutron star systems. These are quite new. So there's one published so far, but I don't think it's alone. Can't say more than that, really. This has an orbital period of about 900 days. The companion is some kind of compact object. Initial mass is expected to be around 1.5 plus or minus 0.5 solar masses. I think this has gone down a little more. It's got an eccentricity of 0.36. And it has a separate B star. So if we put these pretty much all back in together, it doesn't have the large white dwarf plus neutron star. Yeah, so you can see that these are a lot of these are from different evolutionary phases. Different evolutionary phases, but they're all sitting in a roughly similar region of this period eccentricity diagram. So I'm going to go through some explanations. I have loads of time, so we'll be quick. There have been a few proposed explanations. One, I'm going to go through everything, and I'm not going to go through everything in major detail, but I will mention these ones. So grazing envelope interactions, white dwarf interclicks, tides, triples, maybe. What's okay? Triples and eccentric mass transfer. The idea of the grazing envelope on the AGB is that if you have an AGB star in an eccentric orbit, the companion gets close, have some kind of enhanced mass transfer during the eccentric passages, and this allows increasing distance this drives jets. And the main point to look at is this bottom plot here. If you compare, you've got one model of tides here, and then the tides in the grazing envelope. And if you just have the tides, then you expect the system to be relatively circular for 1,000 years. But if you include this grazing envelope interaction, then your eccentricity hardly decreases. So it goes from 0.34 to 0.325 in the same amount of time. This mechanism doesn't really increase the eccentricity, but it does slow down how quickly the eccentricity decreases. One problem with this is that you would expect a significant amount of circumbinary dust to be formed. And this isn't really seen in the observations, and it's certainly not seen in all of the observations of all of these objects.
With this, would you expect the larger spread in eccentricities at small periods or at high periods? So
I really am not sure. So I think what I got from this suggest is that they think that the eccentricity just isn't really going to change that much. So I guess, or at least during the AGB evolution, so it just stayed roughly the same as it was going into the AGB, and then it presumably is going to depend quite a bit on the initial eccentricity as well, which usually comes from a distribution. Yeah. But so this is just like a way to slow down the tides at least. These whiteboard meter bits. This is a Robert Flatiron 2010. I think this is the expected distribution bearing size. And yeah, the idea is you want to pick when you're making your white at this point. And this does kind of a nice job of like populating the region where we see these eccentric systems. This doesn't help the systems that don't contain white dwarfs yet. So there's quite a few pre-white dwarf systems. And it's also a bit difficult to do this with cluster observations of planetary nebulae, so the white dwarf would be kicked out of the cluster system. Tides, I've actually done some work on this. Not so a problem, but I will talk about some of the stuff that I've done. So I'm going to go back to these giant stars in the LMC. These are actually free mass transfer systems, which is why I thought they would be a really interesting example to look at, so that you can try and constrain the tides without having to do like messiness of mass transfer. Get a bunch of distributions here. These are just the observed data. In blue are the circularized systems that they observed, and in green are the eccentric systems. So you can see that the eccentric systems are in wider orbital periods. The eccentric systems are also mostly that's actually the crux of the problem with these observations. I'll mention that in a second. And one thing that I did notice is that they I think this probably just comes from the, yeah, I don't know, but they tend to have lower effective temperatures. So I thought that was interesting. They do. So the problem with these low mass systems and the eccentricity is that when giant stars that are less than about 2 solar masses and 1.25 solar masses are on the giant branch, they have these really deep convective envelopes. And they also spend a pretty long time on the giant branch. And so this is why these systems that you would most expect to be circularized, because they have this deep envelope and they're there for a long time. So it's really an issue that there are quite a few that are seen that are not eccentric. And from their paper, they suggest that the equilibrium tidal dissipation is overestimated by a factor of 100. I don't think that this is right. Don't totally agree with the way that they do their calculations. I'm going to go into a little bit more detail. Yeah, so I have an improved tidal dissipation treatment. This is just for the equilibrium tide, and this is dissipation that's just appropriate for population synthesis codes. So it's still a parameterization, but it just allows you to slightly more accurately look at calculate how strongly the tides are dissipated. So here, plotting is the difference between if you do like a detailed calculation of the tides compared to the kind of popular early description, and the difference in the tidal dissipation strength. This is a log scale, so you can see that, yeah, you can get some pretty huge discrepancies. You can get many orders of magnitude difference, and the tides, the detailed calculations are weaker. But this only really affects the systems where you have a really small convective envelope in terms of radius. Then in the general region, you do have slightly weaker tides, but it's not. It's more like a factor of view. It's not several orders of magnitude difference. Here I've just taken one system. Here I've got a one. I have a label for this. Oh, yeah. This is just showing the eccentricity evolution of a 1 solar mass to 0.8 solar mass star. Here I'm using the updated prescription. Here is the original prescription. And the main difference really is this kind of shoulders around the end of the main sequence. And you see that on the giant branch, you still have pretty efficient dissipation, and your eccentricity shrinks a lot. but at least with the early prescription, you get quite a lot of main sequence tidal dissipation, and that doesn't really happen. And that's just because, like, often in the models, you have this like tiny convective region on the surface of these low mass objects, and yeah, so that's the main difference. It doesn't make a huge difference on the RGB. Okay, so I have some lights. I just finished kind of soon, but okay, so based on these, I took a look at models. The primary is less than 2 solar masses, relatively flat distributions of eccentricity and period. We actually had more than 10 simple models, but I had a bunch of models. I was looking at the critical Roche filling factor, like when, so for the circular systems, okay, so for the observations, I just took the observed Roche filling factor and the eccentricity. And then I compared the original BSE to updated BSE with my tidal dissipation description. And the circular systems, I just looked at how Roche filling systems were when circularization happened. And I also did find some of these systems remained eccentric until the end, even mostly periods. And I do relatively successfully shift the Roche filling factor slightly. I do have a small extra tail of around like of 0.6 R over R, and the systems are still managing to be eccentric. So if we compare it to these observed samples, and particularly just look at the eccentric systems, you can see that there's quite a few with R over R around 0.6, and just a couple with R over around 0.8. So this is a couple of the BSE description, because basically everything with R over 0.6 we're expecting to be synchronized. Right. And then I just have a little table. So I've looked at all of these systems in detail. I did have some nice bits. I recently changed laptop. I don't have them to hand, but I do have this table of the 88 stars that they observed. There are about 20 which were in the slow mass forms that seemed convincingly like RGB stars. Some of them like maybe RGB stars, and that were eccentric. And I've gone through all of them. And I think, broadly speaking, most of these are actually not a huge problem. So quite a lot of the eccentricity column, a lot of these have, okay, even though it's non-zero eccentricity, it's an eccentricity of like 0.05, which is a really, really tiny eccentricity. So I'm not sure that, yeah, you could, or I wouldn't feel confident saying that these stars that we've observed all the way in the LMC are eccentric with this small eccentricity. Some of the others have relatively small RLs, and I've done quite a lot of looking at like these individual systems and looking at the RLs where you would expect them to be circularized. And so all of these RLs, I would really expect to be circularized. So there's really two systems which are being problem here. So I don't have like a definitive answer for how much weaker the tides are, but I think I don't find this compelling evidence that the tides are going to be a factor of 100 weaker based on basically two problematic systems. Okay. Okay. I don't really have time to go through this, but I have also applied this to various different evolutionary phases and looked at the critical circularization region. And the main gist is that with the updated tides description, to get to the white dwarf branch, everything's circularized to about 2,000 days, whereas the description is 3,000 days. So it's a bit of a difference, but it's not crazy. Just mention about triples. Okay. Jan from Soviet Union had quite a nice out in 2 years ago. And experience affirmation. This is where the binary, the outer tertiary overflows its flow, and transfers as to the inner binary. Quite an important experience as. This is kind of exciting. It solves some period distribution problems. They haven't looked explicitly at eccentricity distribution. So naturally fills this gap 1,000 days. Perhaps at least a triple step content as well. I don't think these models are great. But I do have some STB plus main sequence where they all apparently to be stable row flow overflow, and some of these systems with AU about 1 AU, well, the same matrix is about 1 AU are coming out with eccentric orbits. These seem to be from the Kozai mechanism. There are a bunch of reasons that I don't believe this. My list kind of here. Let's try and pick any moments. I'll ask about it. I'll come back to it. And then just a quick mention about this eccentric mass transfer prescription from Adrian Helium, which is, I think we decided A would be the state of the art. It's also not perfect. Yeah, I'm kind of out of time, but in summary, the type should be effective at secularizing these binaries with giant screens and largely the connected envelopes. Systems with higher eccentricities. And so far suggested explanations maybe we'll deal with one area or another area. One thing I'm wondering is if there is one solution to this for many, but I'm kind of wanting to pass it back to the experts so we can a little bit. So thanks very much. I think we'll have a couple of minutes for questions.
How about those STB binaries? What do you want to show?
So so I have these post row flow systems. Okay, so the problems with these models. Oh yeah, so a good thing. I know that it's definitely from the Kozai mechanism. So I know that this is a hideous little plot, but black solid line is showing a semi-major axis. This black dashed line is showing the radius of periastron. There's a bit of a sampling issue here, but you can see these clear oscillations. Also, if you look at like the relative inclination, that's flipping the eccentricity is changing. So that's all cool. So that's nice that they came out. The reasons I don't believe it is there's not very many of these. It's pretty difficult to convince the code that a giant star should go through stable mass transfer ever. So that's just an issue, and I don't really believe any of the results that come out because of this. One of the other problems is that the systems quite often go through some kind of like dynamical instability, and then you have to use an n-body integrator to look at them. And then I think it just gets like kind of chaotic and difficult to reproduce, very sensitive to numerics, difficult to characterize, hard to have any meaningful statistics. And the biggest problem is mass transfers assumed to be conservative, which then for an STD where you're removing like a huge amount of mass, you're just stripping it, you then end up with this huge primary. So I also didn't do for that reason, but I thought I'd mention it because it was like the first time I've ever done a calculation where I managed to get an eccentric post-mass transfer system. So I'm going to look into this more. This is really new. I actually found it by mistake when I was doing something different, and I was like, oh, well, I'll mention this now. So, yeah.
This is related to the slide you didn't get to show. I was curious to hear about what issues the state of the art for eccentric mass transfer.
Yeah, great. Cool. Yeah, so we kind of spoke about this, right? So this was an update from the Sierpinski model where you you have a very eccentric orbit and then your mass transfer is like a delta function. And that has a problem that then when you're at very low eccentricities, I think if you're at 0, it just crashes. If you give it a minutely small eccentricity, then this black dash line is showing the time evolution of the eccentricity, and it actually excites the eccentricity, but that's almost definitely not something that should be happening. And problems with this are one, that you assume that the mass transfer is conservative. Like I think that's a huge problem because most of the time we don't think the mass transfer is fully conservative. That's a huge problem about this. But as Sylvia mentioned as well, you typically need huge mass ratios for this to work properly, or quite big mass ratios.
Yeah, no, in the derivation, there's the assumption that the mass ratio is very large.
Yeah.
And I think a mass ratio, like my student looked into it, and the methodology is okay if your mass ratio is above 10.
Yeah.
then it's kind of hard to convince yourself that it's still stable mass transfer if you're above.
I know. Yeah. This is just from my place having school for a few years, just before he left academia, and I scheduled a lot of with him to extract as much knowledge as I could. So he's a pretty clever guy. And his paraphrase quote was, well, it's an improvement on previous work, but it's still very crude, and it's by far the second most egregious assumption that we're making.
Yeah.
Assumption, yeah. So you do something pretty awful when you have emerging neutron stars or black holes. So you basically kind of like artificially inflate them just for the last few orbits, because post-Newtonian corrections, it takes a huge amount of time to do the full spiral properly. So you just get them pretty close and then have like a parameter that the like orbits. So I think that's a problem as well.
Why is that a problem?
Why is it?
Yeah, because it's not going to change your delay time by much.
Yes. So the reason that it's a problem is that we were also using white holes for a while, and for making neutrons are a black hole factor of 10 or even 100 bigger doesn't make a huge difference. But making a white hole that much bigger does make a huge difference. And it took us quite a while to realize that that was happening, because at the start we were using the high mass systems, and then I did some stuff with the low mass systems. I was like, this is insane. This is wrong. So that's considered and it's a free parameter in there, and it's not really, it's just that like a numerical function rather than like anything physically motivated. And it then kind of working on this at the moment, but it makes it kind of difficult to do low mass and high mass systems consistently.
Yeah, thank you. Actually, Monica asked basically my question, but I have another question, because my main takeaway from your talk is we have some options, but none of them work.
Yeah.
So, and I understand from your tides that you say, okay, well, the tides could be a bit better, but not 100 times. That goes the same for the other ones.
Yeah.
So there's just something we're completely missing. Do you have any idea of what direction to go? Or
yes, I kind of want to go back to the mass transfer. Like I ended up with this because one of the mass transfer people were like, we don't know, we don't know if it's mass transfer. Hey, Holly, you do this other stuff. Maybe you can explain it all away with this other stuff. And it's been super unsuccessful, broadly. So I think it's time to look back at the mass transfer. And I kind of mentioned as well yesterday, generally, that I think that this assumption that systems are circularized at the time of mass transfer starting is just not really well justified, at least a lot of the time. And so we know a lot of systems are eccentric when they go in, and then that makes a huge difference in mass transfer. So I think it'd be great to look at a little bit more detail, like how mass is transferred in these eccentric orbits. Yeah. And one thing I do find a little disturbing about these observations, I'm going to go all the way back. Wait. I can just look back this way. Or not disturbing, but something that I'm contemplating is even though some are eccentric, they are also not all eccentric. So you do also see circularized systems. So it's not just that we're like a little bit over in the parameter space. I think there's something a little deeper than that.
We have time for one more question from
yeah. One clarification question, like for the improved tidal prescription, I'm just wondering if that's like structure dependent, like how the thickness of convection zone, and also associate with that. Let's say we force the star, like the forcing period is less than the, let's say, eddy turnover time in the stellar convection. Does that, okay.
Yeah, it's in the slow, it's a pretty nice regime because it's firmly in the equilibrium tide regime, and they're also slow orbits. I mean, the turnover time for a giant branch star is about 30 days, and these have orbital periods of like a few hundred years. Right. So it's pretty nice. And just for a little extra detail, I don't use the Hutt prescription or formalism. I use the Eggleton formalism, and in this, your lag time is proportional to your quadrupole moment of the star, and so your lag time isn't a free parameter. So that's just a nice thing about the formalism. Yeah.
Okay, I saw a lot of other raised hands, but I guess they're going to be for the coffee break, right? Okay, so let's thank our speaker.
This adapter if you need.
Okay, perfect. Yep.
Well, next we have Nikolai.
Yeah.
He's going to talk about which binary systems will help us constrain the mass transfer efficiency.
I hope at least some of them will help us. But yeah, so thanks for giving possibility to present some of our results. So mainly, yeah, I will speak about, I mean, some top priority candidates, which could potentially help us to constrain all the physics we were discussing here, or at least all of this, feature. And then also I will make a small introduction of what did we start to do with available method prescriptions and how efficient it is. So, okay, let's start from the beginning. Since ages, it has been assumed that one of the main features that could indicate the post-binary interaction is like high rotation of the former secondary star of a group. And kind of with this knowledge, we just look on the sample of like uniform sample of galactic O-type star and just took a fast rotating domain. By fast rotation, I mean with VC9 more than 200 km per second. Then we extensively started to really analyze each star in this domain. I mean, everything we could do, like proper motions, chemical compositions, by binary status, etc. We end up with this picture, but in order to like kind of understand it better, and also in order to kind of speak about these results with theoreticians, we need to divide VCNI by Vcrit. So then many people understand that half of this fast rotating tail actually rotating with like rotation in terms of Vcrit less than 0.5. Because then with this data, we can go to any of the simulations where people are kind of looking for OB plus neutron star or OB plus black hole, and like with this dashed area, which I show like it's all our targets should for example potentially have a neutron star as a companion. Okay. Then, if we will plot all of this target on the HR diagram, we can see, okay, they're kind of young, they're all close to the 0 H sequence. And also we can spot in terms of nitrogen abundances that around like 3 stars. It's working well. Okay. I mean, there are 3 stars which are really nitrogen enriched, and why they're so enriched. And in terms of helium, I don't see much enrichment, but if we will plot them like helium abundances as a function of VC9, that we see that, okay, yeah, we have some enrichment, small enrichment, plus if I will put here a kind of single track, like with, okay, with the initial rotation velocity of 300 or so 1 km per second, that even while star evolve, I can't reach this enrichment. But we should not forget about these things as error bars. They're kind of useful. But okay. Also, it's regarding fast rotating domain. But I would like to advertise tomorrow talk by Carlos, who will speak about slow rotating domain of all these type stars. So please also follow his talk tomorrow. Okay. Helium is okay, but if we will also put all the targets on the CMO diagram, there also a lot kind of interesting thing is going on. We see that like on the right top corner, kind of very, the kind of enriched star. And also I put here kind of, again, single track evolution with a very slow initial rotation. And if I will increase the rotation, like it was 50 per second, now it's 100, 200, 350 per second, here I stop. So, and it's up to the end of the main sequence. Okay, I can't reach that bunch of habits. And these three stars, particularly, it's this one that what I show on the HR diagram. So their nitrogen regions are really close to the zero H sequence. So it's kind of very interesting actually to look on them. You can, I mean, I provide their names. Go for it. It will be interesting. And also error bars, because it's extremely difficult to measure all abundances for such star. And for the same target, we have kind of different thing, different measurements, but it's okay. It's important in which corner it's locating. And also, if I will put here another survey with magnetic slow rotator, fast rotator, but also galactic object star, we see that they're all spread around. But we have like one fast rotator with extreme high enrichment of the abundances. And from one side, to explain all the spread, we can go to the binary moves. And here, for example, is a track of donor of the Fiuki in terms of CMO. And if you look on the accretor, so it goes to enrich and doing the mass transfer at the end. Here is the Fiuki, like this crosses actual observed value, but with a model, we can really reach this enrichment. So one of the explanation of all this, of that corner, it's of course binary interaction, but we really need to be careful that with a single star revolution, we can reach it as well, more or less. That's why we also need to see the actual age, like how rejuvenated it is. Okay, it was about more or less single stars, and now we know that algos are extremely powerful projects, which they're really, I mean, it is really nice to study them because for that reason, well-constrained orbit, we know actual masses, inclination, and moreover, if we're able to disentangle vicinai of both components, it's also perfect because here is one of the systems we are studying nowadays, and here on the bottom panel is showing the actual vicinai for both. It's not vicinai, I'm sorry. It's already, I'm already subtract inclination, so it's already equatorial rotation velocity and also synchronization velocity on the current time. And as we can see, they are not synchronized, and especially in terms of primary, it's completely something interesting going on. And like we have another system also not synchronized primary, and here we have a fast rotator. It's a primary which is also far away from the synchronization velocity. So that's a thing. I mean, this, for example, I just showing this free system, which is kind of, I mean, they are top priority targets, which potentially could help us to understand all this mass transfer and so yeah, just to show and yeah, just to sum up. Okay, then after all what we have different already available models which we can use, and then with a lot of which we already discussed caveats, which we really need to be careful, and especially the last point, which is completely go under the questions. So, and just an example, I already showed yesterday, like another system. So we already start to fit, I mean, at least the location of secondary or primary and secondary. And I mean, since I'm working mostly in terms of rotation, these red lines are actual observed equatorial velocity, and it's extremely, I mean, hard to then spot at which precise moment we are see the system. So that's why it's kind of, we need to put a lot of effort in it. How many minutes I have? 2, 5.
I'd say 4.
No, I think I even already can stop here because it's just a few other systems. But as you can see, even different prescription can show us different, how it's going in terms of mass transfer. And it's also main question, why different, with the same input, why is it different, have different tracks, which is kind of, we need to also sit and go one by one in lists, etc. So I will just leave the conclusions, which are kind of interesting. So thank you very much.
Hey, nice. Thanks for the nice talk. One quick technical thing just for us to discuss later. This do-j accretion that you have as a free parameter, it might be a bit more unphysical of a choice to have that on and off. We can chat about that later. The other question I have is more or less to show this V over V crit that doesn't go all the way to critical. How much do you trust your V equatorial? My naive expectation as a theorist is that you get gravity darkening and you have a higher contribution from higher latitudes. So you're observing the slower rotating parts of the star naively.
True, it can happen. But we are not on that real critical regimes. I mean, in terms of critical.
Oh, you don't know. That's the thing. If you're critical, what would you see really?
Yeah, I mean, that's a good point.
Okay.
Thanks. I have 2 questions. First is that your galactic O-type stars, they can enrich surface nitrogen via 3 channels, I guess: wind, mixing, and mass transfer. So is there any way that you can break this degeneracy? And the second question is that some of your stars are from the mean survey. So you have these magnetic properties so you I wonder if you've looked into the correlation with the magnetic properties and the stars, and yeah.
Okay, yeah, I will first answer to the second, because I mean, I plot and I especially, I mean, distinguish like magnetic, not magnetic, fast, slow rotating, but they are kind of really spread around all of it, so I think it's difficult really to understand, I mean, to distinguish it really where it comes from. And speaking about the first question, but first, yeah, I would like to for sure exclude the binary interaction and all this mass transfer enrichment because of the mass transfer in this sample. So that's why I think it's first we need to make a simple star model, and then just to play as much as we can, kind of, can we reach such enrichment or not? But so without any binary interaction first, that naive approach. But then in terms of internal mixing and what is the 0 point of the abundances, things too. I mean, it's a big uncertainty.
I guess if there are no further questions, we can say thank you for the nice talk, Nikolai. Okay, last talk of the afternoon, I guess. We have progenitors of stripped envelope supernovae as constraints on mass transfer stability by Reynolds.
Thank you. Yep. Hi, I'm Reinhold, new postdoc at KU Leuven. Is that working? That's not working. That works. So I'm going to first talk about some work, really the research goal that we're trying to do here, which is focused on trying to get better constraints on rapid binary pops and simulations. The motivation, the computational tools that we have to do this. I'm going to focus on the dynamical stability boundary, predictions for stripped envelope supernovae, and then the thermal stability boundary and some things that we can do going forward. So the goal really here is to identify observations that will allow us to properly constrain models of stable mass transfer. I don't think I need to motivate this to this particular audience. But to do this, we're going to be using both detailed evolution in the form of MESA and also rapid binary pops in the form of Compass. For those that don't know, I'm a developer on Compass, so that's why I focus on this one. As many of you know, MESA is a detailed 1D, so it's flexible and extendable. You have many different parameter options to test the physics, but it is slow compared to Compass, where the physics is simple, modular, very approximate, but runs very, very fast. And so if we can do this properly, we can make predictions on things like rare events like binary black holes and things like that. But it is intrinsically low detail. The connection to gravitational waves, which is for many people a key area of interest, is that we don't necessarily know what the formation channels are. Flor showed this yesterday, but I really like this plot because it emphasizes that we really don't know what the formation channels are for binary black holes, even though this is a phase of great interest to many people in the community. And this is something that we want to know much better. But to do this, we need a better understanding of mass transfer stability. How well do we know the stability boundary? Not very well. As many people in here know, the old method from Soberman 97 was to use these zetas corresponding to the envelope mass, the response of the envelope, the donor envelope to mass loss. And we had a great discussion yesterday about the limitations of this model. And then a few years ago, Hongwei Ge, who's in the room, looked at this more improved model for critical mass ratios that account for a lot of the more detailed physics that go on in this mass loss when you don't have immediate instability or stability in your envelope, but you have a delayed effect. However, as we noted yesterday, these models require fully conservative mass transfer, right? So there's no angular momentum loss, and that restriction we find is actually critical. When we compare the effect of the limitations of both models, this plot here shows the fraction of systems that experience only stable mass transfer, both immediately after the first mass transfer episode and also at the end of the evolution before any supernova has taken place. So after maybe several mass transfer episodes. And what we see is that the fluctuation in the amount of just the raw fraction of the systems that have experienced stable mass transfer is significant. Something like between 5 and 50%. Just from these uncertainties that are fairly standard in these approaches, right? So even after a single mass transfer episode, the stable mass transfer fraction fluctuates from 5 to 50% within standard modeling uncertainties. So these are things that we really need to know. These are standard modeling uncertainties, and we don't have a good grasp on them, but they have a significant influence even at this very early stage, not even worrying about all the way to binary black holes. How can we use supernova observations to help constrain this? So for those that aren't very familiar, supernova observations come in these different categories based on the spectral lines that you see. So you have your canonical type 2, which are hydrogen rich. You have 1Bs, which are hydrogen poor but helium rich, and 1Cs that are helium poor, corresponding to different amounts of envelope stripping. You also have these 2Bs, which have a little bit of hydrogen at early times, which they interpret as having a thin hydrogen envelope that gets blown away toward later times in the explosion. But you can interpret this as a continuum of envelope stripping in the progenitors. And so using a volume complete sample of supernova types out to 100 megaparsecs from Leo et al., what we can do is we can use these observational constraints on our population synthesis, assuming very simplified models of how mass transfer applies to the supernova that we see. So in this very, very simple approach, which is also very speculative, if you have a single star or an effectively single wide binary star up to about 18 solar masses, We think that these correspond to type 2 Ps. Anything above that, maybe you have some wind mass loss that doesn't leave your envelope. If you have stable mass transfer, you retain a little bit of hydrogen envelopes. These are your 2B progenitors. Common envelope should strip the entire envelope, leaving you with 1Bs or potentially 1Cs. And then if you have a merger, an evolved merger with a star that has a core, so at least one star with a core, you should have a blue supergiant progenitor giving you an 87A-like explosion, right? This is very hand-wavy. Doesn't include things like wind mass loss or things like this, but as a first order approximation, this is what we're going with. And what we find in this kind of complicated plot here is that if we try and compare the ratio of channels that have hydrogen-rich envelopes or a little bit of hydrogen envelope or none at the time of the supernova to the observations on the right here. So these columns here are unraveled pie charts. And as we vary the different kinds of binary physics that go into it, we're changing the column there. What we see, if we kind of squint our eyes, is that things are okay. On a pop synth level, this is kind of pretty good, right? We're not really off by even a factor of 2 in some cases. It's not great, it's not a perfect fit, but our models are doing all right. Yeah, like I said, at the pop synth level, this is fairly reasonable. The first takeaway from this is that none of these models are terrible. So our defaults are kind of close. The second one is that the evolved mergers actually really, really common. So that's this dark blue band here is something like 1/3 of all of our hydrogen-rich supernova explosions. That doesn't mean that 1/3 of type 2s are coming from blue supergiant progenitors, that they're all 87A-like. You might have some relaxation of your progenitor if you have a lot of time passing after the merger. But it means that a lot of the supernova models that we see that assume a single star progenitor might be very wrong, right? The structure of the donor, of the progenitor of the supernova might not be that of a single star. And this is not accounted for in supernova simulations. So the conclusion from this is that a pop synth roughly reproduces the observed supernova branch ratios. For now, you kind of have to squint. It's not great, but it works kind of well. But we're really not accounting for more detailed things like post-case B envelope mass loss and partially stripped star winds. So to do this better, we also want to have better observations, but we need to account for these very important physics factors. But then we wanted to explore even earlier than this, if we can get a constraint even earlier in the evolution to see if our rapid pop synth is even doing just the simplest stuff that we think we can do correctly at the level of case A mass transfer. So can rapid pop synth even capture simple case A? The answer is no. So when we look at COMPASS versus MESA on the main sequence, and we're plotting here, so now we're looking at the thermal stability boundary. And I cut out the slide that discusses thermal stability because I think everyone here is familiar with the zetas that come up a lot in stability discussions. But here we have this thermal stability zeta corresponding to whether your star will, well, in this sort of fiducial model, whether you think it will experience fast case A or slow case A on the nuclear timescale at the initial interaction. At the onset of the first interaction. What we see is that according to MESA, you become less stable with time. So as your star progresses along the main sequence, you're more likely to experience thermal timescale fast case A. Whereas in COMPASS and other pop synth codes, rapid pop synth, you increase your stability. So you become less likely to experience thermally unstable mass transfer. At the ZAMs, things are okay, but this is a big qualitative distinction that I don't think has been reported on previously. And this is in direct contradiction to results from MESA. Diving deeper, we were looking into where this problem comes from. And really what's happening is that the way that the rapid models are constructed, where you have, if you have mass loss, you shift to a new single stellar track. This is not able to capture the differences in core structure that you get from detailed codes like MESA. So here I've also included binary C just to emphasize another pop synth code. But really what you see, the important one here is on this M1 dot track. You can see that MESA experiences this fast spike here corresponding to your thermal timescale mass transfer. And neither of the two rapid codes are able to reproduce this. So in short, your rapid codes are not able to match this thermal timescale mass loss. In effect, they're kind of readily producing reverse algals, these systems that are a more massive donor slowly transferring mass into the accretor. They sort of produce too many of these in a sense. But the short takeaway is that these pop synth codes are systematically mistreating the stability boundary. This is something that it is potentially very a major problem. What can we do about it? Well, option A is to do what we love to do in pop synth, which is to find some prescription. You know, we run MESA, we figure out what the core mass is after doing these runs a few times and say, okay, cool. If you have these these two masses in this interaction. Here's the core mass. Just use that. Change your mass and then you're good. This is a bit hacky, but everything in PopSynth is hacky. Option B is to build up a whole new PopSynth model that takes into account a more refined core definition and structure. Things like having, maybe some kind of fit to a core that isn't just here's your core mass, here's your envelope mass, but maybe something that's more detailed than that, where you can fine tune it to more detailed stellar models and try and account for some of these more subtle differences. The second option is much more time consuming, probably a lot more work and hard to convince people to do, but also more accurate and maybe the best long-term option. But I'll let the community decide what to do. Either way, this this result only impacts case A mass transfer, so it shouldn't have such an impact on systems that start interacting on case B or case C. However, given that 50% of stars above 40 star masses interact in the main sequence, this likely has an impact on many of the major PopSynth predictions that we're seeing, especially because people don't really look at case A as a major uncertainty in PopSynth. So just to conclude, we find that we're not modeling the dynamical stability boundary in PopSynth. This has an immediate effect on the post-interaction systems that we're not accounting for. PopSynth roughly reproduces strip envelope supernova, but we need better observations and theory. And PopSynth systematically overpredicts the thermal stability of donors on the main sequence, meaning even case A systems are biased. We need to quantify the impact of this bias, and we also need to decide as a community what to do going forward. That's it.
No one else? Okay, awesome. Yeah, I knew KSA sucked, but now I know it even more, at least in population census. But I didn't really understand. I loved your plot of the zetas with the green for Compass and the red for Mesa, but I didn't really understand why it's so mirrored. And this might be too detailed, but
why it's so
exact mirror of each other.
Yeah, they're.
I mean, the age is going to be roughly the same. It's just subtle differences in the evolution of the code. I would say, I don't necessarily see a mirror to it. It's more that the PopSynth ones are becoming more stable, so they're going to move up, and the diesel ones are moving down.
Yeah.
Okay. Yeah. I don't know. I want to understand why it happens this way. It looks this way. If that's a long answer, we can talk.
Why is it steeply opposite as you go up in mass? I think that's the statement. Like, why does the steepness continue as you increase in mass? It's like
for PopSynth.
For both, very extreme. They more steeply disagree as you increase it. It's more like when you increase in time, right? The closer you get to the terminal age main sequence, the more extreme it gets.
I don't know if I can give you a good short answer on that one.
Okay, let's talk.
If you cut the x-axis in half and sorry. I'm just saying maybe as you were saying, maybe also it's a matter of plotting because of course they live less. So if you actually cut the x-axis, you will see not the same stiffness, but it's also a matter of the time scales for the evolution. Just saying.
Yeah.
Hey, I fully agree that one should never do case A mass transfer with a fast code. So my question may not make sense, but in PopSyn you have these tracks that are for stars that are, well, not in all PopSyn codes, but in the two codes that you're showing here, it's based on the early tracks. So you always have stars that are in thermal equilibrium. And so I think a lot of magic comes from when you strip the star, what is the next track that you're going to and where on that track do you get? So this result, can it maybe be related to how you decide which track and where on that track you're going to?
It is exactly that result. So by those choices, that's how you get these curves. That's how they're plotted. It is a good question if we can do better by choosing differently, whether choosing a different mass track. So you're supposed to lose a certain amount of mass. Maybe you lose more or less, maybe we change that. Or if you choose a different evolutionary phase that you get to. But these decisions are
Yeah, so how do you model rejuvenation? Like in physical terms, you're trying to do rejuvenation by adjusting the tracks.
You match the main sequence fractional age.
Yeah.
So if you are 50% along the main sequence, you lose the amount of mass that you're told to lose, you drop down to that new mass, and you're 50% along the new main sequence. So you effectively re-age the star.
I'm kind of assuming that Compass and Binary C do that in the same ways that Hurley recommended.
Compass does some funniness, which you can actually see here. The fact that they don't quite match. Binary C, this is what we were talking about yesterday, pumps up an artificial wind. So that's, and it's very, well, it's sort of weakly sensitive to the overflow rate. So what you see is that Binary C can be quite a bit over its own Roche lobe for a long period of time before that wind really makes a difference. But then it will still shift down to a new track and re-age in that process. Compass does this without doing the wind. It will say, what is the Roche lobe size I need to fit into? And then just pop down to that new size. So it's sort of like having a very large wind artificially in one time step. But they're both, I mean, they're both doing it wrong.
I mean, this was my question. So.
Okay. If at some point you said there's two options to go with, just as an announcement, we are working on option B of creating a way more detailed and well, taking way more things into account in interpolation tables in Binary C, which will be released soon.
Fantastic. We should talk.
It's also in Matisse.
Yeah, Matisse does something similar.
Yeah.
Okay.
Matisse will consult is
Something similar. But I didn't go for that because I will talk about something else. So as long as it's consent, let them talk. Go.
And just to, as a follow-up to what we were saying before, I mean, not to spoil my talk, but actually the problem with dropping down to an evolutionary track when you're losing mass during the main sequence is also like a great problem because, I mean, after you are losing mass bit from mass transfer or like LBV winds or whatever you want during main sequence, I mean, population synthesis prescribed a completely wrong structural evolution because it's just prescribing like lower mass supergiants, while instead you should go to the other side of the HR diagram and become like for Wolf-Rayet stars. So yeah, I mean, just saying post case A evolution in the population synthesis kind of like wrong.
I agree.
Can I ruin the pop synth party and just switch a bit something else? So when talking about supernovae, it's always a bit of a madness. One thing that I can suggest is that, for example, you talk about the mergers that will lead to peculiar type 2p supernovae, basically. I think you can already split them in basically two classes, those that were undergoing case A mass transfer and merged, because in that case, they become a main sequence.
That actually contributes to our effectively single mass fraction. So this includes case A mergers. We don't even distinguish those because
then they would just be type 2p supernova at the end. They would just evolve as main sequence. Yeah, okay.
More so than the case BC mergers, yeah.
Yeah, not as bad as in the case of BC mergers, because in that case, they may become blue supergiants. Yeah. But then it's also very complicated. Like, do you also sample with different initial masses? Like, how high up do you go with the initial masses when you populate these supernova types?
Pop synth is not really well defined above 50 solar masses. Some people will push it above that, but it's not really supposed to be. Yeah.
Because then from 30-ish to 50, you should expect full stripping. So in that case, it would all be one.
So this is actually an interesting one. We don't know what this lower mass bound is for where you get a fully stripped supernova progenitor. That one we focused, this one you can't really see here. M-min Wolf-Rayet is this minimum mass where you form a Wolf-Rayet, so you lose the envelope before you have collapse. This is very closely related to the missing red supergiant problem, where you see red supergiants up to 25 solar masses, but not as type 2p progenitors. You only see up to 18 solar masses. Some people have suggested that means that you lose that envelope mass between 18 and 25. But it's quite an open problem. So we looked at what that changes about the rates if you allow these single stars up to 25 to retain their hydrogen envelopes. It didn't solve the problem, at least at this level of coarseness.
So then at the very end, just very quickly, you cannot predict the other types of supernovae. So the very fancy ones, so like the superluminous ones, or
We didn't look at superluminous. We looked a bit at distinguishing 1Bs and 1Cs, but even
That's enough.
observationally, yeah, even that level is almost you're kind of pushing the observational distinction too far. Then they don't even have that quite figured out yet.
That's fine. Thank you.
I do want to make one comment on the red supergiant problem, which is that there are kind of two red supergiant problems that get discussed. One is that there don't seem to be red supergiants anywhere above a certain luminosity. And the other is that when you look at the population of type 2 plateau or type 2 supernovae, hydrogen-rich supernovae, that have then an observed progenitor, and you compare that to the population of red supergiants in the field, there might be sort of an upper luminosity cutoff or an upper luminosity, sort of an upper mass limit on the ones that we then see explode, which I don't think winds, unless they're winds that only happen in the last decade, can explain that. So the fact that you don't reproduce that solution to the problem with population synthesis is not surprising at all.
I agree. It could be eruptions, but yeah, we can't model at that level of detail.
Right.
Let's end this here because we're already 5 minutes over time. But thank you, Reynold, amazing talk, and thanks to all the speakers.
Sure. I claimed a mic. So.
Any announcements?
To be back in 20 minutes.
Anything the discussion they don't have
We'll have to figure it out now what we say, so we don't know what to say yet.
We need to let's get together with the troops and then okay, a few things.
I charged them over lunch.
Oh, you did?
They were in the thing, right?
You did because of this thing. Say, oh, I didn't. No, I didn't.
Oh, yeah,
Okay, great.
yeah.
Okay, well,
I charged
them. Great, good thinking.
Okay, guys. We have 3 things. So he's not just right. And he said he's going to give a talk just for like decision because the mentalistic environment. How much storage
Any risk of overflow?
And then say, let's work on those, and we can use the slides from the beginning again. Yeah, I mean, this is also my board, isn't it? Yeah, maybe we can just write on those. And write as like Brian. Yeah. Okay, so then we have to get in contact with Julie and Brian and settle this.
Yeah.
Okay, then so we should probably do that.
Created like statements.
No, that's exactly. I saw it. Actually,
Stability or like it's great.
We'll just keep it. Brian is here. We can also yeah, I will just and then it's good.
I have no doubts about these.
Yeah, I would just mention Jimmy because this is not the discussion.
And it's short about yeah, why not? It's also fine. But let's work out these now.
You're playing but it's great.
I will not. I will not let you take blame for my. I mean, okay, very good. Your hands are clean of anything that I say.
Now that you're here, I already talked to you briefly about this, but the original idea was to have this kind of equal discussion, which is this thing after here. So it's kind of the same as like Emily already did, because we wanted to, we already thought about that, but I think there's some stuff to discuss. So
I guess I think we have some questions at the end, so I was thinking we would throw those up, but then also take additional questions from the audience.
I think that's great, and then
yeah. So the sole really is like, how do you want to distribute organized? Yeah, there is. Yes.
Yeah, I can.
Yeah, because I can't write. So
I or somebody.
Yeah.
I can take notes.
That would be helpful.
Yeah.
I can stand up and write on the board. I can be your hand.
Exactly. Right with the left, that nobody can read that. Yeah, and then you just have to think of how to tally. Like, it would be good to have some structure on how to go to certain groups, and then also back and about this trying to review. So there's an hour. Yeah, probably. So we have a reception at 5.
Yeah, and there will be a reception before the time that, yeah, but we have to go over, but we don't want to arrive before the break.
Yeah, but the reception is planned at 5:15.
I know. Yeah, I think aim at.
You guys do like
So rather than people doing it on Slack, I would just say like maybe label the questions and say like one.
Yeah, maybe you notice. Yeah, so you want to, your questions are probably great, or do you want to add like how
I'm really not going to play with Binaries. It's new enough to me that unfortunately when
just
I
keep sending it because I mean, we like to know more about
how does this happen?
Let me go.
I'll ask Rob. She knows which of the things.
These were the questions we had. So we could add. I was just planning. Well, I would do it on here, except it gets really tiny when I'm in the external mode. So we can add questions. I was thinking to add them.
Right here.
Or get a symbol per question or something, and then tally next to it.
You can tally for these here. I need some space to tally them, and I can try
really tall.
Here.
Or a year as well, right?
Yeah, you can tally that. I think it's more US versus we don't need to be very strict, right? As long as people kind of self-organize in groups that are same order of magnitude.
We want slides again.
Well, not necessarily. That's up to you. Familiarize with those tools to decide.
I think that groups can present back in any form they want. If they, I mean, my view would be just we want them to present back, but whether it's someone just getting up and talking, I think to me that's fine.
Say these, and at the end, like when you say these, we expect people to present back, you can make a Google slide deck for those that want to keep slides, but let people know that it's not mandatory to have a slide.
Yeah, I mean, to be fair, the slide that I made earlier, I made it in like the last 30 seconds. So.
How much time do you want to take for coming back?
I guess you can do a lot.
I think we should keep maybe the number of groups at most, like 5. So like if they don't, if there are questions, I mean, we can add questions.
So keep the for 5.
How long are you?
I was probably going to fit it in like 20 minutes or something. But we'll see.
Explanation, but then you still will have only half an hour for the discussion. Then it would be 4, and then we have half an hour and half an hour. That's okay.
There's an hour. There is an hour and 45 minutes.
Yeah. Yeah. So there will be. I think like 20 minutes
times
of
15 minutes.
explanation, and then they. Like I would say aim
for 5 so that it's actually 5:15.
I think the biggest thing is just to efficiently get people, get the questions up, get them into groups, and so we can figure out the time even after we release them. I mean, we just have to do that.
do something like say you can just like 5 remarks 1, 2, 3, 4 corners and then in the center and people just walk there and then they find a place. You can send it to the back. So we just have to tell people yeah, sorry, this is what we do. After your thing.
Some of us
There's two options. One option is we tell everybody, okay, it's over, go out, or we leave it going, but then we have to make sure that otherwise it's like spiraling. So if we are happy to stay here, the party
It could be that it was like, so it's actually like very safe. You don't all the training to be there.
I think so. Yeah. I think we should be okay. But yeah.
Again, sorry for making you.
I think.
Thanks for evaluating any of it. I'm sorry. Also. Sorry, it's complicated.
I think it's also I wanted to ask if you wanted to, if you think you can
whatever some of these
should be fine. You can pull it all out. You can pull it up. No, okay, yeah, but I do feel really sorry about taking out of guys.
But it's not showing.
I understand. I also feel guilty.
Let's go grab coffee.
If you have other people that you want to.
No, so I'm gonna see my father tonight. That's why. So tomorrow I'm free.
I think like that's why maybe I should this is a long as you reach almost they are so these ones still are higher. They're all unlucky master constellation. They're almost constellation. Yeah, this does make it look like.
Yeah, so I guess it is the same gap. It looks like it's got the same gap, right?
First one we saw. The first part of this is distinct from the beginning, and the result of this is that in this log you're at what? I can't even tell that subtle difference between 0.55 and 6.5. For Mesa, all the some very take out nuclear.
You
Allow it to So you've got a flirting and you've got a fixing.
So yeah, so I think
you see how it responds on a nuclear timescale to mass flux in the absence of nuclear. You don't want it to you want it to be like that color. How would it look? Because if you allow it to, if you take away mass on a nuclear timescale, are you here on? You're shifting the track by like a little bit, so you have to say you're taking the mass. So interpolate between 20 interpolate the mass and also grading have the same fractional. You don't just switch tracks and still shift tracks and still a situation.
there's a lower, there's a technical trial that happens all in my life.
Change that's first only that these were pretty hard to get.
So that's something kind of on my next one. Sort of, I thought about when I was looking at like the astrophysics to assume some of these states
Case B, so this is why this is why no, it's terrible, and this is why in this so the data analysis that went into this plot was ruined because you don't have an envelope left to say, oh, these stable ones should be type 2b. We should completely, so I have to go back and okay, well, let's try all the different types of mass transfer kind of thing but also super reliable because we have no idea.
But like I don't think anyone's done a good job or
some small shouldn't have the same envelope at the time. Super
I was thinking that.
But it is single low mass, low is 18 not only but in some cases and then high mass. You don't know even if you think the boundary is you don't know how big that window is you have.
Yeah, no, it's I mostly work on
and you don't even know the other one. I mean, this is if you have a full
like I based on the thanks very much.
So for me, the rotation
model regarding the code
is perhaps the structure and so the temperature. What I aim to do is
oh yeah, this is like kind of stuff. Yeah, just like describing like when the working period is smaller than larger than any kind of the viscosity needs to be and then
I'm not sure.
There's probably another part of mine, but I'll look. Supernova hydro,
yeah, but we have early reanalysis. We have to reanalyze it in
really orders of magnitude. Yeah.
That was so the epic call after this.
I can take the
he's the one that's saying let the scale master model. We don't even we don't always.
So it's easy to check.
Also the guy that came up with this new model that was those or with this. It's a two-stage
the effect of
stop
can run an exponent, and it seems like
So as a result,
say,
your common envelope doesn't shrink as much as it used to. You also have the same
Right. Power, and
there's
so
some other.
yeah, I think Andrew Barker has a no. It's just like it works out like a broken power law, depending on your viscosity at different times.
Yeah, I was hoping that there was some rapid
Because like people getting from 3D, like some.
I can't speak for all of us, sure. Stuff, so I don't want to
Or like 3D people, like some of the 3D results, like they say that they close to like some other like claim it's not.
That's the thing. This is what I
Oh, right. So that would still be what I'm doing with my research. That's the life population.
I think one of the things that came from Adrian Barker and his group was that it's not just like one. Yeah, so it kind of like goes from there's some regions where it's more like that, some regions where it's more like
that's where they extend the metallicity. I didn't think they were at
it goes from like 0 to maybe not one.
And we've just different approaches. We're not inherently.
Pretty big enemy.
The CMO, I mean, I'll get things that no pressure.
Yeah,
I don't get why you need to package all of that in a software.
For saving most.
On a cluster normal.
Have a whole grid in both your single cell and your binary interaction.
Oh, they all in binary. So you don't need many of them. Someone else build this. It's kind of the same as the one we have a lot of.
Okay, so in basically,
Yeah. So
I love that.
I'm not familiar with. Oh, submit that.
Running idea with your running them. Running, then checking what.
Because we like celebrate that as like fancy like restart. Yeah.
I have benefited from
starting what? Unfortunately.
Yeah, but then when doing grades, you go from 5 solar
turn to like.
So that was really the goal of this. My takeaway from this factor of 10. So this observation, trying to capture the fractional uncertainty rate on the system. The uncertainty on the observations is already quite large. Uncertainty in our models, even doing slight variations to these these are the massive.
I even feel like
you see variations.
or my house condition in general.
But not really the point.
So it's we're running all over New York. Just
Like 5, 6 miles, like slow, like
They're great. If you stop sprinting, none of them. That's how I would say it. But I think it's at least a good first order confirmation that our models are so fascinating.
Like the street, like it still counts.
Still counts.
To me,
this one, I
not that. Yeah.
So I'm very
with the Nike.
too many things.
Yeah, there's a Nike app, like doing the run
Earlier, including supernovae.
Yeah.
I would make the same statement now. If there's too many uncertainties,
If there's no reception, I will just run to the supernovae.
Hence why we're not that case say. So you bring it all the way back. Say what? Can we even say the first thing we can do is simplest thing to do is a binary? Can we do that? No. Can't even do that. So we gotta work that.
Right. So
if you keep going back to
the
black hole, you
furthest
gotta
point
go
I
a
reach
few
is the
rooms back to
natural
black
poly.
right. Yeah, right. So I don't know. That's pretty. That's
Yeah, I need to publish this one. This one's this is in my PhD thesis. I've had feedback on it, and I've just sat on it.
It will show you like your
Yes, I need to like stop like
Yeah. Yep, we tried this. I like the observations aren't that good, and theory isn't that good. It's still larger. I'm not like inspired by this, so I've sort of lost. At some point, I'm also. Yes. No. I know there's people working on this, so my co-authors have told me I need to get on.
If you decide as well, you can add it to the setup like this is how the first name. The thing is, you don't have to start. You don't have to search for these things anymore, which goes to time.
Yeah, first name, first name.
You can take as possible.
118.
Give it to you instead of doing these that thresholds to you won't. It was then you can just start picking.
Whatever happens with the models we need to so one they will kind of improve like the stars expand right above the roof, but they're so far apart that they just tiny mushrooms, like a shrimp.
That is like just 100%.
Exactly, and that's why it's a bit higher. The case B, all the case B.
I'm using this.
or these are very in line with each other, which is great. So
wondering that because
how we
mass transfer efficiency is always like the amount of mass that they actually accreted is 0.3 more solar masses.
There is, and I remember your paper, but
everything else is not. It's just lost.
But you also found, if I remember correctly, that these are stable.
Yeah, all of them, yeah, until like 0.5 or something. It was always stable. But again, it's like stable. All of them could be stable if you change. Actually, all of them reached the
Wow, so you can lost.
I can't. Otherwise, I have some of them which
like it's so foolish to see, but it doesn't tell you anything. It's just like I think Strava watched this.
Until like 0.3 or something. Yeah, because I read your paper. Yeah, sorry. He took yeah, he was like, oh yeah, but it's the dynamical enhancement must transfer. It's like, no, if you look at the dynamical enhancement, it's like 100. Yeah, it's like, moment you do the envelope one, like that. Oh, nice.
That's also.
Okay, but this is because of the surface. So this is the you can't trust this because this is my modification. Right, this is when I change the versions.
This is a mistake.
Oh, you can't trust it.
Balance of having enough coffee to stay awake and so much coffee that you're like, yeah, no,
It is. This is the peak. This is from the. This is from the nickel.
Yeah. What's the character? Right. This is
okay.
All right. So for this next session, Julia and I were asked to sort of lead. I'm going to give a formal talk, and then we're going to sort of put up some questions we have at the end, and then in the next session we'll be breaking up into groups. You know, either some of the questions we raised or questions from the audience. So as I'm going through, if you can think up some questions that you might want to raise or general questions for a broader discussion, we'll put them up at the end. And I also want to keep it, very informal. If you have some question when I'm going through this and stop me. So I was asked, or we were asked to talk about electromagnetic observables during mass transfer across wavelengths and timescales. And I know this is a workshop on stable mass transfer, but I'm going to talk about things that can happen during unstable mass transfer as well. And I'm going to be a little bit provocative. I think I'm going to talk about a lot of things that you may not normally associate with mass transfer, that you, or you may not appreciate could be related to mass transfer events. Things like fast radio bursts and fast blue optical transients. You may not have heard of the Blue Ring Nebula, so I hope to try to go through these. And I'm also going to switch between sort of massive star considerations involving compact objects accreting and some things that I think are more broadly relevant also to lower mass binary interactions. So as we've heard in this talk, you know, if you want to go from a massive star binary to a gravitational wave source, for example, or many of the other exciting things that happen along the way, you have a number of different phases of mass transfer onto the compact object or into the compact companion. And this can occur on a variety of timescales, from nuclear being the longest, the thermal timescales, and possibly even dynamical timescales. So when we talk about, you know, dynamical unstable mass transfer, it's not like that happens immediately. It could at least take a few orbits. So you can have very brief phases of mass transfer that in principle could produce something detectable prior to even some kind of dynamical phase like a common envelope. And of course, if you have these mass transfer rates onto a compact object, you know, they represent a range of accretion rates from sort of, you know, order Eddington or up to things that are, you know, super, or even what I'll call hyper Eddington accretion rates. But they may be very short-lived phases, so they may not appear in the local population of events, but they're nevertheless occurring out there in the universe. And exactly our partition, say, between thermal and dynamical time will depend on some of the questions that we're addressing in this workshop. So I just want to go over from a theoretical standpoint a few aspects when you do have super Eddington accretion onto a compact object. I think a generic feature is that you get very powerful outflows from the disk, winds from the disk or jets, and sometimes these are interchanged. And one essential feature is if you're accreting at a sufficiently high rate, basically photons are trapped in the accretion flow, so it cannot cool. And when it cannot cool, the energy that's liberated gravitationally as matter falls into the potential well cannot be radiated, obviously. And so what simulations show is that a large fraction of it actually comes out in outflows. And so if you feed the outer edge of some accretion disk at some rate R out, actually what makes it down to the compact object can be a small fraction of that, which tends to, theoretical models tend to say is some power law in the inner to outer radius. And we know that these, you know, disk outflows / jets can power sort of large scale nebula. I'll come to this in a second. Microquasars. It may be responsible for beaming the X-ray emission in these systems, which may or may not be intrinsically super Eddington, but certainly in some cases appears super Eddington. And then also, as we've discussed, if you have a sufficiently high mass transfer rate, you can get mass loss out of L2, which may produce a large, extended, possibly dusty disk that could produce an infrared excess. And of course, we see these wind-inflated ULX bubbles in other galaxies. These are highly accreting sources in our own galaxy. The prototype we've already talked about is SS433 with the Manatee Nebula, where you have some kind of evolved donor star accreting probably onto a black hole. There's all types of phenomenology. You see this sort of big, large-scale, multi-parsec, maybe even hundreds of parsec nebula that are basically inflated bubbles by the winds from the accretion disk. On smaller scales, you can see radio emission from what appears to be a processing radio jet. You see these lobes where the jets go out and shock the swept up interstellar medium material, producing hotspots in X-rays and in non-thermal radio waves. So there's a really deep rich phenomenology of these systems, which in these cases, you know, extend across, you know, multiple. This is why it's called the manatee. It looks like a manatee. This is from my student Naveen. So another feature, interesting feature, I think, of these systems is that the the accretion disk can precess, for example, as a result of lens carrying precession about the spin axis through a black hole, and this may be responsible for causing these ULX sources to swing in and out of our line of sight, and you can measure these superorbital periods. So I want to connect now to some other observed phenomenon astrophysics, which I speculate with my student might be related to these sources, and these are fast radio bursts. We all know what fast radio bursts are, but essentially there's been a discovery of one of the most studied fast radio bursts that shows that the arrival phases of the bursts are periodic. So every 16 days, the FRBs only arrive in these few day windows every 16 days, and you see some actual structure and the properties of the fast radio burst across this few-day window. And we're also, learning that, and so it's sort of been suspected that all FRBs arise from magnetars. It's not exactly clear how a magnetar would produce this type of periodicity. And we also now have evidence that some fast radio bursts occur in old stellar populations like globular clusters, where it may not be so trivial to make young magnetars. And so this gets people thinking: is there something going on in terms of binary evolution that could be related to fast radio bursts? I should say my review is highly biased towards things I've been thinking about. But so I think one of the interesting things is whether you could get periodicity from an X-ray, a binary, for example, an accreting neutron star or black hole. And as I said, because of this lens tearing precession effect, you predict some connection between the orbital period of the binary, which is basically how big the accretion disk is and how long it takes for the jet to precess. And these are sort of known ULX systems. They exhibit this kind of behavior. And sort of it's interesting that the precession periods are similar to the claimed periodicity times in a few FRBs. And so the picture, without going into any details, since this is not the right conference for this, is that you may get shocks or reconnection in plasmoids that are ejected along the spin axis of the black hole. And this could potentially produce FRBs that you only observe when the jet is pointing towards you. So it's interesting to think, as we look at populations of fast radio bursts, what types of galaxies they happen in. Is there any connection to where we might be getting phases of super Eddington accretion, which you kind of need in these scenarios to get a powerful jet to observe something. Another interesting connection to FRBs, I think, is the fact that many of these repeating sources exhibit these compact radio nebula. So there's 3 FRB sources now, and sitting at the location where the FRBs are coming are these very radioluminous. They're brightest non-nuclear radio sources we know about, very compact, less than a parsec in size. And we also know that they're highly magnetized, not only because they produce very bright non-thermal synchrotron radiation, but because we see a high rotation measure, which tells us that this medium is baryon rich. So it's just a pulsar wave nebula would not be baryon rich; it would be electron-positron pairs. But the fact that it's baryon rich is suggestive. Okay, maybe there is some baryonic matter, for example, mass transferred material in these nebula. These are far more luminous than the radio sources I showed you. For example, from SS433, which are a few orders of magnitude dimmer. On the other hand, we know sources like SS433 are long-lived systems, 10 to the 5, 10 to the 6 years. So we hypothesized, well, what if you had very much younger mass transferring sources, very short-lived mass transferring sources? Could that explain these very compact but nevertheless much brighter radio nebula? And so with my student Naveen, we worked on these sort of inflated hypernebula models where we basically consider a model where the outflows from the accretion disk are inflating this bubble. So we're tracking the properties of the expanding bubble. And then we're assuming the jet goes out and shocks and injects relativistic electrons. And then we follow those electrons as they cool through radiation and expansion and follow the synchrotron radiation they produce. So you can essentially predict, given a mass transfer rate and how long you think that mass transfer rate should exist and the power of the jet, you can predict things like what should be the time-dependent size of the nebula, what should be its synchrotron emission, and things like rotation measure, which you can compare to observations. So this is just showing this type of model in greater detail. So this is an example on the right showing the number of particles you inject into the nebula, the magnetic field strength, et cetera. And so typically what we find is you can get actually quite, if you have sufficiently short phases of very high mass accretion rates, such as we might get in thermal timescale mass transfer, or maybe even pre-common envelope dynamical mass transfer phases, you could actually get quite bright radio nebula that might, instead of extending hundreds of parsecs in size, might be less than a parsec in size because they're very young. So this is just showing some light curves for different assumptions about how long. So transferring the same amount of mass onto a black hole companion for different amounts of time, what type of radio light curves these nebula would have. And so you can ask questions like, okay, this should produce actually thousands of Milijansky radio sources across the sky, potentially, depending on how frequently we think these mass transfer phases happen. But they could be, so you can go through and ask, for example, the Very Large Array Sky Survey, how many of these mass transferring compact hypernebula might exist in the survey, and we find it could be substantial, but only a fraction of these will actually exhibit time variability over the course of a survey. Otherwise, they would just basically be stationary, temporally stationary sources. But anyways, it gets you thinking about whether we could actually go out and look for these short-lived phases of very rare mass transfer. I want to now switch topics and talk a little bit about things that apply to all stellar mergers. In fact, most of the ones I'll be talking about are lower mass stars. These are we've heard about this luminous red nova, whether they are luminous or red, I guess is somewhat debatable, depends on what phase you look at them. But this is a number of the luminous red nova sort of light curves. And these are the samples. There's slightly over a dozen of these now. And we compiled them in this paper with Tatsuya. There's a few aspects I want to point out about the light curves of these, and we'll get to why we know that they're from stellar mergers in a little bit. But basically, there's two peaks to the light curve. So there's an early peak sort of at the very beginning. Actually, there's a pre-dynamical rise in many of these, which is suggesting some mass transfer happening before the final dynamical plunge. But then there's a first peak, and there's a second peak in the light curves. And this actually, I'll come back to this in 1 second. But the other thing I want to say is that, in many cases, you can go back and look pre-imaging at the location of the luminous red nova and get a constraint on the progenitor system. And these are sort of the donor radii and assumed donor masses for a subset of these for which you're able to do that. You see that many of these luminous red nova, the stars, are sort of mildly evolved or yellow supergiants. They're at the end of the main sequence or slightly beyond that. We're not seeing a lot of red giants or red supergiants in the progenitor samples. So these are stars that are presumably undergoing mass transfer as they're evolving up to the red giant branch and are merging. So I want to talk a little bit about how these light curves are determined to sort of give you some hint about what type of information you can get on them. So this is just an example of a simulation. I've talked quite a bit on these as well. Of a common envelope event where you have a companion star which falls into the envelope of the accretor, of the donor. And to generalize grossly, it depends on what is the mass ratio of the system, et cetera. But to me, the rough outcome of this is during the plunge phase, some fraction of the outer envelope of the donor star gets basically stripped off and ejected into space. There'll be possibly further mass loss as the companion spirals in. But typically speaking, for some mass ratio that's not extreme, you might eject a few 10% of the envelope. And in that process of ejecting material, it's sort of heated up to a temperature which is of order the escape speed. And so when it re-expands, it will acquire a kinetic energy which is comparable to the thermal energy deposited in the material. And actually, this is just to point out that, even prior to the dynamical plunge of the companion, you start to get mass loss, for example, from L2 that can sort of set the environment around which this final coalescence occurs. So when you look at these, like a light curve of a supernova, any kind, what you're seeing first in the beginning of the light curve is the fastest outer material. And then as time goes on, you're seeing deeper and deeper in. Of course, this is grossly simplified since it's not a one-dimensional problem. But nevertheless, you can model it in a simple one-dimensional way. And what you find is that you naturally get these two peaks that we see in the luminous red light curve. Essentially, the first peak is the outermost ejecta layers, which acquire the highest speed. They have the highest thermal energy, and they radiate their energy quickly. But then as the photosphere retreats inwards, it reaches the point where hydrogen recombination sets the photosphere location, and then that proceeds inwards to the ejecta. And so the rest of it can in principle be powered by hydrogen recombination. And Natasha has worked on and pointed out this early in this game. So basically, by measuring, the point is by measuring in this early phase, you're learning something about the fastest material, and by measuring this, you're learning something about the bulk of the ejected material. What I want to say is that there are a lot of similarities to type 2 supernova, where you also see two peaks. One is called the cooling envelope. It's when the shock goes through the red giant and the outer layers cool and radiate. And the other is the plateau phase, where indeed the photosphere is controlled by recombination. But I also want to point out there's differences between type 2 supernova and mergers. One is that in mergers, in supernova, radiation pressure always greatly dominates gas pressure. In luminous red nova, they can be comparable, so you have to account for that. And the other is that supernova recombination energy doesn't matter. So recombining hydrogen is not what powers the light from a supernova. It's the energy dumped in by the shock. But in these cases, actually, the 13.6 electron volts you get per recombining hydrogen actually dominates, and that affects things. So you could take these types of simplified models, as we did with Tatsuya, and make predictions. So if you consider that the donor mass, a fraction of it is ejected, which is fixed, which is questionable, and you and then you assume it's ejected at the escape speed of the binary, then you have all the properties you need to make some analytic predictions for how luminous these red nova should be and how long their plateaus last. And so this is just showing some examples of what you get, assuming the merger occurs at on the terminal 8-base sequence, or maybe 10 times off of that. And so generally what you find is that brighter and longer, it's not surprising, brighter and longer transients from more massive or mergers that eject more material. And what we also found was that there was a few cases where even if we allowed the entire envelope to be ejected, it wasn't sufficient to explain their luminosities. And so this was suggested to us that there has to be some extra heating source other than just hydrogen recombination powering some of the light curves, if these are actually luminous red nova and not something else. And so a natural thing that lends itself here is that, as I mentioned, prior to the actual dynamical plunge, we have discussed there could be thermal timescale mass transfer, there could be many orbits of material which sort of create a circumstellar medium surrounding the merger. So when the material from the dynamical plunge, the fast material that's ejected, when they actually go together, goes out, it will collide with this material. And the shock actually can get hidden because the fastest ejector sort of spreads around the top, and so you can actually get shock heating, which can boost the available energy source. And so we may be seeing hints that that's present in these systems. And we know that this happens. We probably are all familiar with the example of 1309 SCO, this contact binary that was observed by Ogle for 10 years, which is the poster child for how we know luminous red nova make mergers. This was the binary where we actually see its orbital period shrinking, as well as its p dot rising. So it's merging. You can see the contact binary getting closer and closer together, and you could actually see the light curve, the phase light curve, evolve from this double peak structure where you see both sides of the binary to the end where you essentially see only a single peak. And our argument with Andre Peja is that you can understand this if you start losing mass from L2, for example, at a higher and higher rate, eventually the amount of mass loss becomes so great that it obscures one side of the contact binary. And so it sort of takes your double peak light curve and slowly changes it to a single peak one as you lose mass at a greater and greater rate through L2. And the angular momentum loss through L2 can potentially be sufficient to cause the p dot or contribute significantly to the p dot that is observed. I want to switch gears. The problem with luminous red nova is we observe them, they're bright, and then there's this mess because there's this slow material, this dusty molecular material, it all forms dust. You can't actually see what's going on in the center for many, many years until the dust clears. So we'd like to find analogs of stellar mergers after they've evolved. I'm running out of time. So with Terry Hoadley, is a professor at Iowa now. We worked a few years ago on what we think is a stellar merger product, the so-called blue ring nebula system. And I don't know how many people have heard about this, but I'll give some shout out to it. So this was a blue ring detected by Galax. So it's actually a biconical outflow like this. You could see the blue and red shifts as you go across this. And what you're seeing is basically fluorescing H2 that has been heated at a shock as some hydrogen-rich material has been ejected from some object in the center. It turns out in this case, you can sort of trace back how long this conical outflow to the origin. It took about 2,000 years ago, and there's at least a few hundredths of a solar mass of material in it. And there's this interesting central star in the center, TYC 2597, which has a number of peculiar properties. So it's between a 1 and a 2 solar mass star. it has an infrared excess, so it has a dusty debris disk around it. It also has UV excess. It has variable H alpha emission, which means that the star is continuing to accrete gas. These are the properties. So it's a fairly luminous star. It's a bit puffier if you compare it to, for example, horizontal branch stars. It's a bit lower surface gravity than most of them. But what's weird is it's a fairly massive star, but it's out of the galactic plane, which is where you'd expect to see older stars. So what we think is happening is that this was a 1,000-year-old stellar merger. So the same thing we described is actually similar to 1309 SCO. But there was some material which during the, let's say, merger common envelope phase was not completely ejected from the system, but remained bound in the accretion disk and continues to this day to accrete on it. And this, but this outflow was shaped into this bipolar structure by the interaction with dense equatorial material. So one of the tests of this, we were working with the observers on this, myself and Ken Shen, and we said, well, we know one prediction of these types of common envelope events is that you heat up the star as the companion falls in, it spirals in, it heats up, perturbs the donor star, and so this star should be a little out of whack. It should still be recovering from being out of thermal equilibrium. And so we did some simple MESA models where we just dumped energy in for an inspiraling star into this 2 solar mass star with different phases after its sequence evolution, and we sort of tracked how its luminosity would then settle back onto the thermal equilibrium. And indeed, we told the observers to go. It turns out you can go back in the Harvard archival plates and look at this star 100 years ago and actually see that it was brighter and has been dimming over the last century. And so when we combined, oh yeah, I'm behind time. When we combined the requirement to explain the dimming rate, the luminosity, the effect of gravity, we found that this worked pretty well if we had the inspiraling star of 0.1, 0.2 solar masses. Okay, I need to finish. What if a compact star goes into a common envelope and we have a failed? I think it's something else we think about. What happens if we have a failed common envelope event? Well, you could get potentially one explanation is you get a prompt merger between the compact object and the core of the massive star. And Sophie Schroeder, for example, has worked on this recently, that the energy released by that merger, also Noam Soker's worked on this, that energy released by that merger could basically go out and sort of effectively be like an explosion inside the common envelope ejecta, and then that could give rise to a very luminous supernova. But one thing I want to say is that, even if, let's say you do mostly eject the envelope, so the binary tightens, but not completely, and you do have some relic material left over in a circumbinary disk after a common envelope. Just want to highlight some work by my student Semi, where we looked at the long-term evolution of these post-common envelope binaries, accounting for a number of pieces of physics that I don't think were previously considered. Things like the fact that the central helium core will be a source of UV radiation, which can, it's kind of like a protostar system. You're placing the protostar with the helium core so it can photoevaporate, for example. So what we found was, not surprisingly, actually, even if 10% of the common envelope remain in the disk, it could actually cause significant evolution of the binary. Okay, my thing's gonna be taken away from me now. So, all right, I will stop by simply saying that these circumbinary disks, they may cause delayed mergers between the core and the common envelope. And I think this is interesting because it means that these mergers could happen within the environment of this relic disk. We could get explosions, and not in some big hydrogen envelope from the common envelope, but in a more tenuous, radially extended medium of this disk. And we actually do see these things called fast blue optical transients, whose time scales actually are remarkably similar to what you get if you disrupt the helium core by a compact object. So I'm going to finish there. My takeaways are up here. I think the main one I wanted to say is that, massive star binary and also lower mass, well, this is mostly massive star binary, involves multiple phases of these hyperred accretion. What I'm instilling you is that there should be direct observational consequences. Even if these are rare things, they're very powerful, and they should be directly observable. And I think our local systems are a little bit biased. Okay, so I'm going to finish there. Some questions that then we'll segue into having questions from the audience that don't have to be on anything I talked about. But
yeah, so, Brian, we can also have audience questions first.
Okay.
Before we break into the discussion, and we can use that as sort of a point to transition to these questions that you have prepared. So, questions for Brian.
Should we first clap?
First, let's clap.
Very sorry for talking so long. Yeah.
Now, questions for Brian.
I have two quick questions. So I was very intrigued about the progenitors of the luminous red novae. You said they were slightly evolved stars, which kind of to me seems like we're missing the AGB stars. Can we learn something about stability of mass transfer from these systems? AKA, what does it mean that we're not seeing AGB star progenitors? Does it mean something, or is there some selection effects against them?
My guess is, well, Natasha may have her own opinion. My guess is that these ejections from common envelopes, my guess is they become dusty very quickly, and so the optical part of it is very short-lived, and then so these would be more infrared bright transients. So we may be missing them for that reason, but there could be other explanations. Maybe we don't have enough yet. I don't know. It depends on.
My other very quick question is, what if the common envelope sets in not in like the normal overflow way, but in like the tidal instability? Like what if we have like a Darwin-Riemann instability so that your secondary star may fly into the envelope in a much more radial way, in a much more higher velocity way? How would that change? Would it change the transient itself? Like that first peak, would it be more narrow? Would it be higher? Would it be?
Yeah, I mean, I think if you ejected material very quickly, then you wouldn't have any time to sort of, slowly peel off parts of the star. So it probably would, your transient would have a very abrupt rise. I didn't show this.
It's like the plunge in would be faster, but then as you're deep in the star, I think those last little bits probably would be the same, but the initial plunge in would be shorter.
Right, and I think most of what we see with the luminous red nova is what is ejected during the initial plunge would be my guess, because these things only last for they only last for a few months. So
in their paper, which will be soon submitted, we do actually have initial blue peak. I mean, we call it as a blue because observers call it blue. It is like a 16,000, 15,000 Kelvin peak that comes directly after the plunge, and then we move to the plateau.
I had a question myself. How much, how much of the properties of the nebula is coming from the properties of the stars before merger? In a sense, can you use the properties of the nebula to say anything about the pre-merger?
When you're talking about nebula, you're talking about long-lived nebula, like from SS433?
Exactly, yeah.
I mean, my guess based on these models is that nearly 100% of the mass transferred is actually going out into this nebula. So if you can measure the mass in the nebula, my guess is that that's like an estimate of the integrated mass transfer, more or less, because a lot of these models predict that only like 1% or 10% actually gets down to the compact object at most. But what I don't know from the observers is how well you can actually measure how much mass is in the nebula, because you probably are only seeing the mass that has just been shocked. But if you could figure out like sort of the integrated amount of momentum to produce a given size, then maybe you could get a better estimate. So it would be good to get a sense from observers. But my guess is you're not going to be about better than a factor of 2 or 3 or something.
No, that would already be nice.
What?
Factor 2 would already be nice.
Okay. Yeah, we should think about it. Yeah.
As a follow-up to what Hughes just said, you could also have inefficient mass transfer before the actual onset of common envelope evolution. So you would have a fraction of the mass that was actually ejected from the system before the system actually starts the plunge in. So perhaps you could have some signature in perhaps like, I don't know, like a sort of offset on the light curve or something like that, that could be attributed to this, I don't know, like homogeneous disk or whatever that was emitted before the actual common envelope ejection.
Yeah, I mean, my guess is so these light curves turn off not because they're running out of, say, material to run into or to I mean, they mostly turn off because you're forming dust. And so the peak, if you could follow this bolometrically, it would continue in the infrared. So actually, my view is if there's ongoing shock interaction, that you might see that imprinted in heating, that is where the energy is being reprocessed by the dust. So I think it would be interesting, yeah, to get infrared. I mean, I think Roman will be very good at this, but maybe there's other things you could do from the ground. Yeah. Wise, Kishiloide has a bunch of wise candidates that I think are.
I have a question about this kind of so-called like failed common envelope or common envelope where you don't successfully expel the entire envelope and you have a merger instead. And I'm just wondering how much we understand how much of the envelope can be removed, if any of it stays bound, if it's possible, or yeah, roughly what fraction of the envelope can be removed still, if any.
Right. So we found it was with my student semi, we found that there's a fraction that does accrete still, and then there's a fraction that gets photo evaporated from the UV, the helium core. And exactly how much angular momentum we put in the disk, that fraction, you know, could shift. But I would say it's kind of order unity is accreted. I mean, like I wouldn't say 50-50, but it's not, you know, you can get both matter that is unbound, photo evaporated from. So I think not all of it would end up into the black hole, say, if that's a black hole or.
Okay, thank you. So yeah, some, but not all.
Yeah, I think we need better models for if there are these disks that survive and don't get ejected. How much angular momentum do they have? Do they have the angular momentum of the original binary or something else? Yeah.
Yeah, I would like to go back again to the failed common envelope case. So the point is that according to what you're saying is that when we are supposed to have a merger, we don't really have a merger. I mean, we don't have like the black hole inside a star. We have a black hole and everything around that has been disrupted, right? That's the general overview.
I'm saying that after a common envelope, you may have the helium core or the core of the evolved star and the black hole, you know, still orbiting each other, but there's the disk.
Yeah.
And then when they do come into contact, I don't think of it as the black hole falling into the helium core. It's actually more like it tidally disrupts it. It's a little different with a neutron star. Okay, it may be more relevant to think of that as falling into the helium core.
So, I mean, with neutron stars, we are still fine to look for Thorne-Chetkov objects. So it's not like it disproves the fact that there might be Thorne-Chetkov objects as well, right? For neutron stars, it behaves so differently.
That's another question. I'm not sure I believe the Thorne-Chetkov objects can survive, but okay.
Okay.
Maybe I don't want to exclude it. Yeah.
For Tizio, stay tuned for the next workshop on unstable mass transfer.
All right.
Yeah. One more quick question or comment from Helium, and then.
So you, in one of your slides, I think you showed 10% of mass loss from the merger process. I guess perhaps it's
this
from
is
the
just very
MHD?
crude. This is just very crude. I'm just saying it's closer to 10% than
Yeah.
1% or 100%.
So
I mean, it varies. I mean, you can ask people who do the simulations. You know, this is just a rough number from this particular paper.
So I guess from the light curves of luminous red nova, you can constrain the mass lost from the merger process. Does it match this temperature?
It does. I mean, you can make it match. I will say it's very sensitive. It's very sensitive to assumptions, like whether you use the velocity that is the observed spectroscopic velocity of the transient or some estimate of the escape speed. We don't know that the observed velocity. So I would say it's reasonable. The two exceptions I highlighted were these two events, which would require larger than 100%, which to us was suggestive that there's an extra energy source, because these models assume that it's just going into vacuum. Okay, so that's the only energy source. So that was why we were motivated to think about shocks or other things going on under the surface that are adding energy. Yeah.
Right. I think we should move
okay.
on because we're actually supposed to have a group discussion. There's not too much time left. So let's thank the speaker again.
We're asking people to add questions. So what were some broader, these are some questions I raised, or we raised, Willie and I, but Matthias going, yeah, go ahead. Yeah.
Basically, the idea is that we do another group discussion like this morning. We just split up. I think we have roughly 25, 30 minutes to discuss, and then we come back and just inform everyone on what was discussed in the different groups. So here's just some ideas of questions that we came up with. But we also have Mathieu here, who will be my hand because I can't write. If anyone in the audience has other questions they want to discuss, and then we'll just add it. And the idea is to sort out this quickly because we don't have that much time. So if anyone has another urgent question, apart from the ones that are on there already that I guess you've read by now, now's the time to shout.
Do you want to read these questions out first so we're all on the same page and maybe you can editorialize a little bit?
Okay, so question one is how do we actually spot interacting system, and now more thinking of stably interacting systems that might actually be there for a certain amount of time, especially with large upcoming surveys of different techniques. So that's question number one. Question number two is what are sources of pre-dynamical ejecta and stellar mergers, for example, from a dynamical runaway phase or a thermal mass transfer phase preceding dynamical phase. Question number three is what are the properties of merger products? So for example, what are their rotation rates? Are they slow or fast? What is their composition? And how can we actually, again, find those from observations? Can we tag them somehow? Are they out of thermal equilibrium? These sorts of things. Number four is do high mass stripped stars, for example, post-common envelope, have debris disks or nebulae? Thanks. How long do they survive and are they actually detectable? And question number five is why is the observed luminous red nova population dominated by main sequence or moderately evolved donors? That goes into one of the questions we had before. And where are the giant star common envelope events, which is what we had before. All right, so any other urgent questions that should be added to that list?
I guess, I would maybe do something like, what can we learn from observations, like by comparing two models? And like, if so, which observations? Sorry.
How I synthesize that.
You write bigger?
Okay.
From observations, and then maybe like which are the most promising of mass transferring outcomes, basically, like of this mass transferring event.
What can we learn from which observations?
Okay, anything else?
Yeah, I have one. Are the pre-dynamical ejecta in systems that go dynamical then, and the pre-dynamical ejecta in system that remain stable the same? Or could that be the difference that causes one system to go?
Can you say that in French? Because I couldn't understand it.
Is there a difference between the pre-dynamical ejecta for stuff that then goes common envelope and the ejecta in system that remains stable throughout? Or could those differences be the cause of the difference?
Could we combine question 2 and your question into pre-dynamical ejecta?
Yeah. Great.
Question mark?
Okay.
Pre-dynamic.
I'm going to take my.
Exactly.
All right, I should leave it up there actually.
Okay, any other question? Yeah, I think so too. All right, so the plan is to now split in groups for like 25, 30 minutes. make sure you think of something you can report back. If you want to use slides, we'll put a slide deck in the chat, but you can choose if you want to or not, so you don't have to. And whatever is reported back, we won't have super much time because we don't want to be late for the reception. But it would be interesting to hear from the different groups. So we don't have nice smileys, so we'll just do something very easy. Corners are numbers, so 1, 2, 3, 4 for the questions, 5 and 6.
Wait, what was
1, 2, 3, 4, 5 and 6.
Not the middle.
This is 6 because this is
5. Then we only have no 5.
No, this is five.
Okay, okay, no, that's fine. Okay, 1, 2, 3, 4, 5 and 6. I want to go somewhere else. So.
I also want to go somewhere else. Nothing against 5.
1, 3, 4, 5, 6. Okay. Oh, and we come back at 40?
We come back at 4:40. And anyone who's standing in a corner, write the number behind them so everyone knows which number it is.
Yeah, 6. I just want to know, like, can we actually display?
We have to write it.
Here we go. I'm working on that. Yeah. 5.
Currently,
I don't know.
you mean currently?
Join us.
No. I have a quick
No, join us. No, we need Brian.
I just want to get on that. What is this?
It's generally like.
How
can we use you?
You as
You as an observer. Yeah, exactly. Knowing what everybody is.
So I
This is 5.
There's some complex. So I want to use stuff.
That's maybe the reason.
Probably have.
Okay.
So to make slides.
I'm more thinking about the.
I don't know what
I'm more thinking about the.
It'll show you.
Basically, what the
2 and 5, I was saying. Question.
Yeah, a little bit. Depending on how
They are really.
for pre-dynamical injector, you've got to remove different amounts of momentum from the binary, and therefore the driver envelope or driver dynamical instability or not. And I can see as processes that can lead to that. It's like that's from a
I just open it.
tech creature. I mean, it's possible, right? The young star objects have normal stars, normal massive stars don't have magnetic fields. And then I guess there is the disk wings that also have accretion through a disk. I don't know how significant that can be.
I don't want to be the one who talks about that, but
You want to go to as well, or a real two?
Yeah,
We should did about two. I wanted to. You wanted to? Okay. We were just discussing this.
I also onto a common object, either a black hole or a neutron star, and then accretions forms, and then because
everywhere like an accretion disk where everywhere like inflow,
the potential
outflow, even if it's sort of optically thin, but geometrically big. So then you get like everywhere, like so your accretion rate at the inner edge would be very different. It's actually same kind of estimate. But it also works if you have, like, it doesn't have to be like a compact object. If you have like a normal interacting, you could get around that it's currently transferring things. From then, so you could be fixed but very little star, and because almost everywhere is kind of bound by this outflow, and so then the outer edge, some of this outflow could get to the L2, eventually go into like a circumbinary outflow, like there's this paper spread by Fuller, Flu and Fuller.
Yeah, he was cited by somebody on this line.
And so I think that, and so here kind of related question to that, which is, I mean, once you get this circumbinary outflow, and you can start shrinking the binary.
Oh, they're almost both
it kind of always goes into a merger. But
during one, yes, that's a thing. It's a kind of
and stop this.
Just leaves common phenomena.
Like this process stops, and you just
I don't think we have to solve like specific systems and what they are, but let's
so, for example, one thing that's actually on this paper in tools, so
they did a lot of accretion look through,
like UV,
they will have to put on electromagnetic
binary output and just stop it. You can get
gravitational wave detectors to
back where.
But I mean, are there any more situations of borderline curves?
Let's discuss
will show
lose a lot more angular momentum.
That's how we spot actually.
Yeah, that's what I mean, right? Like for different types of these systems of mass transfer, we could just like have simulations with templates for the light curves, and that's how we spot them.
Stop this kind of dynamic pre-dynamical process, and then you just end up with a
Then
dynamic.
just question of
Maybe it's not possible.
that would also be very mass dependent, what you're proposing, right?
So yeah,
Because the
photometric
UV
surveys is
gonna
more
get
regarding calculus and spectroscopy is when
Maybe you can get both like a UV flux and just kind of like low outflow. Hydro. How can you
tell us how to spot
with OEB stuff? Well, and once you have that, it boils down to you have
also, right? That's the problem from ours. For mass transfer, and it's really easy to.
But in terms of
just one of the
like from a binary evolution perspective, what I need to know is like this parameter that Pablo mentioned this morning, how much mass we put on my accretor star, and this parameter that is the angular momentum
templates, and they just like compare with the observations, and whatever is the least like the
form a disk around the accretor, and then
like the
mass from that disk.
Residuals. Like
that would get the angular momentum of the Keplerian.
That's what they
quasi Keplerian
and then they try to they have the model, and they try to refine the fit. So I think the same approach can be applied to any type of data.
I mean, the radius is much smaller than the orbital angular momentum.
Ideally at the same time.
So that would lose less angular momentum.
That would the approach.
Would remove less angular momentum than what we assume.
You match filtering. You see whatever fits best out of your predefined grid. And then you can define or
nothing to
do. You can actually improve the model.
Like the models for the
and try to infer the
wins.
That's based on the assumption that you have simulation.
More than I do, so that's
depends on what you input
like
the model.
Are there like
can you summarize this in 2 sentences?
Or like,
I'm trying to take notes.
Yes. or there are simpler things.
For envelopes and contacts, for eclipses. Well, but it doesn't mean that they're interacting.
What do you mean, like in contact binaries?
Right. Yeah, okay. Contact binary light curves are very different. So
it is, but I mean, if you consider.
Yeah, but that's not gonna work. Like that's gonna be zero mass loss, right? The line driving gives you mass loss rates of the order of at best 10 to the -5 solar masses per year. Yeah, exactly. That's very high. I'm overestimating. Yeah.
and you don't have a long time, except KC.
But the thermal winds,
Is it in the context of stable mass transfer? Or is it like
Thermal wind, like you mean like the sun, like pressure? I mean, if it's tides, then they are all interacting.
But I mean, this is, so I found a large population of rapidly rotating redshifts that aren't they're not transferring mass onto a companion, but they are spun up. Red giant rotation should be like a kilometer per second or less.
Basically, if you have like a puff of this,
Second, and they're in binaries.
gradient, and you get like a significant.
They're on the lower giant branch, so they'll probably
I don't know.
mass transfer phase later on, but.
When you
we
have
found out
like
by looking for
when you
anomalies
have
that
these
support
these
things that
winds,
got rejected through the pipeline.
where from which radius is
like anomalies, right? You could so
it's all
Uh,
one way is to
centered and
separate
it's very
these
similar to
different
what
types of interactive systems to like some templates, but then another way is to look for anomalies, like new physics basically.
I don't know if that matters because if it's not opaque.
But it's yeah, you're bound to find other types of phenomena. Right? Like anomalous phenomena. But still, like some of them could be
outflow would be a doubt.
interacting systems.
That's getting relational.
So you about actual interactions, I think things like Doppler tomography for accretion disks, which is a spectroscopic thing. Accretion disk light curves that can be painted onto a system which are visible in eclipsing binaries where there's clearly extra parts of things that are obscured and not.
And circumbinary disks.
Does every bit cancel each other? Because it's orbiting much faster though than binary. Probably cool. Maybe
That way,
also.
in general, it's tracking. It has to be.
Yeah, it has to be tracking the
right?
star. Yeah, I don't. It's I from the top of my head. I don't. It's also probably should. There are papers. There's like these L2 outflows and then
almost binary outflow. Because it's like the inner parts of the disk are fast, but then the outer are slow.
But then the other parts wouldn't they be the most skewed by the Roche potential? Because inside you're circular, but then outside, I think I saw there was a diagram about the velocity of the disk, and it's very like lopsided as well. You have the one closest to the L1 point that's like funneled and faster moving, and then you have
another thing that's a giveaway, I guess, is the hotspot of a stream interacting with a star.
Doesn't really cancel out. Maybe cancels out
your signature in there. Depends. I don't know. It's probably some model that we can make at least in.
I mean, what I mean is that the contribution of
these hotspots are clearly visible. It's because they're obscured.
Goes in all directions.
Slightly out of phase.
What I mean, the momentum
parts of the observation.
Yeah,
it still hits it on the side.
But what I wanted to say was if the way it works is that you have a team of all these ideas is that you need to have like an idea of what disk is like, right? To see that's fine. The light curve on the disk, the spectra. And I think like for these large samples,
right, because it's gonna be tidally truncated, so it's gonna be on that side.
So you have a good understanding, or at least some idea of what you you can use like some machine learning techniques to extract the features and then just look for these features automatically. Right? That's like the
I can see how that basically the Roche geometry breaks the symmetry of the disk. Therefore,
you don't have to know.
But your answer to Evan's question, no, because of the Roche geometry.
Or to some
your answer.
first approximation, yes. But then,
but
to extract the features.
Sure, but we still need to inform slightly what to.
It's gonna be on the same order. You need to be able to like produce some synthetic.
Right, yeah, exactly.
Right. Then extract the features from.
I don't know anything about disks. I live in a 1D world.
Okay. Just
I think there is a
what extra things could be there? How much rotation of stars? Because they're being spun up. Is that something that? Okay, factor of 2, maybe then your argument doesn't really work.
Here's where most of
I think most of it, only this outermost part is where the mass is being most.
That's
just
where the
losing
mass
mass
is
from one part.
Oh, okay.
And there it is like,
I mean, the question then is also how does it jump from here to here?
Well, I'm
That's
not,
even worse.
are we sure?
Maybe,
Are we
maybe
sure
it's
that the
fine.
mass loss
Maybe
from
we
the
can fill in what they mean. Are we sure about it?
I was just trying to remember the only situation which I've ever
I
studied.
mean, we did list a couple of things already here. Maybe we could just
We're
figure it
gonna
out.
do
the
so
whole thing.
bad, we're gonna do so bad.
Yeah, no, I think we're finished. I've got 6 things here.
Not sure.
One A supernovae count as
I mean, just that's the thing. Like, okay, I think
They are important.
clearly we agree that disks are a source of ejecta.
Oh, to be fair, good point. No,
If you understand that, should we try to consider
we are the
potential
result of
source of pre?
creating white dwarfs.
Well, again,
Which then, say no and then.
Love soccer has a bunch of jets. And then these jets would, they would just deposit like, so we were like, poles.
Yeah, and that's usually the picture that I have in mind when we take away the orbital environment of the equator. So, okay, the mass went on the equator, it's orbiting the equator, and the jet throws it out.
That's a very interesting effect, right? But I think very difficult to infer. On a population basis, you might do something with that.
Like if you have a cluster and
These
exactly
it's not very, these outer regions are very low with respect to.
Like a blue striker or something. Whatever. Yeah, I guess, okay, so I'm also listing slightly post-mass transfer things in here, so let's remove stragglers. Right, but then we can just list the entire thing of all of the mass transfer products, right?
I mean, this doesn't need to.
Yeah, it's like slightly beyond.
And all the things are, like my question was like, are we assuming
those are also the blue stripe.
would they be different? Could this be the reason why we have this branch? Yeah.
Yeah.
For example, it starts losing a lot of angular momentum. It goes,
right in a way, like, okay,
but then at some point, maybe the parameters change, they're getting closer. So it's terminates. And then you're just there with the tight binary that just from this kind of stable manner. It's not,
Probably does. I mean, that's kind of, I think, what Brian argues for with this
very general, I don't like
thing. It's kind of the picture that you're painting. There is dynamical interaction, it spirals in, then it stops. Like I think he came up with this idea through the common envelope. As you spiral in, the density decreases because you're expanding the envelope. That's removes the drag.
So which big photometric surveys?
And then you stall. And then Brian's model is that, well, then the long-term evolution of this thing, depending on the delay when you stall and when you actually end up merging, gives you the whole sequence from
SDSS DR18 is coming out,
and
SDSS 5
model. So that's very close, I think, to what you're
DR18 infrared high resolution spectra.
Yeah, he was specifically for post-common envelope, and you're thinking of a generalization of that. I think it's a similar idea.
Well, they have a variety. They have like large
This is more than
set of
half of the like sort of retraining.
And but what does it mean tidal translation, by the way? Because what happens
There's
is
the
the
local
mass
volume
wanted to
wrapper,
be very
that
disk,
might
and the
be
tides don't allow
That's
it.
what the mass.
Exactly.
Milky Way happens.
Yeah. But then you're losing it mostly from.
I think it efficiently loses its angular momentum.
Actually, yes, that's.
Migrate.
Don't use it as spectroscopy.
Like,
Maybe I don't want to like when no. The thing is when photometry puts in first and it's nice Roche geometry that doesn't detect some and so say that's you have the Roche potential.
I mean, Gaia is more sensitive to, at least now, astrometric variations with strokes wider binaries. So likely not interacting.
The material that's not rotating doesn't obey that potential anymore.
So in a
So then because you have the Coriolis force added on, basically, right? That's the only thing
something that's clearly changing the
Yeah.
period.
And then this gets like
Yeah, okay, fair enough.
this really says, Coriolis.
But I mean,
Can we
they
see that
even
again?
invite
Was
like
the paper somehow arguing?
It's in a binary.
It's driven away outside.
Okay, but I think so, yeah.
That was
I
kind of,
guess,
I think, the
kind of a
sketches
highway.
part.
Not entirely sure.
Explain like how it gets there.
It's just that it uses it as a
But
sort
he
of
did cite
highway.
this.
Right, yeah, exactly. I mean, it could be gravitational waves.
Which is kind of related to that you mentioned binary pulsars and the decay of
This
gravitational wave.
my mission start working if you're massive enough because you're L over M
Or anomalous
the loss
surface
and that can trigger
compositions. I mean, we showed, and I think a lot of people showed nitrogen enhancement, but how do you
yeah, the
disentangle
donor two that's
from
what I
just
thought should
inherent,
work. Yeah, so
like
both of
rapid
them.
rotation versus spin up? Yes.
Interruptive mass
Yeah,
loss
I've had
event that, yeah,
One interesting thing that wants to do with switches on
But it's just
Very high initial rotation.
basically put our accretion disks around stars and just see what their contribution to their light curve would be.
It was like a very old.
And see if in the Gaia HR diagram.
What about in evolved? What about in evolved stars where they should be slowly rotating?
Right, just.
But I guess if they already had anomalous.
Here, you're getting the star out of the
Excess.
They already had anomalous enhanced nitrogen on the main sequence, they would still have
And
it.
that's the only thing that happens, yeah, the mass is growing, like, it grows on a logarithmic scale in luminosity, and it grows a little bit.
Was there runaways?
I mean,
also what the runaways done.
So that's a level of detail that's quite important.
Mass and luminosity, but
It's like a next order thing to look at, but definitely.
and so these could also, but these
They're
would
very
be
close.
mass dependent. Like a low mass star will.
It's related a lot. That's very nice. Evaluate the masters.
That's actually. If it becomes an AGB because it's floating that much, then it's not true that even the low masses.
I mean, if they just say like, oh guys, we're interacting, we're transferring that, just so you know.
I think it's
Like one line in one band.
Yeah, it's a sort of like, it's a sort of signal, like 100% correction rate. Mass.
Yeah, but if that mass is ejected fast compared to your orbital velocity, it's kind of a cloud.
Hey, also, who's going to
Assuming that the ejecta are fast compared to the orbital velocity, which extremely difficult, especially late.
Oh, yeah. Well, that's what happened to me last round. I don't think it's.
Becoming that rather compact thing, in this case, velocity.
We have to make a slide again?
So that might be.
I mean, it's probably good.
But like, do we have like the slides? Yeah. Are we supposed to add stuff too, or?
White binary. Maybe it's the same thing?
Well, I actually, there is also, if you put it too short, right, there is no disk because the stream directly impacts the star.
So you go from none to big.
Yeah.
And if the mass is driven away from the edge of the disk, then you have much more surface area.
Okay, no slides.
Is it public available?
So it's SDSS5 is currently taking data, so I don't know when the first data release is going to.
They made you just
That's how I see it.
Yeah, this is practical.
Well, I mean, this is long telescope at Apache Point Observatory. I can.
So then the argument is there, like here, no, because I know all the Europeans, so probably not. There is like a star here. Not a star there, so I would expect they're not symmetric.
Yeah, so previously, I mean,
Because the
SDSS
disk itself is deformed.
in its first 3 or 4 iterations was mostly galaxies, but was also doing stars. And then the big stars component was apogee. Now SDSS 5, like the apogee mission or survey is complete, and they're transitioning to Milky Way mapper stars, and then I don't remember.
That's what I simulation like.
That seems like local volume mapper might actually be
Like,
galaxies.
no, there's another like thermal.
Yeah,
I wanted
yeah, so
more than
I'll see if I can find out for you.
Doppler things. Yeah, so, yeah, there you go. Yeah. And then physical as
that would not change the J dots that we're using in our one-day simulation, but I'm thinking in terms of creating trap around the system, but then long after the interaction, you have this light bulb shining on the top. Well, it could, like, original models for 87A were trying to explain the rings of 87A just with.
What is a nova? What does a nova do? It's basically a large expanding. You know, right? It's like a flash, and then
maybe you don't need a feature as prominent as the rings of 87E. Maybe there are like
talk about the rest.
The rest of these things. I mean, in a sense, the
I guess
nebula thing.
Also in principle, it should be
like this. Yeah, and you could have that, and in that case,
there's going to be a couple
they have massive star.
I like dwarf novae. And that indicates accretion disks. And their periodicity.
It would feel like it
would be like the creature's wind is significant and significant.
A lot of things look like that.
That's probably very fair to say too.
And then you would,
and those other things, are they not mass transfer related?
No.
I guess you should find for binaries with like post-interaction binaries and look for.
But I mean, I won't say. But I don't know like how easy it is to look at like have one feature.
Yeah, there are many things with
like
even
what kind
as
of follow-up we need.
as it claimed so bad.
I guess if you saw it,
then it also has a joke.
It helps in light curves of Markov.
People say, no, it's the chat.
Then you can look at the recurrence time scale.
I don't think they're mutually exclusive. Actually,
it says something about the system with mass transfer.
There's also a time scale. If you look for classical nodes, you're going to see those over years. Right. These are going to come back.
Yeah, like months.
So like if you have tests,
but the thing is, like I really appreciate this argument that I made earlier. I don't think we have a good observational reason.
But then yes, there might be other things that
bring in strong.
Oh yeah, but that's a fine indication of that it might be. Right, exactly. That's fine. That is all fine.
Mass transfer things don't seem to be
good step in the right direction. Yeah. Test, recurrence, time scales are fine. Yeah, okay. I mean,
yeah, that's true. In terms of the nebula,
it can take longer, but
the amount of mass that ends up there might be different.
Novae, super bright.
In terms of just an outflow and populating, like coloring.
It's like transient. It's a transient survey. I mean, if a novae goes off, well, there's a interactive binary right there.
Yeah. I mean, to have the angular momentum transported at least, there will be some local magnetic field. What I'm saying is that we don't need to impose.
I don't think they're going to be right at all. Likely, and maybe a spectral signature. I think there are papers on this.
Local magnetic fields. I mean, yeah, these things are rotating. Presumably, there is a stellar dynamo in there. Well, that's
should be hot.
Yeah, but that how does that? No, it doesn't. Okay.
And is there something from gravitational waves that clearly indicates that there is mass transfer? I know that there is systems in which we expect mass transfer to occur and gravitational waves.
Well, I think it's like you just don't see anything in the
I think that is a possibility. If you need
you need
That's
to
all.
detect
And speculate.
This will need some local magnetism.
It's not vice versa.
As long as you have a gradient in pressure, you can travel away, whether it's like radiation or something else.
But what if the magnetic field actually cages?
Well, but maybe it would make it seem.
Yeah, gravitationally interact.
Yes, but the eclipsing will help with seeing how things change over phase. And so if there's something like a hotspot,
Reconvene in probably a few minutes.
but
At least you're all in this room.
Might be part of the things that drive then the orbital.
that's a hard giveaway for.
Why not? I mean, I think you're right, but I don't think that we know that this is definitely not happening.
Oh, I mean, yeah. We're not talking about the probability of these systems being detected. It's how they're moving. No, but it's like what giveaways would you look for to infer interaction?
Well, magnetic braking for massive stars. Basically following the idea that you just brought up. So this is probably with the stars.
So I guess it would depend whether or not it's like a star and an interaction. A planet around the star, and sometimes
magnetic braking needs to be connected to
planetary
There's
engulfing.
a theory that
needs to drag angular momentum.
which needs to the tubes needs to got right?
Yeah, but the magnetic field line that it's
Something like this, basically.
using that delta M is using as a lever to torque your star has to go. Well, if it's the star that you're torquing, it has to go in the star. If you just want to torque the disk, maybe it doesn't need to go in the star. Yeah,
Tidal interaction and mass.
Going back to like the sources, just come up with some conservation of momentum. Maybe like outflows from the outflow.
Yeah, there is this tidal interaction is
That's another source. That's a thing to do. Synchronized.
Out of it is not, then gives you some part of the orbital angular momentum will be transferred between the
Yeah, that's crazy. No, it's actually super impressive how they managed to improve those things and actually you see spiral arms.
But that should leave like a very structured nebula around.
Like this maybe we can mention non-synchronous binaries. So if they're not synchronized, that means something recent, very recent.
Oh, right. I'll put this on the.
We are now finding systems that are less than normal time scale.
It's more of an effect.
Right? The donor star is still out of thermal equilibrium. But that's
right. So
around those you should be able to see any of the
so clearly asynchronous
just
systems
so young
that
right?
interact.
I mean the
close
time
enough to
scale
found something.
of the star is going to be much shorter than the time scale of the interstellar material that this star
You would not see these kind of it's a long that's actually true. To try and L over M up and have mass loss events, right? You do need some amount of thermal time scales of the reader to really like structurally respond.
Oh, but I thought that like I'm thinking of a scenario where you have like case B mass transfer, say, where the accretor during the mass transfer goes through burps, and then you catch the system once it's a strip star that is contracting left, but the burps have happened before during the mass transfer. The thermal timescales were during the mass transfer. I don't know if it makes sense. Actually, I didn't. Yeah, in Palmer. around, like, yeah, you like those stars, we report by them. Look around the stars now.
But at least we can see that we have different mechanisms. Because that would be, I wouldn't see why it shouldn't be spherical. Well, at least, it's spherical.
All right, I think it's time to head back in.
Maybe okay, wind, mass loss, not so much. I think it's also spherical from one star in a lopsided binary, the frequency. So it's spherical, but in a wrong reference frame. So I'm not sure it's spherical. I'm not sure if it's that giveaway, but.
No, I think another dog.
Right now, any takers from wind slides? Remain and
They're just always staying outside, so they don't have to.
There's a reception. Maybe it also showed that, like, even.
I don't think I totally.
Okay. I am assuming that it is so good. Synchronous donors. So definitely anything out from the previous dimension could fall back.
Nobody was
also
nobody can reason about.
I actually wonder if that's why we see so many circular equatorial things. Maybe on the equator they don't really leave, then you see them, while along the poles they're faster and
Binaries, compact binaries. Doch, we machen jemanden schreiben das an. I think people, typically, because this is using telescopes used for apogee, so Apache Point Observatory in Las Colinas. Seeing those with the workshop so far, we make a photometric cut based on H-band magnitudes. I don't remember what that is. It might say it on here. So I don't. How would we basically just? It could be totally not relevant to you at all. But I would send it. Yeah, it is right. Like in the beginning, was like.
I've done it before, not big beat.
Demonstration.
You can't tell.
You're more expert.
Oh,
I think that's a fair statement based on the last discussion.
It's just
that on
I know we're not or like
maybe show that and put it on the slide or directly on the slide.
I don't think so.
I think it's going to.
Time and also. Yeah.
Drop the movement and.
I would love to, yeah. Because I think this is the paper she talked about. We don't have much to ask. I wear a watch, but I think afterwards I'm like a board game.
I don't know.
All right. Is everyone back from the group discussions? I don't know if there's still some people outside, but I guess they'll realize. Okay, so we don't have super much time before the reception, which is in the other building. So the idea is just that someone from every group comes up and gives a very brief summary of what was discussed for the rest to also get a idea. I don't know if anyone made slides.
We made a slide.
You made a slide? How do we?
I didn't see where it was. Was it?
You can just bring up your laptop.
Yeah.
All right. So should we just start with question or group one? Anyone from group one? Yeah.
I have a plan.
You get like 3 minutes. Is that okay?
Okay.
Okay. Does this work? Yeah. Right. So we were mostly theory people in group one, although we were talking about observations. So if we say something insane, you know what happened there. Okay. So the clear things that we think we should look for when we're talking about systems that are currently undergoing mass transfer. So we thought we could do Doppler tomography in closed binaries that show accretion disks. Accretion disks themselves, so if we can detect something that must be an accretion disk, then that is indicating mass transfers going on. Stream hotspots, which would show up somehow in light curves as well. So it should be like a component in there if the binaries are eclipsing. And then eclipsing binaries in general could indicate that if the period is short enough, it can indicate that these guys should be going through mass transfer because they're short enough to be interacting. Also circumbinary disks, this we're not quite sure where we would be the best place to detect them. We were thinking infrared, but I'm not sure if that's the best way to detect a circumbinary disk or not. And also nova should be super bright, so that should be visible. Dwarf nova as well, like we can look at light curves with tests or something and look at the recurrent time scales of these things. Then there's also the question, like, can we be sure just looking at a light curve that the system is a nova or not? Because a lot of them, like light curves are basically going up and down, right? So I don't know how unambiguous that would be. And then also in general, like some kind of outflow that we could see in infrared. And then this is a bit of a like cheating a little bit, but BE systems, if we look, I mean, they should be post-interaction, but if you have a companion there, then they are interacting now again for the second time. So because the companion is accreting, and that should be stable. So we can also look for that. And jets, I mean, if something has jets, it has to be accreting something, right? So jets. And then talking about effects of post-mass transfer, as in we're thinking, if the system just finished mass transfer, what are the things that we could look for? So this is cheating again a little bit, but like rapidly rotating things that should not be so rapidly rotating in principle. That can mean that they just went through mass transfer, stripped stars, blue stragglers, and yeah, I don't know what we wrote here.
Asynchronous.
Asynchronous, yeah, but that was what do
Low
we
mass
mean?
white dwarfs. Low mass white dwarfs.
Low mass white dwarfs, yeah. Yeah, and then in general, thinking of what are the observations that we want to look at. There's, of course, TESS and OGO and Plato in the future, SDSS, Apogee, and of course, Gaia. Okay, this is what we discussed. If actual observers want to say something.
Any questions or comments?
Lisa, maybe?
Lisa, yeah, so we were looking at Lisa, and apparently there's a paper saying that if we look at the frequency of the gravitational wave, like the change of the frequency or something like that, you can tell if the system is transferring mass or not. I have no idea how that works, like how.
If the orbit is widening, then it's mass transferring.
Great. Oh, so that's great. So we can use Lisa, that's amazing.
Any other comments? All right, then we go to the second question.
Isn't will also be able to tell?
Yes, that's it. Can you hear me? Yeah, I guess so. So the question was, what are sources of, well, basically pre-dynamical ejecting stellar mergers, or just in general mass loss from the binaries? And I think that if I just draw a diagram, that would be quick rather than just having to explain it all over. So if you have a Rostov overflowing progenitor here on the left, well, first of all, here on the accretor, you're going to form a disk. That's, I think, well established. Well, depends on many circumstances, that's fine. One thing you can think of is the fact that the disk should lose mass where it through sort of winds. Now, the way it actually does this, that's debatable in a sense. But this could be sort of the geometry in a sense. I hope that the people on the left can see it. Okay. So that would probably produce a sort of, I don't know, polar-ish geometry for this. Otherwise, you can think of the ejecta from, well, not ejecta, but in a sense, the mass that spews away from the outer Lagrangian points. So in a way from this point over here
And also this point over here, depending if you prefer the donor or the accretor doing this, but then this would produce probably something that will remain across the orbital plane. So that's a different geometry for the material. Then, well, of course, the accretor itself could have some sort of polar outflows because of winds. I say outflows, you could say jets. And in that case, well, that has another kind of geometry per se. And am I missing something else? What? Oh, yeah. So the fact that you have mass transfer changes some things in the L over M of both the donor and the accretor. In the case of the donor, well, the luminosity can stay roughly the same, but the mass will decrease. And in doing so, the L over M will increase. And so you might have that it's unstable, and perhaps you might undergo this sort of burps of mass. And if it does that, what will geometry look like? Well, again, not so sure. Maybe it will be sort of a shell, but then, you know, how will it be spherical? It's still in a binary, so maybe it will be just sort of a half shell, sort of. But the same also applies for the secondary, because the accretor in this case, the luminosity will increase, while the mass will increase, but not so much. And so you might have a similar contribution in this sense. And I think I've said all that there was to it, I hope. So.
All right, thanks a lot. Any additional comments, questions, anything?
Couldn't have been that clear.
We kind of, yeah, we're short on time.
Just one tweet.
All right. So thanks again, and let's move to question 3.
Okay, so we had identification of merger products. I wrote all these notes after the discussion, so they're a little bit haphazard. But we had so you can get the magnetic field. I didn't know this. You can get it identified from spectral polarimetry. So this is something that you can measure fairly easily, I guess, in stars. And when you have a merger, the idea is that you become potentially you become rapidly rotating immediately because you have all the angular momentum from the binary before the merger. In which case the new product is rapidly rotating, moves redder, spends about a thermal timescale there until it relaxes back to the blue, where it might be identified as a blue straggler. In this case, I'd asked why this is not necessarily a fast rotating system if it's kind of recompressing. And it's because the outer layers can couple either through sprout dynamo or magnetic fields. You could spin down effectively. It'll couple to the core, and then you have a slow rotator, even though it had this very large radius initially. The blue supergiants are not blue because of their composition, but because of their different structure. Their internal structure keeps them unusually blue. You might also immediately get slow rotators. This is the result from Fabian Schneider's group, that you don't necessarily keep all the angular momentum in the final product right away. Your low mass main sequence mergers may be red for, if it's on the thermal timescale, maybe 10 million years. So it might be quite hard to imagine. Well, you might actually see many of these still quite red, but also with these high magnetic fields. Unless you have magnetic field decay on, it can decay on a 10-year time scale, potentially, depending on the initial geometry. I didn't quite understand the argument, but that was something that came up. And then we discussed a little bit how you could estimate the ejecta mass of the merger from the debris disk around the circummerger debris using these density momentum arguments. Questions?
I don't know if there is any.
Comment related to it. So I was going to say, in this particular case of this central object of the blue ring nebula I talked about, it is a very bright X-ray source. So it's very X-ray active and relative to other stars. So I think these types of systems, if we can find post-merger systems that, we can actually measure the properties and we're confident that that's what's going on, I think it's interesting. So anyway, it's just a comment.
Agree.
Any other questions, comments? Yes, no, maybe? Okay, then we move to question 4.
So 4 didn't form a group, but I made a slide.
On my show. Wait, that's perfect because Katie also.
It's nice that it's organized. So.
Should be working. Okay, do high mass strip stars have nebula or outflow? Yes, they do. So here I'm showing 2 images. These are 2D spectra. I feel like pretty much everybody in the room already knows this, but just so we're on the same page, these plots are showing wavelength on the x-axis and spatial extent on the y-axis, because when you have a shell spectrograph,
That is not a board.
Oh,
Not a board.
sorry. Over here.
Oh, that's not a board. Just throw below.
Is that a board?
That's a board.
Okay, sorry guys on that side of the room. When you have a shell spectrograph, you place a slit on top of your star and you have some of the background on either side of the star. So this is the spatial dimension I'm talking about. And when we look at some of these forbidden lines in these strip star systems, we're seeing symmetric nebulae in some of them. So a naive interpretation of this could be common envelope. And in the case of an asymmetric outflow in this system, maybe this is L2 overflow coming from these systems. So yes, we do see this.
Yay.
I actually have a question about this. I'm just going to go. When you say symmetric, you mean symmetric along one axis, right?
Yes.
You didn't flip.
Yeah. So one of the things we want to do is that because we have many epochs for these stars, you can imagine adding all of these different angles up and maybe you can get a 2-dimensional profile of what it actually looks like. So this is a very limited picture of it, but yeah, that's something we want to do.
Taken into field spectrograph. Any other questions? Comments? All right, then let's go to question 5.
Stressed about this. Okay. Maybe. There she is. Good. Okay, so we had a group with lots of, I think, theory-focused people and some observers. So we thought about a bunch of different reasons for why we don't see specifically giant formed luminous red novae. And I think the main thing is that it could be the case that we do have them in data. It's just that they're infrared transients that don't have optical counterparts. And so if you require that they are optical counterparts to like make yourself believe that this is a thing, then you're just going to miss them always. A good potential place to start digging is the 70 or so transients that are in like this sprites catalog that came from a Spitzer survey. And there are 60 of them that don't have optical counterparts. Contamination is probably a thing that we should think about. And then we went off on a big aside where everyone yelled at Emily for being an observer for a second. And that was fine. And then we decided that probably it's the case that Roman may also be really helpful here and that there are target of opportunity
like options here. So maybe something that if people are interested, they should consider that. We also spoke for a bit of time about the idea that maybe like we know that planetary nebulae are post common envelope systems, at least something like 30% of them. So could the non-spherically symmetric planetary nebulae like be these types of systems, but with a helium star in them? And we spent a bunch of time kind of like musing about like, oh, well, most planetary nebulae we see because there's a white dwarf that's ionizing all that gas and like lighting it up. But there are pre or protoplanetary nebulae that could be connections to like helium star style planetary nebulae. So I don't know, something to think about there. And then we got some like amazing information coming from Natasha here. So one thing that's completely bonkers to think about, and there's a bit of a brain breaker, is that if you have a failed common envelope with say a 10 solar mass donor and a 2 solar mass donor, you could imagine that the common envelope ejects the 10 solar mass donor, then there's a merger that puts 2 solar masses on top of that stripped helium core. And the star is going to continue evolving the way that it does because of the helium core, but it's just this like under massive giant star. And we don't know anything about it one way or another. So maybe this is happening. And Emily pointed out that there are observed systems that are giants that are either over or under mass for their given cluster. So maybe that's something that we should be paying attention to. We said the word astroseismic effects and everyone was like, we don't really know. Maybe we could see them though, because the relaxation of this new type of red giant would be probably faster than thermal because of the high luminosities. And then finally, just in general, we thought about general differences. And this hasn't ever been really computed with models, but in general, because you're dealing with giants, the escape velocity is likely to be slower. So the plateau will be longer and dust formation starts to become a problem that could just completely like mess everything up. That's what we said.
Any comments, questions? Or is everyone ready for the reception?
The spirit survey with it's Castival et al. I don't remember the review that they just
we'll put it in the slide.
If you want to look for the sprites, it's the spirits survey. So the Spitzer infrared transient survey, and Castival is the Mansi Castival is the first author. I forgot the year.
We'll put it in.
There's also going to be some new candidates coming out from Kishaloy Day.
Yeah.
They have a bunch of wise data where they see I don't remember many more than this sprite. So yeah, this sample will be growing even with what we currently have. But it will be great to have Roman. I agree.
Good. That's what we meant by other, because we didn't have a thing to link to yet. But we're very excited.
I have a question about this 10 solar mass star with a 2 solar mass star, where you remove the envelope and then merge and you reaccrete the 2 solar mass star. And I'm wondering if this could also happen if the masses were like 10 times lower. So if you have like a 1 solar mass star plus a say 0.2 solar mass star, and if you can get the same effect or not.
That was just a vague speculation about whether it could happen. We don't have yet common envelope produced for the 10 solar mass donors in the proper way. So it was just a very, very big speculation. I mean, if 1 solar mass star will be able to remove the envelope from 10 solar mass giant, and then we'll little bit re-expand and accrete. I mean, everything could happen, right? But it so I mean, sorry, it was just a wild speculation about a possibility, but to go to precise numbers, no. Don't quote me for that.
Well, like 1 with a, you said like 1 with a like 0.1.
Well, O.Y will be just likely mixed up inside the envelope. It will be not removing the envelope.
Private communication.
It's going to be in a paper.
And I'm blamed for the rest of my life.
All right.
That's 5.
There were
No,
there were 5. Number 6
Yeah, because
merged with.
Six is here.
Ah, no, sorry.
Wait, is there?
There were six any more questions on 5, right?
No. No, there was six. Okay. And Katie again?
So what I have prepared is not as neat as Katie's, but I did spend time writing it down, so I'm going to show it. Big.
Plug it in.
Okay, this is as big as it goes.
Can you make it a bit bigger? Like command plus?
That's as big as it goes.
You hold command plus.
That's what I'm doing.
Oh, really?
Yeah. Because the display is wrong.
The resolution is like what? Right.
Is it that? Oh yeah, that's fine.
There's a view into the top.
Okay. So yes, we spent a lot of time talking about LSST. That'll bring a lot of luminous red novae. And an exciting thing about this is that it might also bring pre-imaging of progenitors. So just a variety of transients. We can also learn about what type of galaxy it came from the spectra. So this is not just related to luminous red nova, but just in general from the spectra, we can gain information about how the velocity of the material, the ejecta mass. Yes, and it might be really exciting to see a remnant binary in these surveys. And a big question is how can we prepare for all of this incoming data? We also talked a bit about LISA. I'm not very familiar about on AMV CVNs, but Sylvia brought them up that they might be seen to be widening systems. And there could also be imprints of mass transfer physics on the gravitational wave background of double white dwarfs. Brian also talked about this V1309 SCO, which could be a blue straggler in the making. And then these are all just a bunch of other random things we talked about. So a very interesting thing seen in CVs is that CVs that white dwarfs in CVs are systematically more massive than single white dwarfs. So an idea might be that these low mass white dwarfs are becoming unstable and not leading into these CVs. So that could tell us a bit more about binary physics. And then, yes, I think the most interesting one out of the rest are these supernova explosions. So in addition to the huge diversity of composition features, there are also features of binary interactions pre-explosion. So I forgot the one that was mentioned, but this is the one that I remember. So trying to explain these bright supernova outbursts as super Eddington accretion onto the compact object right before the supernova happened. So this can try to bring in sort of what we expect the population of pre-supernova binaries to look like. So.
Any questions, comments? Anything to add? Okay, then Lieke, you have some practical. First, thank all the speakers and people who put beautiful slides together and discussions together again. Okay, and thanks Julianne and Brian for leading this last hour, obviously. We have two short announcements. The first is I would love it also if all the people who made slides and discussions and summaries of those, please upload them on Slack if you want to They're very useful resources. And then second, now we're going to the reception, which very luckily, we managed to move from this dark windowless space to the roof of the other building. The side notes are that you cannot just enter and leave that building at wish. So we all have to enter the building as a group. And I don't want people to be lagging behind. So my chair is going to lead the group, and I'm going to close everyone out here and chase you away. So what's going to happen is you should all gather your stuff, because you will probably not be coming back here today. Take it all the way up to the reception. We'll have drinks. You can continue your conversations there. And then, yeah, Jared?
Oh, before everyone gets up, I do have one announcement as well. So
Okay, yeah, and I did want to say, so when we're up at the reception, there will be substantial hors d'oeuvre and drinks. You might still want to get food afterwards. Note that Jared and I will have to close the reception as well. So you have to be gone before Jared and I are gone. That is.
An organizer needs to remain at the reception until everyone's gone. One more announcement is that we've posted in the Slack a link to a follow-up survey to our first one. I'm curious to see how your answers change or don't. So please, let's say before the end of the coffee break tomorrow, and I'll send it in an email too, but before the end of the coffee break tomorrow, please fill that out. All right.
Okay. See you on the roof.
See you on the roof.